Welcome back to the Deep Dive. Today, we are giving you the ultimate shortcut, a way to deeply understand the absolute bedrock technology of modern business data, the relational database. If you're prepping for a big project, or maybe you're just catching up on the architecture that underpins your whole company's analytics, or you're just curious about how all this structured data stays reliable, then this is definitely the deep dive for you.
And our mission today is very laser focused. We're going to extract the core architecture, the capabilities, and this is the important part, the limitations of relational databases, or RDBs.
Right.
And we're going to do it specifically through the very demanding lens of modern data analytics. We have to move beyond just the simple definitions and really get into the why behind their design.
Especially the trade-offs, right? The things that dictate analytical speed.
Exactly. Those trade-offs are everything.
Okay, let's unpack this with the absolute fundamentals. We're starting with a crisp, non-jargon definition, which I think the material we looked at summarizes just beautifully. At its most basic, an RDB stores data in these highly structured units called tables.
Right, which computer scientists will often call relations. It's the same thing.
The same thing.
And you can think of a table as a sort of blueprint for a specific category of information. Each one has two primary, very predictable ingredients. You've got rows, which, represent individual things.
Your record.
Your records, exactly. So one single customer or one specific order that they placed.
And then you have the columns, which define the characteristics of those records, the attributes. So for a customer table, the columns might be something like customer ID, first name, last name, and maybe shipping address.
Precisely. The structure is totally explicit. Every column has to conform to a specific data type, a number, text, a date, and each table has to represent a distinct entity.
You wouldn't just mix customer details and, say, product dimensions into one giant, messy spreadsheet.
You wouldn't, or you shouldn't. You keep them separate.
But, okay, if they're separate, how do we link Jane Doe to the 100 products she bought last year? I mean, this is the core magic, right? This is what makes the system relational and so powerful for analysis. The separate tables are connected, they're linked, through these predefined mechanisms we call keys, and they establish these very structured relationships between all those different data elements.
And that explicit structure, the fact that the relationships aren't just, kind of implied or based on matching some text, but they're mathematically defined, that is the governing principle we're really digging into today.
And it dictates everything.
It dictates how you query the data, how it maintains its integrity, and, ultimately how fast you can actually analyze it.
All right, moving into our first major section here. We really need to stress that the relational model it's not just a convenient way to store data. The sources we reviewed really highlight that it's rooted in these formal, pretty profound theoretical principles.
Oh, absolutely. It was developed by E.F. Codd back in the late 1960s, and it was based on mathematical set theory and first-order predicate logic.
Okay, so that sounds very academic.
It is.
Why should an analyst care that it's based on all this formal theory?
Well, because that grounding is what guarantees data integrity and reliability. It's not just a file system, it's a rigorous model based on relational theory. And that theory, it prioritizes two non-negotiable concepts. Logical consistency, meaning the data has to follow the rules you set, and explicit relationships, which you just mentioned.
So when you're running some complex query that's going to determine, quarterly revenue, you need absolute certainty that the underlying math holding all that data together is sound.
You do.
And that the relationships you're relying on are, unambiguous.
Exactly. And the research details the specific mechanisms used to enforce this integrity, the primary and foreign keys. Let's start with the primary key. It's the unique identifier for each individual row. It's the fingerprint.
It's the fingerprint. I like that.
If the data is modeled properly, every single row in that specific table must have a primary key, and that key has to be unique, and it can never, ever be null or empty.
But wait, if the primary key is the fingerprint, isn't there a huge risk if a key is generated poorly? Can you give us an example of a common data integrity failure that a primary key actually prevents?
That's a great question, and it really gets to the heart of why this concept is so necessary. Imagine a data entry error. Two separate customers, both named John Smith, are accidentally assigned the exact same internal ID number.
Yeah, happens all the time.
All the time.
Yeah.
Without a primary key constraint enforced by the database itself, the system would just happily accept that duplication. It wouldn't know any better.
And then what happens?
Well, then an analyst later tries to pull John Smith's purchase history, and what they get is this messy combination of two different people's data, and that leads to totally incorrect metrics like lifetime value or churn rate. The primary key constraint prevents that fundamental confusion. It ensures every record is a distinct, identifiable entity.
Perfect. So the primary key ensures uniqueness within a table. The foreign key, then, must be the mechanism that ensures referential integrity between tables.
That's it. These are the references used to connect the separate entities. A foreign key is just a column, or sometimes a set of collars, in one table that refers back to the primary key in another table.
So in our order table, we don't store the customer's entire name and address every single time they buy something. That would be crazy.
Insanely redundant. Instead, we just store a foreign key, the customer ID, and that little number links the order back to the unique primary key in the customer table.
So if the primary key ensures that Jane Doe is unique, the foreign key on the order table is the explicit codified mechanism that guarantees that that specific order belongs to that unique Jane Doe.
And the relationship is enforced by the database engine itself. It's not an optional thing.
Without that, linking a customer's past purchase history to their current profile would just become a fragile assumption-based nightmare, especially when you get to scale.
An absolute nightmare. And those two concepts, primary and foreign keys, they are the real scaffolding of the entire relational model. They ensure that integrity remains constant.
Okay, now let's move to a concept that is structurally essential for maintaining this integrity, but which, and this is kind of counterintuitive, it becomes a real analytical headache. And that's normalization. The research details that data is stored in normalized tables with these very clearly defined schemas.
Normalization is the formal process of structuring the database to minimize redundancy and eliminate what are called data anomalies or errors. And if we think about this process in stages, we usually talk about the first three normal forms, 1NF, 2NF, and 3NF, because those are the most relevant for business systems.
Okay, let's start at the beginning. First, normal form, 1NF. What does this actually achieve?
1NF is really simple, but it's crucial. It just states that all columns must contain atomic values.
Gotcha.
Meaning single, indivisible pieces of data. You can't have a single column called, say, phone numbers that contains 3 different contact numbers separated by commas. Each piece of information has to live in its own cell.
One value per cell.
One value per cell. It ensures that every row and column intersection holds only one value.
Which makes searching and querying infinitely easier, I'd imagine. So what about second normal form, 2NF?
2NF, it addresses redundancy that's related to what are called composite keys, so keys made up of more than one column. It requires that all the non-key attributes must be fully dependent on the entire primary key, not just part of it. The goal here is to prevent these partial dependencies.
Okay, that's a bit abstract. Give us a quick example of a partial dependency that 2NF would solve.
Sure. Imagine a table that's recording products sold and the supplier for that product. The primary key is composed of 2 parts, product ID and supplier ID.
Right.
Now, if the supplier address is also stored in the same table, that address only depends on the supplier ID, right? It has nothing to do with the product. So every time that supplier provides a new product, we redundantly store their full address again and again and again.
I see. So 2NF would force us to move the supplier ID and supplier address into their own separate supplier table.
Exactly. And that eliminates that update redundancy completely.
Okay, so 1NF ensures atomicity, 2NF removes partial dependencies. Now, the gold standard for most transactional systems is third normal form, 3NF. What's the final purification step here?
3NF eliminates what are called transitive dependencies. This means a non-key attribute cannot depend on another non-key attribute.
What's an example?
If you have a customer table and you store the customer's zip code, but you also store their city and their state in that same table, well, the city and state are determined by the zip code, not by the primary key, which is the customer ID.
Right. So if that customer moves, you might have to update their city and state in multiple places if they were also stored in, say, the orders table.
Precisely. You've created an update anomaly waiting to happen. 3NF dictates that zip code, city, and state should be split into their own separate dedicated zip code lookup table. The customer table only needs the zip code as a foreign key.
And the benefits are huge.
Massive. You only store that location information once, update consistency is guaranteed, and your overall data accuracy is enhanced significantly.
But, and this is the big but, this structural perfection comes with a serious cost for the analyst. And this is where it gets really interesting for our deep dive. While normalization is the absolute key for integrity, The research explicitly notes that this very process may reduce analytical query performance.
And the reason why is because to answer a really strategic business question, something like calculate the average order value broken down by customer region and product category for all sales in the last 5 years, the system has to perform this intensive logic.
Yes, to stitch everything back
It
together.
has to stitch together not just 2 or 3, but potentially dozens of these highly normalized tables on the fly.
So you have to join the order table to the line item table, to the product table, to the customer table, and maybe even to that separate zip code lookup table we just created.
And every single one of those joins is a resource-intensive operation. When you are dealing with a normalized database containing petabytes of historical data, that intensive linking process can slow down those massive read-heavy queries that analysts rely on to a grinding halt.
Wow.
And this tension, this fundamental conflict between data integrity, which is normalization, and analytical speed, the need for fast joins, that is the central architectural challenge we're going to keep coming back to.
So we enforce perfect 3NF in our transactional systems for accuracy.
But then we have to find clever ways to undo that separation later for reporting speed. It's a constant push and pull.
So we have this beautifully structured, highly consistent environment built on this scaffolding of keys and normalization. How do we, as analysts, actually interact with it? How do we pull out the critical business insights that are hidden across, dozens of meticulously separated tables?
Right. And the answer, as the material confirms, is SQL, or Structured Query Language.
The command center.
It is the command center of the RDB world. It's the standard language. And I have to say, possessing strong SQL skills is absolutely fundamental for any data analyst or data scientist working with structured business data. It's not optional.
And its functions are perfectly aligned with what an analyst needs to do. I mean, of course, the primary function is just retrieving data using the select command. But SQL allows us to offload incredibly complex work right onto the server.
Absolutely. You can do serious analytical heavy lifting with SQL, like filtering and aggregating data. You can calculate averages, sums, minimums, maximums, variances.
And even more advanced stuff, right?
Oh yeah, advanced analytical SQL features like window functions. They allow you to calculate things like running totals, moving averages, or rank customer segments without having to pull all the raw data out of the database first.
And most critically, as we just established, SQL is the tool you use to join multiple tables. Because the data is normalized and spread out, that join operation linking the primary and foreign keys is essential for reconstructing the complete picture.
And the complexity of your analysis often directly correlates with the number and type of joins your SQL query needs.
The material really emphasizes that the sheer power of SQL enables both these complex analytical queries and incredibly efficient data manipulation. If your data fits that structured model, SQL gives you a highly optimized way to slice and dice it.
It's a language that has matured right alongside the database technology itself for decades.
So once we understand that SQL is the language of this structure, it forces us to ask a bigger question. What function is this structure actually serving? Because a single relational database technology can actually be designed for two completely different business purposes.
That's right. And they require fundamentally different designs. The sources draw a really critical distinction between OLTP and OLAP.
This is a managerial distinction that, it really informs your architectural strategy.
It does. Let's start with OLTP. That's online transaction processing. This is the operational side of the house. It's the engine room of the business. Its purpose is to support operational transactions, things like processing a customer payment, updating your stock levels, or logging a sensor reading.
And because its primary job is to handle these high-volume, real-time updates, we're talking potentially thousands per second, the OLTP database has to prioritize consistency and integrity above everything else.
Which means its design is typically highly normalized. We're talking 3NF or even higher.
The optimization here is entirely focused on write operations. Fast inserts, fast updates, fast deletions.
Yeah.
You need that customer transaction to complete instantly and accurately, minimizing any risk of data anomalies.
And that highly normalized structure ensures that when a record is updated, it's only updated in one single place.
Okay, so now contrast that with OLP, which is online analytical processing.
Right. The purpose here is completely different. It's retrospective analysis. It's for supporting reporting, running complex predictive models, or comparing regional performance over a long historical period.
And in the OLP world, speed is king, and the queries are these massive read-heavy operations. So to mitigate that normalization penalty we were talking about, the OLAP design is often strategically denormalized.
which is a fancy way of saying architects consciously accept some level of data redundancy in favor of query speed.
So the goal is just to make the joins simpler and faster. Instead of joining 5 small, perfectly normalized tables, you might design 1 or 2 very large, somewhat redundant tables that are structured specifically for analytical retrieval.
Yes, and this is where specific architectural patterns come into play, which are crucial for our informed listener to understand. While OLTP typically uses 3NF, OLAP often uses what's called the star schema, or a snowflake schema.
Let's focus on the star schema. I think that's the most common compromise we see. It separates data into fact tables and dimension tables.
That's right. The fact table holds the quantitative measurements, the facts of your business. Things like sales amount, units sold, or transaction time. The numbers.
And the dimension tables hold the descriptive context, the dimensions, so customer location, product color, or sales region. The who, what, where, when.
And crucially, the dimensions in a star schema are typically wide and flat, meaning they're somewhat denormalized. And the reason for that is so the analytical query only has to join the central fact table to just a few large dimension tables.
Which dramatically reduces the number of complex joins you'd have to do compared to a fully normalized OLTP system.
That is the architectural trade-off.
The key takeaway here seems profound. Relational databases can support both operational and analytical work, but the design, whether you're highly normalized for transactional integrity or strategically denormalized for analytical speed, it must reflect the primary use case.
Absolutely. If you attempt to optimize a single database for both simultaneous high-volume transactions and massive analytical queries, you often end up with a system that performs neither job particularly well. It's a compromise that satisfies no one.
Okay, so once we internalize that distinction, we can really appreciate the RDB's central, almost unavoidable role in the entire data ecosystem. Source 5 lays out exactly where RDBs fit into the modern analytical pipeline, and they're everywhere.
They are. First and foremost, they're the core source systems for analytics. If a company sells widgets, the RDB that processes the daily sales orders is the authoritative origin point for every single piece of analysis that comes after.
And as we just touched on with OLAPI, they also serve as the structural back-end storage for data warehouses. A data warehouse which integrates data from many different source systems into one unified historical view is almost always built on relational database technology.
And it utilizes those denormalized schemas we mentioned for faster reporting.
Furthermore, for the really deep dives into data, the material notes that RDBs are the starting point for a lot of data mining and machine learning workflows.
And why is that? It's because machine learning models thrive on clean, structured, and historically consistent data, which is the RDB's specialty.
So what kind of data is the RDB ideally matched for? It really excels where the data is structured and well-defined. If your data fits neatly into predefined rows and columns with fixed definitions, your ERP data, financial ledgers, transactional logs, the RDB is just unsurpassed.
And second, it's ideal for historical and transactional analysis, looking at patterns and trends based on clearly defined past events.
This naturally leads us to its core strengths. I mean, why does this decades-old technology continue to dominate structured business data? Source 6 gives us several powerful reasons that speak directly to an analyst's need for confidence.
The first one is very simple: reliability. We are talking about strong data integrity and consistency enforced by those keys and normalization rules we discussed. When your CEO asks about quarterly revenue, you need the numbers to be reliable.
Rock solid.
And relational databases provide that guarantee better than almost any alternative.
That reliability is also deeply tied to their maturity.
It is. RDBs are a stable technology. They've had decades of development, debugging, and standardization. The performance characteristics are predictable, the community support is vast, and the system failure modes are very well understood. And all that predictability reduces project risk dramatically.
And crucially, the support ecosystem is just unparalleled. RDBs are well supported by a vast ecosystem of tools. We're talking about every major BI or business intelligence platform, every high-end visualization suite, and all the standard statistical software packages like R and Python libraries.
The integration paths are standardized and robust. They just work.
They offer an efficient handling of structured business data that really no other technology has managed to entirely supplant yet.
Especially for core, highly regulated processes like accounting or inventory tracking, the RDB offers the perfect blend of speed, structure, and integrity.
Let's delve a bit deeper into that ecosystem integration, specifically how RDBs connect with these downstream tools, which Source 9 details. This is where analysts can save a substantial amount of time.
Right. RDBs integrate seamlessly using standardized connectors like ODBC or JDBC with statistical software, data mining platforms, and BI tools.
When an analyst needs to build a model, they're rarely working directly in the RDB environment for the actual calculation.
No, they're not. They query the RDB using SQL, and they extract the necessary data into a specific format that's usable for modeling. They're usually creating what we call analytical data sets or data frames.
And this is where the efficiency really pays off. Because SQL allows for such efficient querying, you can retrieve only the specific rows and columns you need, and you can perform complex aggregations right on the database server. It significantly reduces pre-processing time.
Let me put that into a really practical context for you.
Yeah.
If an analyst needs to calculate, say, a 90-day moving average of product sales and then flag every product that is 10% below that average,
A common request.
very common, they could pull all the historical data, maybe 5 terabytes of it, out of the database and then calculate that moving average on their local machine or in a separate cluster.
Yeah.
But that is expensive, it's slow, and it's computationally very wasteful.
But if they use advanced analytical SQL,
They can write a query that calculates that moving average and generates the flag inside the RDB using the database server's own power, and then they only retrieve a clean, small data set with just the final flags and results.
this is a huge insight for you, the learner.
Yeah.
By leveraging the database server's compute power, you not only save the analyst hours or even days of pre-processing time.
Will you save your company money on external compute resources? The data you extract is almost ready to use, and that minimizes the most time-consuming part of any analytical project, which is always data wrangling.
The structure and the language of the RDB really make it an analytical powerhouse for these known structured queries. But this deep dive wouldn't be complete if we didn't balance those strengths with the strategic limitations. For you, the learner, understanding when the RDB is not the right tool is just as crucial as knowing when it is.
Absolutely.
So where does this stable, structured giant start to struggle in the face of modern data challenges? Source 7 clearly outlines these limitations.
And this is really the driving force behind the rise of all the big data platforms we hear about. The first major hurdle is just big data scale. RDBs may struggle with very large-scale data. We're talking petabytes and beyond.
Especially when the growth rate is aggressive and it needs continuous expansion.
Right. And the reason why is because they were fundamentally designed to run on a single powerful machine or maybe a tightly knit cluster. And while that's highly efficient, that architecture eventually hits a physical ceiling.
The struggle is also compounded by the variety of data that organizations collect today. RDBs are designed for fixed schemas, which means they're simply not designed for unstructured data.
Right. If you're trying to analyze terabytes of customer service transcripts or geospatial sensor data or raw video streams, trying to force that information into the rigid row and column structure of an RDB is, well, it's inefficient at best and often impossible.
And third, there's the challenge of velocity. The traditional RDB architecture has a lot of difficulty efficiently handling high-velocity streaming data.
RDBs excel at recording completed transactions.
Wow.
You know, a sale occurred, inventory was updated. They struggle when data arrives continuously and rapidly, like real-time market feeds or millions of IoT sensor readings per second.
Those continuous streams just introduce latency bottlenecks that RDBs weren't engineered to overcome without extreme complexity.
And let's circle back to that fundamental tension we set up between normalization and speed, because it really manifests here as performance bottlenecks. Source 7 reminds us that those analytical queries requiring many joins can be slow when dealing with truly massive data sets.
This is the direct cost of enforcing that 3NF integrity at the operational level.
It's the physical reality of the database engine spending enormous amounts of time performing lookups and linking row IDs across different physical locations on the disk. For small data, it's instantaneous. For 5 years of global transactions, it becomes a major bottleneck that can render real-time analytics impossible.
And this leads us to the most significant managerial limitation. And it's often the deciding factor in strategic architectural shifts. Scaling costs. Scaling for RDBs is traditionally vertical. That means you upgrade the hardware of a single machine. You add more RAM, faster CPUs, bigger, faster storage drives.
And while that works up to a point, that vertical scaling approach quickly becomes astronomically costly. You hit diminishing returns very fast. A server that is twice as powerful is often 4 or 5 times the price.
And the financial pain isn't just the hardware, is it? It's the software licensing.
Oh, absolutely. Major RDB vendors often license their software based on CPU cores. So when you upgrade a single machine from, say, 32 cores to 64 cores, your license fee can double or triple instantly.
This creates a vendor lock-in scenario where your entire business becomes reliant on one vendor's proprietary, very expensive hardware path.
And what's more, maintaining a massive, vertically scaled system like that introduces a critical single point of failure. If that one giant monolithic server goes down, the entire transactional and analytical ecosystem just grinds to a halt.
Understanding that combination diminishing returns, crippling license fees, and single point of failure risk is really key to understanding why organizations embraced distributed, horizontally scaled technologies, big data technologies.
Which use many cheaper commodity machines instead of one expensive giant.
Right.
It's a fundamentally different approach to the problem of scale.
Okay, so despite those scaling limitations for big data, RDBs remain the core asset for structured, core business data. I mean, they aren't going anywhere.
Not at all.
So how do data professionals maximize performance and mitigate those analytical penalties within the existing RDB framework? Source 10 details several core techniques for speed.
These techniques are absolutely essential for managing the growth of data while still preserving the integrity of that normalized structure. The first, and maybe the most critical, is indexing.
Okay, so this is like creating an index at the back of a technical book.
That's a perfect analogy. Instead of the database having to scan every single row of a table, a full table scan, to find a specific customer, the index pre-sorts key columns.
So when you query by an indexed column, say customer last name,
the database engine uses that index structure to jump directly to the handful of data pages that contain the information. This vastly optimizes performance, especially for frequently queried lookups or filtering operations.
but there's a trade-off, isn't there? If indexing makes reading faster, does it make writing slower?
It does. Every time you insert, update, or delete a row, the database has to update the data and every single index associated with that table. So indexing is a very conscious choice.
You only index columns where the read penalty is high and the integrity benefit is worth that write overhead. Okay, the second technique for managing these large tables is partitioning. For those tables that grow exponentially, like global sales or log data partitioning, allows you to break them down into smaller, more manageable physical chunks.
And these chunks, or partitions, are based on some logical criteria. The most common is range partitioning, usually by date. So if an analyst runs a query only on the 2024 data, the database system only has to search the single physical partition holding 2024 records.
And it just ignores the partitions for 2020 through 2023.
Completely ignores them. This drastically speeds up time series analysis and minimizes the I/O load on the system.
And the third essential technique is tuning, specifically query optimization and tuning. This involves a rigorous analysis of slow-running SQL commands.
A skilled database administrator will look at what's called the execution plan of a slow query, and they'll rewrite or refine the SQL, sometimes changing the join order or how filters are applied, to guide the database engine toward the most efficient path.
So this is an iterative, high-level skill. It's often about advising the system on the best way to use the existing indexes and partitions.
It is. It's part art, part science.
The overarching goal of all these techniques, as the research clearly shows, is to improve analytical performance without sacrificing the integrity of the core normalized data structure. They're technical tricks, really, designed to mitigate the inherent performance penalties of high normalization.
Shifting focus now, let's talk about the human element and the non-negotiable requirements for trusted analysis. Security and governance, which is detailed in Source 11. In a regulated environment, knowledge is only valuable if it is secure and trustworthy.
And relational databases are built from the ground up with robust security tools. That's another huge advantage of their maturity.
It is. They provide essential security controls. First, you have user authentication, just verifying the user's identity. But more critically for analytics, you have role-based access control, RBAC.
Which ensures that users only see the specific tables, or even the specific rows of data they are authorized to access. This is vital for protecting sensitive customer PII, or proprietary financial figures.
Furthermore, RDBs include essential tracking mechanisms like audit trails. This logs who accessed which data, when they did it, and what actions they took. This entire suite of security features is non-negotiable for compliance with regulations like GDPR or HIPAA.
And for ensuring robust data protection in analytics. On the governance side, RDBs are crucial because they enforce consistent definitions across the organization. When everyone in finance, operations, and marketing is accessing the same relational database definition for active customer or gross revenue,
You eliminate those constant, costly internal arguments over whose numbers are correct.
that organizational consistency and single source of truth, it guarantees trusted results for analysis. If the data is defined, structured, and secured in one place with a clear lineage, the resulting analysis is just far more defensible and reliable for making multi-million-dollar strategic business decisions.
Effective governance really starts with structural integrity, and the RDB provides the foundation for that structure.
So after all that, what does this all mean for you, the learner? Navigating the complexity of the modern data landscape. Source 12 synthesizes the managerial implications perfectly. Despite all the buzz around new technologies for unstructured data, relational databases remain a core analytical asset.
They do. They're not generalists. They are highly focused specialists. They're best suited for data that is structured, that has stable schemas, and that ties into well-defined business processes.
So if your business runs on tightly controlled financial ledgers or inventory systems or regulated e-commerce transactions, the RDB is still the most reliable place to anchor your data truth. And this brings us to the strategic decision point. The research highlights that the modern data strategy really centers on integrating these tools intelligently. The key is knowing when to rely exclusively on relational databases for those stable, structured core processes.
And just as importantly, knowing when to complement them with big data technologies like NoSQL or distributed file systems to handle the challenges of volume, velocity, or variety that the RDB architecture simply wasn't designed for.
It's not a competition between the old and the new.
Not at all. It's an integrated ecosystem. The RDB provides the trusted source of truth and consistency for your structured data, and big data platforms provide the flexible, horizontally scaled processing power for everything else. Successful data organizations recognize the strengths and weaknesses of both.
That structural reality brings us right back to the central tension we've explored throughout this deep dive, the one between data integrity and query speed. Given that perfect normalization, as we detailed in our discussion of 3NF, enhances integrity but can dramatically slow down these large multi-table analytical queries, should organizations always strive for that pristine architectural perfection?
Or, given the sheer scale and the demands for speed in modern analysis, where insights delayed are decisions missed, is strategic denormalization, like that star schema model we saw in the OLAP design framework, an essential modern compromise for maximizing analytical velocity.
It really forces every data leader to ask, is guaranteed data consistency or time to insight the higher business priority in a given scenario?
And how much integrity are you willing to compromise for raw speed? That's a provocative thought for you to mull over as you build your own data strategy.
That's all the time we have for this deep dive into relational databases. Until next time, stay curious.
Welcome back to The Deep Dive, where we take a mountain of information. And today it's about the architecture of, well, the entire digital world. And we try to synthesize it into something clear, actionable, and, designed specifically for you.
Today, we are jumping headfirst into what we're calling the data tools landscape. And it's not just a list of software. It's this massive, constantly changing ecosystem of technologies that handle the entire analytical lifecycle.
From the very beginning to the very end.
From the second data is captured all the way to the moment you communicate an insight from it.
Okay, so let's get right into this. If you're involved in modern business at all, or R&D, or even just high-level strategy, you are swimming in this complexity every single day.
You can't avoid it.
Exactly. So our mission today is to give you a shortcut, a clear map of this ecosystem, explain why all this diversity is actually necessary, and I think this is the most important part, how your organization can maybe stop chasing the next shiny tool.
The shiny new object syndrome.
And start navigating this whole maze strategically, effectively.
And the foundational idea we have to get on the table right now, and it's one that pretty much every organization learns the hard way, is that no single tool can do it all.
It just can't.
The idea of a unified one-size-fits-all solution is, well, it's functionally impossible. The technical requirements just fundamentally conflict with each other.
So we're not looking for a super tool. We're actually managing a society of specialized tools. And that idea alone, I think, shifts the focus from just buying things to actually managing a complex system.
It's an architectural mindset.
Right. So let's start with part one and really dig into that. The analytical necessity of all this specialization. Why does this complicated landscape even have to exist?
Well, the necessity It really begins and ends with the analytical lifecycle itself. Data isn't static, it's on a journey.
A journey from a raw event to a final insight.
Precisely. And that journey goes through 5 really distinct stages. And the goal of the tool you use in stage 1 is completely different from, and frankly, often at odds with, the goal of the tool you'd use in stage 5.
Okay, let's nail those 5 stages down because it feels like they're the foundation for everything else we're going to talk about today.
Absolutely. So first, you have to, 1, capture data. There's a creation of the record.
Yeah.
Then you have to, 2, store data.
Keep it somewhere safe.
Persist it reliably.
Yeah.
Then, the messy part. 3, process data. Transforming it into something usable.
The cleanup job.
Then the core of it, really. 4, analyze data. This is where your modeling, your pattern discovery, all that happens. And finally, 5, communicate insights.
Making sure all that work actually drives an action.
Exactly.
So that structural split right there means the tools have to be different. I mean, if the goal of capturing data is all about high-speed transactional integrity, that tool is never going to be great at, say, running a 5-year regression model.
Just not built for it. The whole imperative for specialization comes from the fact that analytical tasks vary so widely across four key dimensions: scale, speed, data structure, and complexity.
And those 4 are what dictate the tool choice.
They have to be. Let's look at the tension there. If I'm running, say, a stock trading platform, my tool has to handle immense scale. We're talking millions of trades a second and incredible speed.
Low latency is everything.
Everything. But the complexity of any single one of those transactions is actually pretty low. It's buy, sell, time, price. That's it.
Now contrast that with something like, I don't know, climate modeling or training a large language model.
Right. A totally different world.
Yeah.
You might have massive scale of data, sure, but the speed you need is often measured in hours or even days for a single training run. The main concern there shifts completely to the complexity of the math and the highly variable data structure.
You're not just dealing with neat rows and columns.
No, you're processing text, images, telemetry data, all at the same time.
So if a tool is built to maximize the reliability and speed for those simple transactions, what we call OLTP, right? Online transaction processing, it's probably using a row-based architecture.
Yes, heavily indexed for super fast lookups. But if you ask that same OLTP system to do an analytical query like, show me the average purchase price for all 10 million users over the last 3 years.
It's going to choke.
It's going to crawl. It has to read every single row and then throw away most of the data in it just to get to the 2 columns it needs. It bogs down, it might even lock out real users, and it takes forever. It is, by its very design, the wrong tool for that job.
And that really gets at this idea of divergent optimization goals. It's the classic engineering trade-off. You optimize for one thing, but it's always at the expense of something else.
Always. We see 3 main conflicting goals that drive how tools are designed. First, there's operational efficiency.
The day-to-day stuff?
Right. Tools built for instant, accurate, small-scale interactions that just keep the business running. Your point-of-sale system is a perfect example.
Okay, what's the second one?
Analytical performance. These are the tools built for those complex, massive parallel queries across huge historical data sets. This is your specialized data warehouse.
And then the third one, which you hear about a lot from data science teams, is all about flexibility.
Yes. Flexibility is king for experimentation. A data scientist needs to pull in new, maybe really messy data, prototype a model super quickly, use their favorite programming environment like Python or R.
And that means they have to be able to ignore rigid structures, at least at first.
They have to. And that's the technical compromise. If you prioritize flexibility, you are almost certainly sacrificing some operational efficiency and probably some of the governance you need for, high-stakes production-level analytics.
It's like asking for a vehicle that can haul 5 tons of cargo, win a Formula One race, and also operate as a submarine.
You'd end up with something that's just terrible at all 3 jobs. It's the same principle.
So the key takeaway here for you, for the listener, is that success in this world is all about matching the tool to the job.
You absolutely have to choose tools based on the specific problem requirements, the scale, speed, structure, complexity of that task, and not just because some vendor has a huge marketing budget or it's trending on social media.
Right. It's a strategic decision. You're assembling a specialized fleet. You're not looking for one giant aircraft carrier to do everything. Okay, now that we know why the tools have to specialize, let's map out what those specializations actually look like.
Understanding this map is, I think, the most critical step toward managing data strategically. And you'll see vendors try to blur these lines all the time. But the fundamental technical priorities of these 5 categories, they stay distinct.
It's like you said, you wouldn't use a wrench to hammer a nail, right? Even if the wrench company started marketing a hammering mode.
Exactly. And crucially, these systems are often run by different teams. They have different security rules, different uptime needs.
The priorities can be worlds apart.
Totally.
Okay, category 1. Let's start at the beginning. Data capture and source systems, the origin. What defines this category?
These are your core operational systems.
Yeah.
They're built for speed and reliability, and they're optimized for transactions, not for analytics.
So give me some examples.
Oh, it's a huge list. Transaction systems for purchases or reservations, CRM systems logging every single customer interaction,
Yeah.
ERP systems, and then just the fire hose of logs coming from your website or your mobile app.
And their absolute core focus is on transactional integrity. The big technical concern is what they call ACD compliance.
Right. Atomicity, consistency, isolation, and durability. A customer buys something, that transaction has to be recorded once, it has to be accurate, it has to be instant, and it has to be permanent.
Reliability and accuracy are everything.
Paramount. And here's the crucial distinction that I think a lot of technical managers even miss. Running big analytical queries directly on these systems is actively bad for the business.
You're actually hurting things.
You are. You risk locking the database, slowing down real-time operations for actual customers, and you can incur massive operational costs. These systems are licensed and provisioned for thousands of tiny fast reads and writes, not for one giant heavy analytical job.
So trying to run a detailed customer segmentation report or a 3-year forecast directly on your live CRM system is a terrible idea.
It is a recipe for disaster, and that's why you have specialized tools for getting the data out, things like change data capture or CDC. They're designed to basically read the stream of changes happening in the operational database without hurting its performance.
So you can move that data to its proper analytical home.
You have to treat these source systems very gently.
Okay, so once it's captured, the data needs a home. And that home has to be optimized for deep, fast queries. That's category 2, data storage systems.
This is the foundation. The technology used to persist and hold the data, and hopefully it's formatted in a way that's ready for analytical retrieval.
So we move from OLTP, the transactional focus, to OLAP, the analytical focus. What are the main types of architecture we see here? Because they're technically quite different.
We can pretty much group them into 3 buckets. First, you still have your traditional relational databases. They're great for really structured data where integrity is key, but they just can't handle massive analytical scale. They fall over.
And then you have the workhorse of enterprise analytics for the last couple of decades, the data warehouse.
Right. The modern data warehouse is built specifically for analytical queries on huge volumes of historical, mostly structured data.
And the key technical difference is that columnar storage thing you mentioned earlier.
Yes, columnar storage. Instead of storing data row by row like a spreadsheet, it stores it column by column. So when your query only needs 2 columns out of 50, like customer ID and sales amount, the system only has to read 2/50ths of the data.
Which makes the query dramatically faster for analysts.
Dramatically. And these systems work on a principle called schema on write. The data has to be cleaned up and structured before it gets loaded into the warehouse.
And then there's a third bucket, the data lake, which really took off with the rise of unstructured data and machine learning.
Exactly.
Yeah.
These platforms, often built on things like Amazon S3 or Google Cloud Storage, they're designed to handle everything. Unstructured data, semi-structured, massive raw files. They work on the opposite principle, schema on read.
Dump it all in first, worry about it later.
You got it. You dump the raw data in, and then you figure out how to structure it and clean it as you need it for a specific project. This gives you incredible flexibility and scale, but the data quality is, inherently lower, and it usually requires a lot more processing down the line.
And the strategic impact of that choice is huge. I mean, if you're doing financial reporting, you probably need the structure and integrity of a data warehouse.
Absolutely. But if you're building experimental AI models on raw text logs and sensor data, you need the flexibility and the lower cost of a data lake architecture.
So the choice of storage directly hits your scalability, your performance, how fast your queries run, and of course your cost.
Crucially, cost. Storing data in a big data lake is usually way cheaper per gigabyte than in a high-performance data warehouse. But The cost to actually process that raw data to make it useful can sometimes be much higher than the storage savings. It's a really complex balancing act.
Okay, so we've captured the raw data in Category 1, we've moved it to its specialized home in Category 2, but we both know that data is almost never clean or ready for modeling at that point.
Never.
And this is where the bridge comes in, Category 3, data integration and preparation tools.
This is often the most labor-intensive, the most resource-heavy, and let's be honest, the least glamorous part of the whole process. But it is arguably the most important for building trust in your data.
This is where you earn your stripes.
Absolutely. These tools are all about moving, cleaning, harmonizing, and transforming data across all your different systems.
So let's get into the technical terms here. We hear ETL and ELT thrown around all the time. What's the difference?
So the old way was ETL, extract, transform, load. The transformation, the cleaning, and structuring happened before the data was loaded into the data warehouse.
Usually on its own dedicated server.
Right. The modern approach, which is really enabled by the power of the cloud, is ELT, extract, load, transform. You load the raw data into your powerful, scalable cloud data warehouse first, and then you use the warehouse's own massive compute power to do the transformation right there.
Which is way more efficient at cloud scale.
Much more efficient.
So what are the specific jobs these tools are doing during that transformation phase?
Well, they're handling core stuff like data cleaning, fixing typos, standardizing date formats, filling in missing values. They do data integration, which is a huge one.
Like trying to combine customer data from your CRM and your e-commerce site?
Exactly. And making sure that John Smith in one system is the same person as Jay Smith in another. That can require some pretty sophisticated algorithms.
And then there's the really crucial work for the analytics teams, feature construction. You mentioned this as a more advanced concept.
Feature construction is where the real magic happens for machine learning. It's where you manipulate the raw data to create new variables, new features that are specifically designed to be predictive.
So it's not just the raw data anymore.
No, it's the difference between having a log of every transaction and having a metric called customers' predicted lifetime value, or volatility of sales in the last 90 days.
And those aren't just simple calculations. They require some pretty complex logic and aggregations.
Exactly. You're turning these raw ingredients, clicks, sales, timestamps, into sophisticated model-ready features that actually have predictive power. Without good integration tools, that whole process is manual, it's slow, and it's full of errors. These tools are the essential bridge between messy operational data and clean analytical models.
The scaffolding that holds the whole thing up.
That's a great way to put it.
Okay, so if Category 3 hands off these clean, structured features, then Category 4 is the engine room. This is where the heavy lifting analysis actually happens. Discovery becomes the main goal.
Yes, the goal completely flips here. It's no longer about reliability and consistency. It's all about flexibility, analytical power, and the speed of iteration. This is where you ask questions, you test hypotheses, you train models.
What are the main activities that define this category?
Well, you have foundational things like deep statistical analysis, so running regressions, A/B testing, that kind of thing. You have data mining, which is using algorithms to find hidden patterns you didn't even know to look for. And then the big growth area, machine learning and predictive modeling.
Building models to forecast the future.
That's the goal.
And the tools here really reflect that need for flexibility. We're talking about statistical programming environments, right? Your custom code in Python, R, or Julia, it's inherently experimental.
Exactly. And you also have specialized platforms designed for large-scale training of things like deep learning models, which often need dedicated hardware like GPUs. The whole point here is rapid prototyping. An analyst might try 20 different types of models or 20 different sets of features just to see what works best.
And they need tools that can handle those rapid, resource-intensive runs without a lot of rigid rules.
Absolutely. So while the data warehouse in Category 2 is demanding consistency, the engine room in Category 4 demands the ability to change, adapt, and just scrap things that don't work and do it quickly. It's a dynamic environment built for discovery.
Which is a stark contrast to the earlier categories where reliability was the absolute king.
Worlds apart.
So that brings us to the final stage, Category 5, visualization and reporting tools, the communicator.
We've reached the final, and you could argue the most visible, and often the most political stage of the whole chain.
Because all the sophisticated work in the first four categories
Is completely worthless if the insights you find can't be understood and acted upon by the business.
These tools are essentially the user interface for the entire analytics process. They translate all that complexity into something a non-technical audience can actually consume.
Right. Their outputs are the dashboards, the reports, the interactive charts we see every single day. They are the final bridge between the data expert and the business decision maker.
And our sources really highlighted this as the place where so much great analytical work just goes to die. The risk of getting the visualization wrong is huge.
It is absolutely critical. A poor visualization, or even just failing to communicate the uncertainty in your model, can completely negate the most accurate analysis. Imagine an executive needs to see sales performance, and the dashboard uses the wrong scale, or misleading chart type, like a 3D bar chart that distorts everything.
Right. You could have spent $5 million building the world's most accurate forecast model. But if the chart you use to present that forecast makes it look like there's a crisis when there isn't one,
Or it hides a critical trend.
the decision made will be flawed. The money was wasted.
Exactly. Or, and this is a big one, failing to communicate the model's limitations. A good visualization tool has to do more than just show pretty numbers. It has to convey context and certainty and relevance.
Which requires a real commitment to data literacy across the whole organization.
It does. Decision makers need to understand what a confidence interval actually means and what the limitations of the underlying data are. That communication layer has to be just as robust and just as intellectually honest as the analytical engine itself.
So we have these 5 specialized categories. Each one is essential, but they're all optimized for different, often conflicting goals. And that specialization, of course, leads to vendor competition and tool overlap.
Oh, absolutely. The boundaries are anything but rigid. Every vendor wants to expand their footprint across that workflow to, increase customer stickiness and grab more market share.
Which makes perfect business sense, but it really complicates the architecture for the user. Can you give us some concrete examples of where these lines get blurry?
For sure. Think about modern data warehouse platforms. They've evolved way beyond just being Category 2 storage. They now have really powerful serverless compute for transformations, that's Category 3, and they often integrate Python or R environments for running machine learning models, which is Category 4.
So that's storage, plus preparation, plus analysis, all under one roof.
Right. And you see it going the other way too. Visualization platforms, Category 5, they're now adding advanced analysis capabilities. You can do complex calculations right in the dashboard, blurring the line with Category 4.
So any given task might be technically possible in 3 different tools in your stack, which sounds like a strategic nightmare.
It can be, but the driving factor has to always come back to integration. Integration is what brings order to the chaos of specialization.
And when the tools work together seamlessly, what's the real tangible benefit?
You cut down on data duplication, which is a massive source of cost. Why pay to store the same petabyte of data in 3 different places? You also maintain consistency, which prevents that awful scenario where the finance department's report and the sales department's report show different revenue numbers.
And that just accelerates the whole process.
It enables a smooth workflow. It shortens the time from raw data to an actionable insight.
And the need for that integration just got more intense with the move away from the old traditional data environments?
Oh, absolutely.
Yeah.
Historically, these environments were really centralized and totally controlled by IT.
Right.
Getting access to data was slow, it was bureaucratic.
The long waterfall development cycle?
Exactly. But today, the whole environment feels completely different.
It's decentralized, it's agile, it's immediate.
The modern environment is fundamentally distributed, it's cloud-based, and it's heavily oriented towards self-service. You have business users, analysts, data scientists, all empowered to access data, manipulate it, even build their own pipelines with these powerful low-code tools.
And that shift is always praised for the agility it creates. You get faster time to insight. You're less dependent on a central IT bottleneck.
And that agility is a huge win.
Yeah.
But it comes with a proportional increase in complexity around governance.
I was just about to ask about that.
When you have dozens of teams setting up their own integration tools, defining their own metrics, building their own pipelines, all running on distributed cloud resources, how do you ensure standards? How do you maintain security and consistency? It becomes exponentially harder than when everything lived in one centrally controlled warehouse.
So the core trade-off of this modern approach is clear. You're trading centralized control for distributed agility.
And if you're going to open the floodgates for self-service, you had better have a really good plan for how you're going to manage that flow.
Which brings us to the cloud. I mean, the cloud isn't just a place to run things anymore. It's the architectural unifier for this entire distributed landscape.
It's the only reason this model is even viable. It completely changed the economics of compute and storage.
How exactly was the cloud so revolutionary in bringing these tool categories together?
Historically, if you bought a database, you bought the storage and the compute hardware bundled together in a physical box. The cloud introduced this radical idea of decoupling storage and compute.
Meaning you can store a petabyte of data really cheaply in something like object storage.
And then only spin up and pay for massive analytical compute power for the 30 minutes you need it to run your big complex model.
And that's the definition of elastic scaling, right? The ability to handle peak loads without having to buy and maintain expensive hardware that sits idle most of the time.
Exactly. The benefits are just so tangible. Rapid deployment, you can spin up a new environment in minutes. True elastic scaling, handling that massive end-of-quarter reporting spike automatically. And crucially, enhanced collaboration, because everyone, no matter where they are, is working off the same centralized storage layer.
And for smaller organizations, this just blew the doors open. You don't need $1 million server farm anymore. You can access world-class analytical tools with a credit card and pay-as-you-go pricing.
It democratized analytics. It really did. It lowered the infrastructure barriers that used to reserve this kind of work for Fortune 500 companies.
But even with the cloud unifying things, the ultimate value of all this still depends on the data flowing smoothly between all these components. If the data gets stuck or corrupted, jumping from category 2 to 3 to 4, the whole thing just breaks.
And this is the #1 friction point for data teams today. If everything is distributed and specialized, how do we make sure the handoffs are clean?
Poor interoperability is the challenge.
It's the core challenge. When tools can't talk to each other cleanly, you get massive friction. First, you get manual workarounds. Analysts spending days exporting CSV files from one system, cleaning them up by hand in Excel, and then importing them into another.
Which are just factories for errors.
And time sinks. And that manual, brittle process leads directly to inconsistent results, which is the fastest way I know to destroy an organization's trust in its data.
Absolutely. If the marketing dashboard shows 10,000 leads, but the finance report shows 9,500, management spends the next week just arguing about which number is the truth, instead of making a decision.
And that, of course, results in delayed insights, which means you're missing market opportunities.
Okay, but wait. If integration is so obviously critical, why do we still see vendors building proprietary connectors and making it intentionally hard to integrate, instead of just universally supporting open standards?
That is an excellent question, and it really gets at the market dynamics. Vendors often prioritize their own proprietary solutions to create customer lock-in. If their tool is the easiest way to connect to their own ecosystem, you're much less likely to switch to a competitor.
But the market is pushing back.
The market demand for seamlessness is huge. And so the only long-term solution is for organizations to demand standards.
So, using standard interfaces and robust APIs is the only way to guarantee efficiency in the long run.
Yes. If every tool speaks the same language when it exchanges data, whether that's through standardized SQL or common data formats like Parquet or reliable APIs, the friction just drops dramatically. The whole value chain flows smoothly. But that requires a strategic investment in technical governance.
Which brings us to our final section. This all boils down to strategic management. If we have to accept this complexity, how do organizations make smart, contextual choices when they're selecting tools, instead of just piling up technical debt and chasing new software?
The first principle for any leader is to understand that selecting tools is not a search for perfection. It is a series of necessary trade-offs. There's no such thing as a universally best tool. The best fit is entirely driven by your purpose, by your organizational context, and by your specific business need.
Okay, so let's break down the 4 key tension points that every decision maker has to actively manage. The first one feels like the most fundamental: simplicity versus analytical power.
This is the constant push and pull between ease of use versus analytical power. So imagine a small business that just needs simple KPI dashboards, sales, inventory, that kind of thing. They would benefit enormously from a really user-friendly drag-and-drop BI tool.
Everyone in the company can use it. It enables self-service.
But if that same company then needs to build a sophisticated custom forecasting model based on 5 years of data and external economic indicators, that easy-to-use tool just isn't going to cut it.
It's a wall.
It hits a wall. They would need a powerful, complex programming environment that only a few specialized data scientists can operate. So you have to balance that accessibility for the many against the raw capability needed for the few to get those breakthrough insights. You can't maximize both.
The second tension goes right back to the distributed nature of the modern landscape. Flexibility versus governance.
This is a constant operational battle. Flexibility lets your users experiment quickly, adapt to new data sources, try new tools on the fly. It's great for innovation. But if you leave it completely unchecked, that flexibility completely undermines governance. The standardization, the security, the quality control you need for high-stakes reporting, for regulatory compliance, and just for general trust in the data.
So a data scientist might need the flexibility to pull in some random file and use a niche open source library, but the finance department needs a rigid, locked-down workflow to produce auditable quarterly reports.
And you need a way to manage both of those realities. You have to define clear boundaries. When is experimentation okay, and when does a workflow need to move into a standardized, governed, production-ready pipeline? Striking that balance really defines your organization's data culture.
Okay, the third trade-off is often the most immediate one, cost versus scalability.
This one dictates your capital investment. Do you go with the lowest cost solution today, maybe using cheaper hardware or a basic open source tool that might just fall over when your data volume grows tenfold next year?
That technical debt will come back to bite you.
It will cost you time and money later. The alternative is to invest heavily now in a highly scalable, decoupled cloud architecture. It might feel expensive and underutilized at first, but it guarantees that you can meet future growth without a painful, expensive replatforming project down the road.
Managers have to be looking 3 years out, not just 3 months out.
They do. And finally, there's the choice that really impacts your staffing and support model. Open source versus proprietary solutions.
What's the trade-off there?
Open source gives you incredible customization, a huge community for support, and often lower upfront license costs. But the trade-off is maintenance. You are responsible for integrating it, patching it, stabilizing it. That requires a lot of in-house expertise.
Expensive, highly specialized engineers.
Exactly. Proprietary solutions, on the other hand, give you guaranteed vendor support, stability, and a clear product roadmap. But that comes with high licensing fees, vendor lock-in, and less flexibility.
So the critical insight here for managers is that these aren't flaws in the tools, they are necessary strategic tensions. The goal isn't to eliminate the pension, it's to manage it intelligently based on what the business is trying to achieve.
And given that inevitable complexity, organizational maturity isn't a luxury. It is the absolute prerequisite for success. If you have a diverse set of tools without any structure, you just get chaos and wasted money.
What are the 3 non-negotiable requirements for an organization to use a diverse tool set successfully?
Okay, first you need skilled analysts. People who are technically mature enough to know when to use the flexibility of a data lake versus the rigor of a data warehouse. Second, you need clear governance rules. And that's not just who has access, it's technical governance.
Like a centralized metadata catalog defining what every metric actually means.
Exactly. So you don't have 5 dashboards with 5 different definitions of sales. And you need consistent access control applied across all your distributed tools. And the third requirement is defined analytical workflows.
Mapping out how data actually gets from capture to insight.
Right. Preventing people from creating these ad hoc, brittle, unreliable pipelines every time they need a new analysis.
Yeah.
You have to standardize your integration tools.
Because the danger of tool sprawl is so acute, what does that actually cost an organization?
Sprawl without a coherent strategy leads to exponentially higher costs. You're paying for redundant storage, redundant compute, redundant software licenses for tools to do the same thing. And it creates this devastating institutional confusion.
The paralysis of analysis.
We've seen it. Organizations where teams spend an entire week just arguing over which dashboard is the truth because 5 different data pipelines had slightly different cleaning rules, no decisions get made.
So it seems we've established that success depends far more on how you use the tools, the governance, the strategy, the people, than just which specific tools you choose. The technology is secondary to the operating model.
Which brings us to leadership. Managers have to get out of the technical weeds. They shouldn't be choosing the specific version of a database engine. They should be defining the business needs that dictate what type of engine is required.
So what are the 3 strategic actions managers should prioritize to master this landscape?
First, they must align tool choices directly with defined business objectives. If your goal is regulatory compliance, your stack has to prioritize governance and auditability over speed. Second, leadership has to actively avoid unnecessary complexity.
Be the gatekeeper against that shiny new object syndrome.
Exactly. Complexity is maintenance debt. Every time a new tool is proposed, managers have to ask, is this truly necessary versus the cost of integrating it and maintaining it forever? And third, they have to strongly support integration efforts and standardization.
That means allocating budget and engineering time to it?
Real budget. For building and maintaining those standard APIs, those common data formats, that metadata catalog we talked about, it's the essential scaffolding that allows specialization to actually work.
So standardization is really an investment in your future agility.
It is. It ensures that when you do need to swap out a specialized tool 5 years from now, it's not a complete re-architecture of your entire system, because the underlying interfaces are clean and standard. And this all leads to the final strategic principle for leadership.
Which is?
Technology should enable better decision-making. It should never be allowed to dominate the organization's focus or its resources. When your data teams are spending more time managing licenses and debugging connectors than they are delivering insights, you've lost the balance.
We have covered a huge amount of ground here, mapping out the necessity of specialization, the 5 crucial categories of the data workflow, and the strategic trade-offs needed to manage it all.
Yeah, we've seen that the modern landscape is this decentralized, cloud-based ecosystem that's all designed for agility. The tools are incredibly powerful, but the real bottleneck is integrating them, governing them, and making sure the organization itself is mature enough to handle them.
And just to reinforce that most critical idea, success in analytics depends on a thoughtful operating strategy, your governance, your workflows, your people, far more than it depends on just picking the newest or fastest piece of software.
Absolutely. But let's end with a final thought for you to carry forward as you think about the architecture in your own organization. We've established that the modern environment favors self-service and distribution, which naturally makes governance harder. So if that old ideal of centralized, strict control from the 1990s data warehouse is no longer feasible in this sprawling ecosystem, what's the alternative?
A very good question.
Is true, comprehensive data governance even an achievable goal anymore? Or is the new reality a kind of strategic controlled chaos, one that's managed by clear intent, strong standardization layers, and robust monitoring, where you accept a certain amount of localized complexity as the price of agility?
Food for thought. Thank you for joining us for this deep dive into architecting the modern data ecosystem. We'll see you next time.
Welcome back to the Deep Dive, where we take complex source material, strip away the noise, and extract the genuinely insightful nuggets you need to become instantly well-informed.
Today, we are opening the hood on the true engine room of any modern data-driven organization, the analytical lifecycle.
That sounds pretty technical, but here's the mission for you.
Yeah.
When you hear the term data analyst, you might picture someone staring at, I don't know, a single massive spreadsheet. The reality, according to the sources we dove into, is far more complex. We're not just looking at what analysts do, but the entire comprehensive toolkit, the interlocking phases and specialized tools they rely on step by step.
Right.
How they turn a massive pool of raw, messy data into an actual, reliable, actionable insight. Something that actually changes business strategy.
And it is a life cycle, not just a straight line. That's a key distinction. It's defined by a series of complementary stages: data access, preparation, exploration, modeling, validation, and finally, communication. And the tools chosen for each of these stages critically affect 4 things: speed, accuracy, reproducibility, and, the ultimate quality, the knowledge that senior leaders are depending on.
So if you understand the flow, you understand where all the complexity and all the value really lives.
Exactly.
And that last point, the foundation, that's really where we have to start. The core concept, immediately, is that data analysts rely on a set of complementary tools. It's not a single all-in-one platform.
Yeah.
You wouldn't expect a carpenter to build a custom kitchen using only a hammer, right? They need measuring tapes, saws, squares, levels, clamps, a whole toolbox.
It's the difference between using a single blunt instrument and having a master craftsman's toolbox. The scope of modern data analysis is just so vast. It covers everything from establishing a secure database connection to making an accurate 6-month forecast.
And no single software can handle every phase of that optimally.
No, not efficiently anyway. And we're here to unpack that necessary complexity for you so you know exactly which specialized tool belongs in which phase of the analysis.
Okay, let's unpack this core idea first before we even touch a single SQL query. We need to define the relationship between the analyst and their toolkit. So we've established the tools support the full analytics lifecycle. They're the mechanisms that carry the data from raw source to final insight. But what did they not do?
This is the critical caveat, and it's
Yeah.
maybe the most important realization for anyone looking to hire an analyst or even become one. The tools, they absolutely do not replace analytical thinking.
Right.
They are spectacular force multipliers, They can perform billions of computations in seconds, but they are entirely useless without the human intelligence that's guiding them. The technology is passive, the mind has to be active.
I see this tension all the time. People assume that if they just buy the most expensive machine learning platform, the insights will, I don't know, just pop out on their own.
Yeah, that's a common misconception.
So if the tools are handling the brute force computation, what is that irreplaceable non-tool dependent value that the human analyst brings? What are the skills that no algorithm can replace?
Our sources highlight 3 absolutely essential skills. And the first one is just non-negotiable. The analyst must deeply understand the business problem.
The context.
The context, exactly. Data exists because of real-world activities. A sale, a website click, a manufacturing fault. If the analyst doesn't understand the operational context, the competitive landscape, the internal cost structures, the why that data was even generated, they're just generating mathematically correct solutions to irrelevant questions.
Solving the wrong problem efficiently is probably the most expensive mistake an organization can make.
Absolutely.
You might perfectly optimize the cost of running a delivery fleet, for example, but if the real business problem is losing market share to competitors with faster delivery, you've just spent millions improving the wrong metric.
Precisely. So that contextual understanding, that's skill number 1. Skill number 2 is choosing the appropriate methods. Let's say you're trying to understand customer loyalty. Should you use a simple time series model to forecast sales next month? Or should you maybe employ a complex clustering algorithm to segment your customers first and then build a separate forecast for each segment? The choice matters.
But wait, what about, machine learning platforms are getting so good at automatically selecting and running dozens of algorithms at once. They call it auto ML, right?
They do.
So how long until choosing appropriate methods becomes obsolete and the analyst only needs to understand the business?
That's a great challenge. And it's true, the tool can run the algorithms, but it cannot select the strategically appropriate method for the specific business question and data constraints.
What do you mean by strategically appropriate?
Well, an analyst might reject the statistically best model, say a really complex neural network, because the business needs a simple, explainable, linear model they can actually audit and defend in a board meeting. The tool is neutral. The human has to be strategic and pragmatic. The analyst is constantly weighing performance against interpretability, which is, a business constraint, not a technical one.
That makes perfect sense. The human analyst understands the trade-offs, okay? And the third essential skill, the one that bridges the gap between the technical output and the commercial outcome.
It's interpreting the results correctly. A model might output a statistical metric, maybe a p-value below 0.05 or a high R-squared score, but those are just intermediate numbers.
Right.
The skilled analyst takes that output and interprets it back into the language of the business. They don't say the coefficient for variable X is 0.15 with high statistical significance.
No, the CEO's eyes would just glaze over.
Exactly. They say, this analysis suggests that for every $100 we spend on Facebook advertising, we can expect about a 15% increase in lead generation from the 35 to 45 age group, assuming all other factors remain constant.
So that interpretation requires domain expertise and critical thinking to turn a statistical probability into business relevance and, ultimately, a suggested action.
Absolutely. I like to use an analogy for something like the p-value. Think of a legal trial. The null hypothesis, the default assumption, which is usually nothing interesting is happening here, that's the defendant, presumed innocent.
Okay.
The p-value is the strength of the evidence against that defendant. So if the p-value is very low, say under 5%, it's like a jury saying the evidence is strong enough that we have to reject the default assumption of innocence.
Got it.
But the analyst's job is then to translate why that rejection matters financially. And that is the difference between mere computation and true value-generating insight.
So the core takeaway here is that the skilled analyst must adapt their tools to the problems. The complexity of the business question dictates the necessary tool set, not the other way around.
You've got it.
If we keep this human-centric framework in mind, then the purpose of each tool in the lifecycle becomes much, much clearer. Okay, let's get into the mechanics. We start the life cycle at the very beginning, just getting the data. This is phase one, the essential groundwork, and it starts with data access and retrieval tools.
Right.
These tools perform the foundational task of extracting data from secure repositories.
And this step is absolutely fundamental, and often it's the most secure and controlled phase of the whole process.
Yeah.
We're talking about extracting data from both operational systems, like the databases that run daily transactions, often called OLTP databases,
Okay, up for it.
and from analytical systems, like centralized data warehouses or data lakes. Those are OLAP systems. You need specialized tools because these systems are designed for completely different purposes. One is for the speed of daily operations, the other is for complex analytical querying.
And what are the specific foundational capabilities that these access tools absolutely have to provide?
Well, the primary foundational step is querying databases. You need a language, which is typically SQL, and a dedicated tool in SQL client or something similar to ask the database, hey, give me the specific slice of information for the last 3 months.
But you rarely get the full picture from just one table, I imagine.
Almost never. And that brings us to the second key capability, joining data from multiple, often disparate sources. That's where the real-world complexity really kicks in.
This is where it gets messy.
This is where it gets very messy. It's the complexity of real-world analysis. You might have your core transaction data in an Oracle system, but your customer satisfaction scores are stored in a cloud-based application, and your web activity logs are in a totally different format, maybe a NoSQL database.
So it's all over the place.
Right. And the access tools have to be robust enough to handle the complexity of linking those disparate records. It's not just about matching on a customer ID. You have to ensure that the data types align, that the timestamps are consistent, and that the joining process doesn't accidentally introduce duplicates or lose information.
Without that robust joining capability, the analyst is just trapped, right? Forced to analyze incomplete, siloed views of the business.
Exactly. And the third critical capability mentioned is filtering and aggregating records.
Now, why is it so important to do this right at the data access stage? Why not just pull everything and figure it out later?
Efficiency and scale. Pure and simple. Filtering lets the analyst focus the query, so maybe they only pull data related to high-value customers or events that happen between specific dates.
Okay.
But aggregation is even more critical for performance. Instead of pulling, say, billions of individual transaction records across the network, you use the database's own processing power to summarize that data.
Ah, so you do the math on their machine, not yours.
Precisely. You aggregate the individual transactions into daily or weekly sales totals before it ever leaves the source system.
So the importance here isn't just about moving data, it's a massive resource optimization. By filtering and aggregating early, you dramatically reduce pre-processing time and network load. You avoid the mistake of moving 10 gigabytes of data when you only actually needed 50 megabytes for the analysis.
You got it. You're performing the first layer of triage right at the source. If you efficiently filter and summarize what you need at the store, you save a ton of time in memory cleaning and prepping all the irrelevant data once you get back to your own analytical environment. And that takes us directly to the next part. Data preparation and cleaning tools. If data access is gathering the ingredients from all the different vendors, data preparation is the painful but crucial process of washing, cleaning, peeling, chopping, and organizing everything before you can even think about cooking.
And this is where the sources tell us analysts spend most of their time. This is the real bottleneck.
It is the single largest bottleneck. The source material really emphasizes this crucial detail. Data preparation often consumes the largest share of an analyst's effort. We're talking 60 to 80% of the entire project time.
That's incredible. Why so much?
Because real-world data is inherently messy. It's just dirty, inconsistent, and riddled with gaps.
Okay, so what specific tasks must these dedicated preparation tools support to tackle this overwhelming bottleneck?
Well, the first pervasive issue is handling missing values. Data gaps are just inevitable. A sensor failed, a user skipped a form field, a payment system timed out. It happens.
Right.
But when we talk about missing values, analysts have to identify why they're missing. Are they missing completely at random, or MCR, where the absence is unrelated to the data itself? Or is it missing at random, MAR, where the missingness relates to observed data? For example, males might be less likely to report their income.
That detail about why the data is missing sounds really critical. It means managing incompleteness isn't just about deleting blank cells. It's a strategic decision that affects the entire analysis.
It absolutely is. And preparation tools provide different methods for managing this. It's a process called imputation. You could fill the missing cell with the mean or median of the existing values. That's simple imputation. Or you could use a sophisticated model to predict what the missing value should be, which is model-based imputation.
And if you just delete the records?
Well, if an analyst simply deletes records with missing values, they might inadvertently bias the entire sample, especially if the data isn't missing completely at random. The prep tool has to make these strategic choices manageable.
Okay, so that's missing values. What's the second core task in preparation?
Correcting inconsistencies, ensuring data uniformity. This is the tedium that saves the subsequent model from catastrophe.
Give me an example.
Okay, so if one system tracks dates as month, day, year, and another uses year, month, day, the tool has to harmonize them. If a customer is categorized as student in one database and full-time student in another, the tool has to enforce a single consistent categorization.
Because if you fail to do that, the modeling tool might read those as two totally separate categories, which would skew the results dramatically.
Exactly. And then there's the third task, which you mentioned earlier. It's much more creative than just creating new variables, which is known as feature engineering.
This sounds like where the analyst really gets to shine.
This is where the skilled analyst proves their value in the preparation phase. Feature engineering means creating highly powerful, novel predictors that were not explicitly collected in the first place. For instance, you might have a table with purchase dates.
Right.
Instead of using the date itself, the analyst uses the preparation tool to calculate 3 new derived features. Recency, how many days since the last purchase? Frequency, the total number of purchases, and monetary value, the total money spent.
RFM. Recency, frequency, monetary value. Those 3 derived features are way more predictive of future customer loyalty than just the raw transaction date. You're turning time into behavioral metrics.
Exactly. And this requires domain knowledge and creativity. The preparation tool enables the analyst to perform these transformations quickly and reliably across millions of records. Another example would be changing raw street addresses into a new feature like distance to the nearest store. You're adding depth and dimensionality that a simple model could never find on its own.
So to synthesize this massive step, why does all this cleaning, correcting, and engineering matter so much at the end of the day?
Because the true cost of bad data is not the cleanup time. It's the flawed, costly decisions that are made months later based on an unreliable analysis. Well-prepared data is absolutely critical for reliable modeling outcomes.
Garbage in, garbage out.
It's not just a cliche in data analysis, it's a law. It guarantees unreliable, biased, or just plain false conclusions if you ignore it. Preparation guarantees the integrity of everything that comes after.
All right, so we've accessed the data, we've cleaned it meticulously, we've even engineered some smart new variables. We now know what we have. Now we move into phase 2, finding the narrative. And this starts with exploratory data analysis, or EA-Day. This is the stage where the analyst stops prepping the data and starts genuinely getting to know it. It feels like detective work before you commit to a theory.
That's a great way to put it. The primary purpose of EDA is to understand the data's structure, identify any lingering anomalies that you might have missed, and detect patterns and relationships before you start any formal resource-intensive modeling.
You don't try to solve a mystery without interviewing witnesses and gathering clues.
Exactly.
So what typical activities do EDA tools enable that facilitate this discovery process?
First, just generating summary statistics. This is foundational. Calculating means medians, standard deviations, ranges for all your key variables. An analyst can quickly see if the average order value is $5 or $5,000. These numbers give you that first quantitative sense of the data's central tendency and spread.
I find the next activity fascinating because it leverages our greatest tool, visual exploration. That's where the human brain is so effective at spotting patterns that numbers alone can conceal.
Visual exploration is absolutely indispensable. EDA tools enable the rapid generation of chart histograms, scatter plots, box plots, and these are used to immediately surface anomalies.
Like an outlier.
Exactly. For example, a scatter plot might show a tight correlation between 2 variables, but suddenly there is a single dot way out in space, an outlier. Maybe someone accidentally reported a $10 million purchase when it should have been $10,000.
And seeing that visually is far easier than trying to spot it in a table of a million rows.
Infinitely easier. Seeing the data prevents you from making blind assumptions.
So EDA tools are kind of the final check against cleaning errors, but they also help us understand the data's spread through distribution analysis. Why is that spread so crucial?
Well, distribution analysis helps you confirm assumptions about the underlying nature of the data. Is it normally distributed, like a bell-shaped curve? Or is it highly skewed, meaning most values are clustered on one side?
Why does that matter?
This understanding is critical because many powerful statistical models, like certain types of regression, actually assume the data fits a normal distribution. If your data is wildly skewed, let's say income data, where most people earn a modest amount but a few earn millions, applying a model that assumes normality is just a recipe for error.
Okay, so what's the big strategic outcome of this whole EDA phase? What does it give you?
It informs crucial downstream decisions. Without ED, the analyst is basically guessing. With it, they can confidently decide on three major things. First, model selection.
Right.
Knowing if the relationship between your variables is fundamentally linear or nonlinear guides your choice between a simple linear regression and a more complex algorithm like a gradient boosting machine. Second is variable transformation.
Gating.
So if that income data is highly skewed, ED might show that applying a logarithm to the variable stabilizes the variance and corrects the skewness, making it suitable for standard modeling.
And the third, decision hypothesis formulation. This sounds like the most exciting part of the detective work.
It is. This is where you might discover an unexpected relationship. For instance, realizing that sales spikes consistently occur 48 hours after a specific competitor's social media posts. That observation provides the precise, testable hypothesis that the formal model should then attempt to answer. It turns a raw observation into a focused scientific inquiry. So once the data is thoroughly understood and you have your hypotheses formed, we move to the heart of knowledge generation: statistical and analytical modeling tools. This is the core engine room where all that clean, structured data is transformed into predictive or descriptive knowledge.
These tools are central because they build models that are designed to achieve, I think you said, three main goals. Can we detail those for the listener?
Absolutely. The models either describe relationships, predict outcomes, or classify observations.
Okay.
To describe relationships, you might measure the elasticity of demand. How much does sales volume change if you adjust the price by 1%? To predict outcomes, you might forecast what customer churn rates are going to be next quarter. And to classify observations, you determine if an incoming transaction should be categorized as fraudulent or safe, which requires immediate operational action.
Got it. And the tools support the core techniques used to achieve these goals: regression, classification, and clustering. Can you just briefly define the function of each one?
Certainly. Regression is what you use when you want to predict a continuous numerical outcome, predicting a specific sales figure, a house price, or a temperature.
A number.
A number, exactly. Classification is for predicting a discrete category or a label. Is this email spam or not spam? Is this loan applicant high risk or low risk? And finally, clustering is an exploratory, what we call unsupervised technique. You use it when you don't have predefined labels.
So you're looking for natural groupings.
Exactly. It groups similar data points together based purely on their characteristics, like segmenting your customer base into budget shoppers and luxury buyers without you having to manually define those segments beforehand.
That seems like a stage of constant refinement, where the first model you build is almost never the best one.
It's entirely iterative. The tools used in this phase have to prioritize flexibility, experimentation, and detailed model comparison diagnostics. An analyst might start with a simple, highly interpretable linear regression model, compare its performance metrics to a highly complex black box deep learning model, and then have to iterate.
So they're adjusting variables, tuning parameters.
Right, or even choosing a different algorithm entirely, all to find that right balance between accuracy and business usability.
So that trial and error necessary to find the best fit really emphasizes that the model isn't a magic box. It's more like a construction project that requires constant testing and modification based on clear diagnostic evidence.
And those diagnostics are key. The modeling tool has to provide clear metrics at every single step, allowing the analyst to understand not just that one model outperformed another, but why. Did it handle nonlinear data better? Was it more robust to outliers? This deep understanding ensures that the resulting statistical relationship becomes a reliable foundation for a real organizational decision.
Okay, we have built the model, potentially iterating dozens of times to find the best fit, but we can't deploy it yet.
Not yet.
We need accountability. This is phase 3, and it starts with validation and performance evaluation tools.
And the requirement here is absolute. Models must be rigorously evaluated before you deploy them. And the reason why is because the model we just built is only proven to be effective on the historical data we use to train it.
Right.
A model that performs perfectly on its training data is essentially like a student who just memorized the practice test. It's useless if it fails the moment it encounters new real-world data, which is the final exam.
So what exactly do evaluation tools provide to meet this essential requirement of proving reliability on that final exam?
They provide two critical outputs: accuracy metrics and error analysis. Accuracy metrics quantify performance. How well did the model predict or classify? If we're talking about regression, a key metric is R-squared, which tells us what proportion of the variance in the outcome the model can explain.
Let's pause there because R-squared is a piece of jargon that needs some clarity. How should we explain R-squared in plain business terms?
Okay, think of the total movement or variability in your sales over the last year. If your model has an R-squared of, say, 0.80, it means that 80% of that total variation in sales can be explained by the variables you included in your model: price, promotions, season, whatever.
And the other 20%?
The remaining 20% is unexplained noise. A higher R-squared generally means a more descriptively powerful model, but it's not the whole story.
I see. And for classification problems, like identifying high-risk clients, the metrics are often more complex, things like precision and recall.
They are, and this leads directly into error analysis, which is often more insightful than just a single accuracy number. Imagine a fraud detection model. The organization has to decide its priority.
Okay.
If they want high precision, they want to ensure that every time the model flags a transaction as fraud, it is almost certainly correct. That means very few false alarms. If they want high recall, they want to ensure they catch almost all of the actual fraud that's occurring. That means very few instances of missed fraud.
That's a key business trade-off, isn't it?
Yeah.
High precision means you annoy fewer customers with unnecessary transaction holds, but you risk letting some fraud slip through.
Right.
High recall means you're catching more fraud, but you risk disrupting legitimate transactions with false positive.
Exactly. And the validation tools, using metrics like precision and recall, force the analysts to articulate this trade-off and align the model's performance with the organization's risk tolerance. Proper validation ensures generalizability, which means the model will perform reliably on new data, and robustness, meaning it can handle minor variations without collapsing.
And this all serves to prevent the great danger of overfitting. That seems to be the central sin of the validation phase.
It is. As we said, an overfit model has essentially memorized the historical data, including all the irrelevant noise and quirks. It's like having a map of your house that details every single dust bunny. It's perfect for your house, but it's totally useless for navigating the neighborhood.
Right.
Validation tools, by testing the model on entirely fresh, held-out datasets, expose this flaw. They force the analyst to simplify or generalize the model, ensuring that the confidence in its predictive power is truly earned. So once the model is validated and we've deemed it robust, we reach the final mile. This is where visualization and communication tools take center stage. You can have the most accurate model in the world, but if the CEO can't understand the insight in under 30 seconds, that model is basically useless.
It's the essential translation layer. The analyst might have a complex 20-variable formula, but the executive needs a clear story and a decisive takeaway. So what is the core function of these communication tools?
Their core function is to translate complex statistical results, a long list of coefficients or error rates, into visual formats that the human brain can process instantly.
So charts, graphs.
Charts, graphs, heat maps, time series visualizations. The analyst is using the tool not just to display data, but to construct a narrative.
But effective communication goes beyond just a pretty presentation. It requires the analyst to curate the view and really highlight the key findings.
Absolutely. The skilled analyst uses the tool to draw the decision-maker's eye directly to the most critical information: the sudden shift in a trend, the highest performing geographical region, or the areas of maximum risk that demand some kind of intervention.
And the sources say modern communication tools demand even more now.
Yeah.
They have to support interactive exploration by the audience.
Yes, that's a huge distinction.
Why is that interactive exploration so vital for a modern organization? Why are static reports sort of fading away?
Because interactive dashboards democratize data access and foster immediate trust. If a sales director sees a drop in revenue and asks, okay, but what about only sales in the East region from 9 a.m. to 11 a.m.?
Right.
They no longer have to call the analyst and wait 2 days for a new static report. The interactive dashboard allows them to click filters, drill down into the underlying data, and explore their own hypotheses in real time.
So the communication tool becomes an active decision support system, and it removes the analyst as the bottleneck to every single follow-up question.
Precisely. And this leads directly to the so what insight. Effective communication tools enable action, not just understanding. If the model says, we should increase inventory in region X by 20% to avoid stockouts, that understanding is meaningless until the inventory manager actually commits the resources.
For sure.
Communication tools provide the clear evidence, the compelling narrative, and the shared confidence needed for management to actually alter strategy and commit capital.
Okay, we've moved from getting the data to turning it into a compelling story that drives action. But what separates a talented analyst doing a great one-off report from a professional, enterprise-level analytics organization?
It's a big gap.
It's the ability to do it again, right? Reliably, accurately, and at scale. And this is where automation and reproducibility tools come in.
This is how analytics moves from being a specialized craft performed once to a scalable, auditable, and reliable business process that can withstand internal scrutiny and even regulatory requirements.
So what are the key capabilities that enable this professional, repeatable process?
They center on three concepts: scripted workflows, version control, and comprehensive documentation. Scripted workflows mean that the entire process, from the SQL query extraction back in phase 1, through all the preparation steps, the model scoring, and finally to the dashboard generation in phase 3, can be run automatically.
No manual mouse clicks.
No manual clicks or intervention. This is essential for reports that need to be generated daily or weekly without any human error creeping in.
In version control, we hear about that in software development all the time. But why is it essential for analysis, which isn't always code?
Well, analytical scripts are code, and version control tracks every single change made to that analysis script or that model training code. This is absolutely vital in collaborative environments.
How so?
If Analyst A modifies the data cleaning routine and 3 weeks later Analyst B sees some really strange results, version control allows them to instantly track when the change was made, who made it, and why. And if necessary, they can revert back to a previous known good state. It's an indispensable tool for managing the complexity and risk in iterative analysis.
So it protects against catastrophic human error.
It does. And the benefits of this focus on reproducibility, transparency, trust, and collaboration are just huge for an organization. Transparency means stakeholders can audit exactly how the numbers were calculated, which demystifies the model and builds confidence. Trust flows from that transparency. When stakeholders know the process is documented and repeatable, they place greater reliance on the results, especially when those results challenge their preconceived notions.
And collaboration is enhanced because standardized scripts and version control ensure that multiple analysts working on the same project are always using the same reliable foundation.
Right. This is how you enforce quality control across the entire data organization. It makes analysis a predictable function, not just a heroic one-off effort.
We have completed the full loop: access, preparation, exploration, modeling, validation, communication, and automation. Now we need to pull back the lens and look at the system as a whole, because as we've seen, the analyst is rarely working in one single siloed tool. #tag integration across tools.
And it's so crucial to reiterate the central theme here. No tool operates in isolation. The analytical lifecycle is a chain. The analyst is constantly shifting environments, moving data from the SQL Access tool, maybe into a statistical scripting environment like a notebook for preparation and modeling, and then finally uploading the summarized results to a separate visualization server.
And that continuous movement of data, that's where integration skills become paramount. It's where things can really break down if they're not handled correctly.
Indeed. The analyst has to be able to skillfully move data between tools, maintain consistency, and proactively avoid duplication of effort or data. Moving data often involves translation layers.
What do you mean by that?
Well, ensuring that data types, formats, and encodings, like character sets for different languages, are preserved accurately between systems. If the date, January 15th, 2024, is interpreted as a text string in the preparation tool instead of a proper numerical data object, all your subsequent time series analysis will just fail silently.
So data consistency is the glue, and the analyst has to be proficient in all those translation layers.
And avoiding duplication is vital for efficiency and reliability. If an analyst performs the same data cleaning steps twice, once in the SQL tool and then again in their Python script, they risk having two slightly different versions of the truth floating around.
That's a nightmare.
It is. Integration tools and skilled analysts who understand data pipelines directly improve efficiency and reduce errors across these workflows. They ensure the data stream stays clean and clear as it flows through all the various specialized pipes.
It really sounds like the modern analyst has to be part data scientist, part software engineer, and part project manager just to move the data correctly.
That's increasingly the reality. And the better they are at managing that integration, the faster and more trustworthy the entire analytical output becomes. Hashtag the managerial perspective.
Now let's turn this discussion to the listener who might be leading an analytics team or managing the budget or setting the strategic direction. This is the managerial perspective providing context on the organizational challenges of supporting this complex integrated analytical system.
For management, the core responsibility is to empower the team by providing flexible tool sets. The pace of technological change is just unrelenting. New modeling techniques, faster databases, specialized visualization methods, they emerge constantly.
So the optimal tool for a specific problem today might be different tomorrow.
Exactly. Standardized software is great for operational reporting, but complex analysis often requires specialized, flexible tools.
But that flexibility has to be managed, right? Otherwise, you end up with chaos, with every analyst using their own preferred software and no one being able to reproduce anyone else's work. I know the source material warns organizations against limiting innovation by falling into a specific trap.
It does. Organizations must avoid over-standardization that limits innovation and restricts the analyst's ability to solve novel problems. If management rigidly insists that all modeling must be done in a single, proprietary, expensive platform, they risk two major drawbacks. First, they might suffer from vendor lock-in.
Meaning the switching costs become so high they can never leave.
Right, regardless of the quality of the service. And second, they stifle their own talent. If the industry-leading techniques are being developed in open-source environments and the organization restricts access to only their internal proprietary tools, their analysts are effectively shackled. They can't grow.
So they can't implement cutting-edge techniques if the software won't allow it, and they can't efficiently integrate with new data sources if the tool doesn't have the right connector.
Exactly. Innovation requires the freedom to select the most efficient mechanism for the job, which often means mixing reliable commercial tools for access with flexible open-source tools for modeling.
That tension between standardized efficiency and the need for flexible, innovative toolsets, that's a constant managerial challenge, isn't it? Especially when budgets are involved. How does an organization decide where to strategically invest its limited resources?
The source material provides a clear framework for this. Tool investment must strategically align with three organizational elements: your data maturity, your analytical objectives, and crucially, the skill levels of your analysts.
So you shouldn't buy a $200,000 deep learning cloud subscription if your main analytical objective is just standardized monthly financial reporting.
Or if your analysts are still struggling with the basics of data cleaning and access. It's about not buying an F1 racing car if your goal is just to drive to the local grocery store. The investment has to be matched to the current capability and the strategic ambition.
Right. So if your primary audience is the C-suite and they need high-level aggregated numbers, you prioritize visualization and communication tools. If your objective is optimizing a manufacturing process, you prioritize modeling and automation capabilities.
The mismatch of investment is a common way companies fail. They either overspend on tools their analysts can't effectively wield, or they hobble their world-class talent by forcing them to use outdated, inefficient systems. The strategy really requires balancing the technology budget with the talent pipeline. Hashtag tech outro.
What an extensive journey. We started with the foundational mindset that tools are enablers, not replacements for the human analyst, and we tracked the entire analytical life cycle, stage by stage. We covered the essential groundwork of accessing and retrieving data, the often painful but vital 80% of the job in preparation and cleaning, the detective work of EDA, the heart of knowledge generation and modeling, the critical check of validation that prevents false confidence, and finally, the crucial accountability provided by communication and reproducibility tools.
And that defined structure and logic, that entire workflow, is what transforms raw, messy data into reliable, auditable organizational knowledge. It's a complex, integrated system, and its weakest point is always the transitions between those phases.
And as we close, let's revisit that tension we identified in the managerial perspective, the difficulty in aligning talent with technology. If investment must strategically align with the skill levels of your analysts, this raises a really provocative question for leadership teams.
Yeah.
How does an organization invest in cutting-edge, innovative tools, the tools required to gain a competitive advantage, without first hiring analysts skilled enough to actually wield them.
And conversely, why would top-tier, cutting-edge analytical talent even join an organization that only provides outdated, restrictive, or overstandardized tools? It forces organizations to think about talent acquisition and tool provision as integrated, mutually dependent strategies, not as separate budget items.
So the strategic investment has to start somewhere.
But where? In the talent or in the technology?
A fantastic, cyclical question to leave with. We hope this deep dive gave you a thorough and strategic understanding of the analyst's comprehensive toolkit. For you listening, think about which stage of this life cycle you find most critical for your own work. Is it the initial cleaning that guarantees integrity, the iterative modeling that generates knowledge, or the final communication that drives real change? Thanks for joining us.
Thank you.
Welcome back to The Deep Dive, the show where we take that complicated stack of data science papers, all that research, the technical notes you send us, and we try to transform them into something you can use right away.
And today's topic, it really gets to the heart of the matter.
It really does. Our mission today touches the bedrock of, well, all of modern AI and predictive modeling. It's the big question. How do we know if a prediction is actually good?
That's the multi-billion-dollar question, isn't it? Whether you're, investing in a system that predicts customer churn or you're managing regulations around loan applications, trust is everything.
And those simple scores you see, they can be so misleading.
Profoundly misleading. So today, we are going way beyond the surface. We're diving deep into the two absolutely core tools you need to make sure any predictive analytics project is trustworthy, stable, and transparent.
Okay, let's unpack this. Our source material today is all about the principles of model validation and performance metrics, and it really lays out the core task for us, validating these models reliably. So the goal for you, our listener, is to walk away with a really crystal clear understanding of two non-negotiable evaluation tools. First, the technique for making sure everything is statistically stable. That's cross-validation.
And second, the diagnostic tool, the one for actually deconstructing the errors.
A mighty confusion matrix.
That's the one. But we have to start with the foundational challenge of model evaluation, because if you get this first step wrong,
the rest is kind of payless.
It's fool's gold, statistically speaking. The absolute fundamental rule for any predictive system is that it must be evaluated on unseen data. Data the model has never, ever encountered before. That's how you assess its real-world performance. It's the moment of truth.
And that initial data split, it's so crucial. It's a concept that I think trips up a lot of people who are new to data science.
Yeah.
Why is using the same training data for testing? Why does that just invalidate the results so spectacularly?
Because the goal of a model isn't just to memorize patterns, It's to generalize them. If you test the model on the exact same data it learned from.
It's not learning, it's just recalling.
Exactly. It's not being tested on its ability to generalize. It's being tested on its ability to perfectly recall its lesson plan. You will always, always generate overly optimistic results.
It's like giving a student the answer key to the final exam.
Perfect analogy. They'll get a perfect score, but that score tells you absolutely nothing about their true competence when they face a new problem out in the world. Validation on unseen data is how we test that true competence.
But even with the simple train test split, there's still a problem, right? If the model's only tested on one random split of the data, say 80% for training and 20% for testing, that single 20% result could itself just be a statistical fluke.
It absolutely could. That split might have accidentally gotten all the easy examples, or maybe it was an uncharacteristically clean subset of data. You just don't know.
So we need stability across the entire data set, not just one lucky shot.
And that perfectly sets the stage for our first major tool, the technique that gives us the statistical rigor we really need, cross-validation.
So let's define cross-validation, or CV. It sounds like a heavy statistical term.
It does, but it's not that bad when you break it down.
Right. At its core, it's really about robustness. CV is this sophisticated technique designed specifically to estimate how well a model will perform on new data by repeatedly testing it across all the information you have.
I like to think of it as buying an insurance policy against randomness.
I like that.
When we rely on just one split, we're basically hoping that split is perfectly representative of the entire world. But what if it isn't? What if, just by random chance, all the really complex edge cases ended up in the training set, leaving the test set way too easy?
Then your performance estimate is completely flawed. It's unstable.
Exactly. CV solves this by forcing the model to split the data, train, and evaluate over and over again. It averages out all that statistical noise from the data splitting itself.
And that becomes so important when you remember that, well, real-world data is always limited and it's always noisy. And sometimes the data sets we're working with just aren't massive.
Exactly. If you have a truly enormous data set, maybe one split is okay. But for smaller, really valuable data sets, every single data point carries more weight.
So our sources point to three key benefits of using CV. It's not just about getting a slightly better average score.
Not at all. First, and most obviously, it significantly improves the reliability of your performance estimates. You see how the model performs across lots of different subsets of the data, not just one.
And second, this is the one everyone talks about. It actively reduces the risk of overfitting.
Overfitting is, it's the central fear in model development. It's what happens when the model doesn't learn the real pattern that generalizes. Instead, it learns the tiny, specific details, the noise that only exists in that one training set.
So an overfit model looks amazing in the lab.
Absolutely spectacular.
Okay.
But the moment you deploy it in the real world, it just collapses because the real world doesn't have that exact same noise. CV helps penalize models that get too attached to the quirks of any single training set by forcing them to validate on lots of different chunks of data.
And how does that penalty actually show up? When an analyst runs CV, what are they looking for?
They're looking at the difference between the training score and the validation score. The training score is always going to be higher.
Okay.
But if the training accuracy is, say, 99%, but the average CV accuracy is only 75%, you have a huge overfitting problem. The model has just memorized the training set, CV narrows that gap, and gives you a much more honest assessment of its real ability to generalize.
And the third benefit?
It supports a fair comparison between different models. Let's say you're trying to decide between a simple linear model and a really complex deep learning model.
You don't want to pick one just because it got lucky on one random test set.
Precisely. You want to see which one consistently, robustly performs better across all the validation sets you can create. CV gives you that apples-to-apples comparison framework.
Okay, let's get mechanical. The most common version we need to talk about is K-fold cross-validation. I think walking through the steps is key here so you can really visualize what's happening.
Definitely. And you can think of K as just the number of rounds or the number of trials you're going to run. A really common standard is to set K to 10.
So step one, we take our whole data set and we divide it into K equal size sections. We call them folds. So if K is 10, we now have 10 little piles of data. Each one is 10% the total.
Then the process begins. In the first round, you pick one of those folds, let's call it fold 1, and you set it aside. It's reserved exclusively for validation, for testing.
And the other 9 folds?
The remaining K1 folds, so folds 2 through 10 in this case, get combined into one big group, and that's what you use to train the model.
So in round 1, the model learns from 90% of the data. Once it's done training, you immediately test its performance on that 10% it's never seen before fold 1, and you write down the score.
That's your first result. Then for the second round, you shift. You reserve fold 2 for validation, and you use folds 1, 3, 4, 5, and so on for training. You train the model all over again from scratch, test on fold 2, and record that second score.
And you repeat this process K times. So 10 times if K10. And the really critical part here is that you guarantee every single data point in your original data set is used for validation exactly once.
Which means at the end, you have 10 separate performance scores. And the final, critical step is that the overall performance metric you report, the number you stand by, is the average of those 10 scores.
And that average is just statistically way more reliable than the result from any single train to split.
It's the definition of statistical rigor.
But this brings up that strategic question you mentioned, the choice of K. Our sources say this is a critical decision, a balance between efficiency and rigor.
It's the classic analyst's balancing act. Let's look at the extremes. If you pick a small K, like K5.
The benefit is speed.
Right, it's much faster computation. You're only training the model 5 times. The downside, though, is that you introduce slightly higher bias into your estimate.
Can you explain that bias connection again? Why does a smaller K create more bias?
Because the training set in each round is a smaller fraction of the total data. If K5, you're only training on 80% of the data each time. That model is learning from significantly less information than the final model, which will be trained on 100% of the data. So the performance estimates can be a little bit skewed or biased compared to what the final model can really do.
Okay, so if a small K has more bias, the natural instinct is to choose a large K, like the standard K10.
Exactly. If you move to K10, the pros and cons flip. You get lower bias, which means a more statistically accurate performance estimate. You're training on 90% of the data, so the model is much closer to what you'll actually deploy.
But the trade-off is the time, the higher computational costs.
A significant cost. You literally double the training cycles going from K5 to K10. And for very complex models, large neural networks on huge data sets, that could be the difference between finishing in a day or in a week.
And if you take that to the absolute extreme,
You get what's called leave one out crock validation, or LOOCV. This is where K is equal to the total number of data points in your set. So in every round, you train on all the data except for one single point, and then you test on that one point.
that sounds incredibly slow.
It gives you the lowest possible bias because the training set is virtually the entire data set. But imagine you have 100,000 observations. You'd have to train the model 100,000 times. It's computationally impossible for all but the tiniest data sets.
So the choice of K is a real strategic call. It depends on your data set size, your model's complexity, and, well, your deadlines.
But there's another layer of complexity here that's really important for real-world data. Imbalance. We talked about how imbalanced data is a problem for simple accuracy, but it also messes with random K-fold CV.
This is a critical nuance. So if we're trying to identify fraud, and only 1% of our transactions are actually fraudulent, what happens if, just by chance, one of our 10 folds ends up with 0 fraud cases?
That fold is useless for validation. You can't test the model's ability to find the positive class if the positive class isn't even there. And that's why analysts move from basic K-fold to stratified K-fold cross-validation.
Gratification. It's about ensuring fairness in the split.
It is. Stratified CV works just like K-fold, but with one extra rule. Before splitting, it makes sure that each of the K-folds has the same proportion of the target class as the overall data set.
So if the whole data set is 1% fraud,
Then every single one of your 10 validation folds will also contain about 1% fraud. This adaptation makes sure every round of validation is meaningful.
which immediately makes the final average score more reliable. So CV isn't just a passive check, it's an active tool for development, especially when it comes to model selection.
Absolutely. Analysts are constantly comparing different algorithms, a support vector machine versus a gradient-boosted tree, or they're tuning the internal settings of the same algorithm.
And if they just rely on a single one-off test, they could just be picking the model that got lucky on that particular split.
Cross-validation takes the luck out of the equation. It forces the models to prove themselves 10 times over. When CV shows that Model A has a consistently higher average score and lower variance, meaning its scores weren't jumping all over the place between the folds, then you can say with real confidence that Model A is just robustly better.
So we've established that cross-validation is how we get a performance number that's stable and trustworthy. But that number, whether it's 90% or 99%, is still just a single data point. It doesn't tell us what kind of mistakes the model is making.
Or which mistakes cost more. We need to look deeper into the failures.
Right, and now we shift focus from the stability of the score to diagnosing the specific nature of the errors, which moves us squarely to our second tool, the workhorse of classification, the confusion matrix.
Yes, the confusion matrix, or CM. This is where we go from that high-level stability to the nitty-gritty details of the errors. It's the core diagnostic tool for any classification model. It's where you lay the model's decision-making process bare for everyone to see.
And the beauty of it is its simplicity, really. It's just comparing the predicted class against the actual class.
That's it. It shows you where the model was right, where it was wrong, and critically, how it was wrong. And it's easiest to understand with binary problems, the yes-no, fraud-not fraud, risk-no risk type decisions.
So we've got a 2x2 grid, and this matrix gives us a complete picture by defining 4 possible outcomes. Understanding these 4 quadrants is the foundation for everything else.
Let's break them down, starting with the 2 ways the model can be right. The true outcomes.
First up, the true positive, PP. This is where the model predicted positive and the actual outcome was also positive. Simply put, we said yes and it was actually yes.
The model correctly found the thing we were looking for. Then you have the true negative, TN. The prediction was negative, the actual outcome was negative. We said no and it was actually no. The model correctly dismissed the things that were not the event. These 2 are success.
Okay, now for the mistakes. The mistakes are always where the prediction is false compared to reality. This is where the model gets confused.
The first type of mistake is the false positive, FP. This is where the model predicts positive. It says yes, but the actual outcome is negative. It was really a no. This is the classic false alarm.
In statistics, they call this a type I error. Think of it like a security scanner that beeps and says threat. That's a positive prediction, but the bag is actually empty. It's an error, it's disruptive, but it's not catastrophic.
And the second type of mistake, often the more serious one, is the false negative, FN. Here, the model predicts negative. It says all clear. But the actual outcome was positive. There was something there. The model missed it.
This is the type 2 error. The security scanner says all clear, but there's actually a dangerous item in the bag. The model failed to detect a positive case when one was really there. This is the failure that leads to real risk.
And just looking at the raw numbers in the confusion matrix gives you immediate insight. You can see right away, are my false positives way higher than my false negatives, or is it the other way around?
But just looking at the raw counts, saying we had 1,000 true positives and 100 false negatives, that can also be misleading if we don't consider prevalence.
That is a crucial point. Prevalence is just the true rate of the positive class in the real world. If you're looking for a disease that only affects 1 in 10,000 people, the prevalence is super low.
Okay.
So even if your model only has 10 false negatives, that might represent 50% of all the actual disease cases you saw. So you always have to read the CM in the context of how rare or common the event really is.
So understanding those 4 quadrants, TP, TN, FP, FN, in the context of prevalence, is the absolute prerequisite. Only then can we move on to the metrics that actually translate this into business performance.
Exactly, which brings us to the metrics that matter.
Right. So once we had the confusion matrix, we can start calculating performance scores. But as you said earlier, the most obvious one, accuracy, is often the most dangerous one to use.
It is. Accuracy is just the total number of correct predictions, TP plus TN divided by everything. It seems so simple and intuitive, but you have to put a giant warning label next to it because accuracy can be extremely misleading with imbalanced data.
Let's use that fraud detection example from our sources. Say we process 10,000 transactions and only 100 of them are actually fraud. So the positive class fraud is only 1% of the data.
Right, 99% is legitimate. So if I build the laziest possible model one that just predicts no fraud every single time,
it would be correct 9,900 times out of 10,000.
its accuracy would be 99%. It looks fantastic on paper, but it's completely useless because it failed to find the 100 critical events we hired it to find.
And that's exactly why we need the nuanced metrics that come from the confusion matrix. They force us to look at the quality of the predictions, not just the overall success rate.
Right. So let's break down the 3 most critical ones, starting with precision.
Precision is also called the positive predictive value. It's calculated as true positives divided by all the things the model predicted as positive, so DP plus FP.
So what precision really measures is when the model says yes, how often is it right? It's a measure of reliability. If a model has 99% precision when it tells you this is definitely fraud, you can be 99% sure it's telling the truth.
And this is really important when false positives type I errors are expensive, when you're trying to minimize waste or disruption.
Think about manufacturing. A model flags a perfectly good product as defective. That's a false positive. That product gets scrapped. That's a direct cost. Or, in marketing, a model identifies someone for an expensive VIP campaign, but they would never buy. That's wasted budget. When wasting resources or annoying good customers is the main driver, you want high precision.
Okay, so now let's flip to the other side of the coin. Recall, which is also known as sensitivity. If precision is about the cost of saying yes when you're wrong, recall is about the cost of saying no when you're wrong.
Recall measures. Of all the things that were actually positive in the real world, how many did our model successfully find? It's calculated as true positives divided by all the actual positives, so TP plus FN.
So this is all about minimizing the false negatives, the type 2 errors. The model's mission here is to be comprehensive, to miss nothing.
And the stakes are often highest here. In cybersecurity, a false negative means you missed a real intrusion. That could be a catastrophic data breach. In finance, a missed fraud attempt is just direct financial loss.
And this leads to that fundamental trade-off. An analyst can usually increase recall just by making the model more sensitive, by lowering the probability threshold so it says yes more often.
But that aggressive approach almost always leads to a huge increase in false positives, which means your precision score drops.
They're like a teeter-totter.
Exactly. You can almost always get higher recall, but you pay for it with lower precision, and vice versa. In those mission-critical systems where missing the event is the worst possible outcome, like missing a disease or a major fraud, you'll usually tolerate more false alarms if it means you get near-perfect recall.
Before we move on, we have to talk about the compromise solution here, the F1 score, because just choosing between precision and recall isn't always enough, right?
That's absolutely correct. The F1 score is the necessary bridge. It's the harmonic mean of precision and recall. The formula is a bit much, but it's basically a way to combine them into one number.
Why the harmonic mean? Why not just a simple average?
Because the harmonic mean heavily punishes models that have really unbalanced scores. Let's say a model has 100% precision. It never makes a mistake when it says yes, but it only has 10% recall, so it misses 90% of the positive cases.
The simple average would be 55%, which sounds okay.
But the F1 score would be much, much lower because it would recognize that the model is fundamentally broken since it can't actually find anything.
So you use the F1 score when you want a balanced model where false positives and false negatives have roughly equal cost or importance.
Exactly. It's often the best single metric to look at when you don't have a clear order from the business to sacrifice one error type for the other.
And we should probably give a quick mention to specificity, the counterpart to recall.
Right. Specificity is just the model's ability to correctly identify the negatives. It's the true negative rate. While recall is about finding all the positives, specificity is about correctly clearing all the negatives. In things like large-scale medical screening, where you want to confidently tell healthy people they're healthy, specificity is really important. But for most business cases, the conversation really centers on that precision recall trade-off, usually summarized by the F1 score.
So to wrap this section up, accuracy can fool you. Precision and recall force you to confront the real-world costs of false positives versus false negatives, and the F1 score helps you find that balance.
Which brings us perfectly to the synthesis. We need to link the stability we got from cross-validation with the diagnostic power of the confusion matrix and turn that into something you can act on.
This is where we put it all together. We have cross-validation for stability and the confusion matrix for the details. How do they work together to give us the full picture?
Well, you can think of them as quantitative guardrails and qualitative diagnostics. Cross-validation tells you how stable and reliable your metrics like precision or recall actually are. So instead of just saying our recall is 95%, the analyst can say our recall is consistently around 95% with very low variance, no matter how we split the data.
It gives you confidence in the number. And the confusion matrix then explains the why behind that number. CV might tell you Model A consistently has a better F1 score than Model B. But the CM, average across all the folds, can show you exactly where Model B is failing.
Exactly. It might show that Model B just racks up way more false negatives, pointing to a specific weakness. So together, they quantify the performance, they reveal the error patterns, and they support a really informed decision.
And this leads us to what is maybe the most critical step for anyone using these models.
Yeah.
The business interpretation of errors. We have to move beyond the abstract stats and talk about money, risk, and what's at stake.
This is where the rubber meets the road. The sources are really clear on this. Different errors have different quantifiable costs that have to be mapped out before you finalize a model.
Let's use that financial sector example again. A false negative in a lending risk model. That means you approve a loan for someone who will eventually default.
And that leads directly to a measurable financial loss. You lose the principal, the interest. So if your main goal is to minimize those catastrophic credit losses, you have to prioritize recall, even if it means you get more false positives.
But on the other hand, let's think about a model flagging potential money laundering. A false positive there, flagging a legitimate transaction as suspicious, that requires a person to investigate.
Right. And that means a compliance officer has to spend their time on it, which creates a huge operational cost. You're paying their salary, taking up their time, maybe even delaying service for a good customer.
So in that scenario, if the human cost to investigate one false positive is, say, $500, but the regulatory fine for missing one actual case of money laundering a false negative is $5 million.
Then the math is simple. The analyst knows they have to tolerate up to 10,000 false positives to avoid a single false negative. The evaluation is no longer statistical, it's pure economic risk management. The model has to minimize the most expensive errors, regardless of what the accuracy score says.
So the data scientist is really acting as a risk calculator, translating these statistical mistakes into dollar amounts.
Precisely. You have to quantify the cost of every FN and every FP, and that cost balance dictates which metric precision, recall, or F1 becomes the true measure of success for that particular project.
But even these powerful tools have their own limitations and practical constraints. It's never a perfect science.
The first one, which we mentioned, is purely technical, computational cost. Cross-validation costs time and money because of all the repeated training. For huge models, analysts sometimes have to compromise, maybe use a smaller K, and accept a little less statistical rigor just to get the job done.
And the second constraint is maybe deeper, and it's often where the arguments happen in meetings. The metrics from the confusion matrix depend completely on the chosen classification threshold.
This is so fundamental. A classification model doesn't just spit out a yes or no. It gives you a probability, like 0.60, that an event will happen. The analyst then has to set a threshold, usually 0.5 is the default. Anything above that is a yes. Anything below is a no.
So if the model outputs a probability of 0.49 and your threshold is 0.50, that's a no. But if you just move the threshold down to 0.45, that same 0.49 score suddenly becomes a yes.
And that tiny adjustment completely changes the numbers in your confusion matrix. A false negative can instantly become a true positive. A true negative can become a false positive.
So moving that threshold is how you actively trade precision for recall.
It's exactly how you do it. If you want higher recall to find more positive cases, you lower the threshold. You make the model more eager to say yes. You'll catch more true positives, but you will absolutely sweep up more false positives, and your precision will go down.
Analysts use tools like the ROC curve to visualize that trade-off, right? To find the sweet spot.
Yes, to find the point where the ratio of benefits to costs is maximized for the business. And that choice of threshold is where the technical work meets the business mandate. The analyst has to answer. At what probability are we okay with missing something versus how often are we okay with a false alarm? That balancing act between accuracy, interpretability, and practical impact is the ultimate responsibility.
What a fantastic deep dive. We've really covered everything from protecting the stability of our scores to calculating the literal dollar cost of every mistake.
We built confidence in the number with cross-validation, and we diagnosed the failures with the confusion matrix.
So let's pull all these threads together for the final takeaway. If you remember nothing else from this deep dive, remember this. The results you get on your training data are inherently misleading.
Always.
Cross-validation is your defense. It gives you stable, trustworthy performance estimates by forcing the model to prove itself over and over on unseen data.
And the confusion matrix, with metrics like precision and recall, gives you the detailed insight into what kind of mistakes the model is making. It differentiates between the costly missed alarms, the false negatives, and the costly false alarms, the false positives.
And being well-informed here means understanding that simple accuracy rarely tells the whole story. The real success metric is dictated by the costs of the specific errors that most harm your business.
Exactly.
So we always end with a provocative thought. We've talked a lot about the trade-off between recall and precision. And it's really an ethical choice hidden inside a statistical process, isn't it? The act of choosing which error is less bad.
It absolutely is. I mean, consider a model a bank uses to approve mortgages. If the analyst sets the threshold to maximize precision, to minimize false positives so they never waste time on a bad application, they are, by definition, increasing false negatives.
Which means they're rejecting more people who are actually creditworthy. They're classifying them as a negative risk when they were really a positive.
And that choice determines whose risk gets prioritized. The bank's operational costs, which is precision, or the public's fair access to credit, which is recall.
It's a huge decision.
It is. Now, let's tie this back to the core problem with accuracy. Let's say a model achieves a stellar 99% accuracy, which on paper looks amazing. But then we discover it fails 100% of the time on that tiny 1% of the data that represents the rarest, most critical outcome.
Like a black swan event, a major system failure, or a specific kind of fraud.
Exactly. Is that model truly useful? You have to make sure your statistical scores reflect the practical reality and the risk landscape, not just the sheer volume of easy, correct answers.
An excellent challenge. That is the essence of building predictive systems we can actually trust. That's all the time we have for this deep dive. Thank you for walking us through these indispensable tools. Welcome back to the deep dive. Our mission here is to take those complex piles of sources, articles, research your notes, and distill them into the nuggets of knowledge you need to be truly well-informed. Today, we are wrestling with a really foundational topic. It's something that underpins virtually all successful modern analytics: predictive accuracy.
It really is. I mean, without exaggeration, it's the hinge upon which the entire utility of data science turns. If a model can produce these elegant, mathematically precise results that, simply fail in the real world,
Then what's the point?
exactly. The whole exercise is just academic and, frankly, very expensive.
Right. And we've been immersed in principles and frameworks that define what makes a prediction truly reliable. And critically, what separates a statistical parlor trick from a genuinely useful forecasting tool.
Yeah.
Our mission today is a deep dive into these core principles of predictive accuracy and model evaluation. By the end of this conversation, you'll know exactly how to scrutinize a model's performance metrics and really understand the strategic implications of choosing one metric over another.
Okay, let's unpack this. the fundamental purpose of assessing predictive accuracy. When people first start building a model, they often get really excited about how well it explains the past, right?
Oh, absolutely. They love how nicely it fits the training data.
But that's a fool's errand.
It is. The goal is absolutely not fitting old data perfectly. That's probably the most common and honestly the most dangerous mistake people make.
Right.
Predictive modeling isn't history class, it's prognostication. The true measure of success, the core value proposition, is generalization.
Generalization. So how well the model works on new, unseen data. Precisely. Data it has never processed. Data that reflects the future. That's the only thing that matters.
And the sources are incredibly clear on why this assessment is so important. I mean, it doesn't just produce a score, a single number. It determines 3 critical things that decide the fate of any project.
Right.
1, model usefulness. Is this thing actually helpful? Does it provide any benefit over, just guessing?
A very low bar that many models fail to clear.
Then 2, model selection. If you built 3 different versions, say a random forest, a neural network, and maybe a simple logistic regression, which one do you pick?
The performance assessment is the tiebreaker. It has to be.
And 3, readiness for business deployment. This is the big one. Can we actually trust this with real-world decisions that have financial consequences?
And that last point leads directly to the single most critical concept in all of this. We have to address the idea of conflating training accuracy with predictive accuracy. Training accuracy, the number measured on the data used to build the model, is almost always wildly optimistic. It's a self-congratulatory measure.
It's the student grading their own incredibly specific, bespoke homework assignment. They've seen all the answers before.
That's a perfect way to put it.
Of course they're going to get an A. The real test is the pop quiz on new material they've never seen.
That's right. The predictive, or what we call out-of-sample accuracy, is the truth serum. It reflects real-world performance because it is measured on validation or test data the model hasn't seen and, critically, hasn't been allowed to learn from.
So if you want trust,
you have to look at the out-of-sample results, period.
Yeah. Okay, so core takeaway right out of the gate. Reliable analytics focuses solely on predictive accuracy, never ever on the training fit.
Never.
So if someone presents you with a model boasting 99% accuracy, your immediate critical question should be,
is that measured on the training set? And what is the performance on new, unseen data?
And if they can't show you that out-of-sample performance,
then the model is statistically questionable and, I would say, managerially very risky.
Now that we understand the danger of looking only at the training set, let's talk about the essential strategy for avoiding the biggest threat in predictive modeling, the overfitting trap.
This is the moment of failure for just so many projects. Overfitting occurs when a model performs extremely well on the training data.
Looks fantastic.
Right, it looks amazing. But not because it has learned the generalized underlying relationship between the variables. It's because it has essentially memorized the noise, the outliers, and all the little idiosyncrasies specific to that initial data set.
It's a fantastic pattern matcher for the past, but it has zero capacity to handle anything new.
Zero.
I think of it as a CEO who only looks at the internal quarterly report and optimizes solely for those specific known numbers, the moment market conditions shift outside that narrow, memorized window.
The whole business model just collapses. It's brittle. That's a perfect analogy. The result is a spectacular failure on any new data.
And what's the sign? How do you know this is happening?
The primary sign of this failure, the diagnostic tool that tells you you're in trouble, is a large, noticeable gap between the training accuracy and the test accuracy.
Okay, so for example,
if your training accuracy is, say, 98%, suggesting near perfection, but your test accuracy drops to 70%.
wow, that's a huge drop.
It's a massive drop, and it means your model is massively overfit, it's too brittle, too sensitive, and fundamentally unreliable for production.
And this is why accuracy assessment isn't just a reporting exercise at the end. It's the primary tool you use to detect and prevent this risky behavior as you build.
That's right. It requires extreme discipline in how you handle the data.
Which leads us directly to the data holdout strategy.
Yes. If we want metrics that genuinely reflect real-world performance, we have to isolate the data. This requires a stringent three-way division of the overall data set, this separation. It's just non-negotiable for anyone building trustworthy models.
Okay, so 3 parts. First, you have the training set.
Right. This is the largest segment, maybe 60% or 70% of the total data. And it is used exclusively for the heavy lifting of model building. Learning parameters, establishing weights, defining the core relationships, All the learning happens here.
Okay, so that's bucket one. What's the second?
Second, we carve out the validation set. This is a smaller but incredibly important subset. It's typically used during the development phase for model tuning.
So it's like the practice test.
Exactly. It's the practice test that helps you get better. For instance, if you're using a deep learning model, you might use the validation set to decide whether the network should have 2 hidden layers or 4 or maybe 10. You tune what are called the hyperparameters until you find the optimal configuration.
The one that performs best on this unseen validation data.
Exactly right. And by doing that, you prevent early, subtle forms of overfitting.
That distinction is crucial. So the training set builds the model, the validation set tunes the model. But we still need a final, impartial judge.
We do.
Which brings us to the rockstar, the truly critical set, the test set.
Absolutely right. The test set must be entirely distinct from both the training and the validation data. It is reserved solely for the final, one-time evaluation. This set must remain untouched until the very end.
Untouched. Why is that untouchable status so important? Why is it considered contaminated if we just, peek at the test set early?
Because of a concept called information leakage.
Okay.
Information leakage occurs when knowledge from the test set even indirectly seeps into the model building or tuning process. If an analyst tests Model A, sees the test set score is 80%, then goes back and tweaks Model A specifically to improve that 80% score.
They've cheated.
They've cheated. They have compromised the integrity of the test set.
It's like the teacher giving the students the actual exam questions ahead of time. I mean, yes, they will score 100%, but that score is meaningless because it doesn't reflect their actual general capability.
Exactly. The test set's sole purpose is to provide an unbiased estimate of the model's performance in the real world. If you use it even once during tuning, you contaminate it, and your final accuracy score becomes overly optimistic again.
So it's not just neat housekeeping.
Not at all. That strict data discipline is non-negotiable for producing trustworthy results.
Okay, so moving on to the actual measurement tools themselves. When we build a classification model, a model that sorts things into discrete buckets like approve or deny, positive or negative, high risk or low risk, we start with the most intuitive metrics, but, well, they quickly fail us.
We usually start with the 2 most basic metrics. The accuracy rate, which is the percentage correctly classified, and the error rate, the percentage incorrectly classified.
Simple enough. 85% accuracy means 85 out of 100 predictions were right.
Easy to explain.
Yep.
But the problem, as we kind of established earlier, is that their shared limitation is that they're often extremely misleading, especially when dealing with what we call imbalanced data sets.
This is such a critical point.
It is. Imagine you're trying to predict a truly rare event, say, identifying a specific form of cyber attack that only happens 0.1% of the time.
Okay, very rare.
Very rare. If your model simply predicts no attack 100% of the time, what's its raw accuracy? It's 99.9%.
Exactly. You've achieved statistical perfection while failing completely at your core job.
Right. So raw accuracy is worthless in any high-stakes scenario involving rarity. We need deeper, more diagnostic metrics that show us where the model is succeeding and, maybe more importantly, where it is failing.
And that's where the confusion matrix becomes the analyst's best friend.
The confusion matrix.
It is the foundational diagnostic tool for classification. It forces us to categorize every single prediction into one of 4 buckets, and that moves the discussion way beyond a single, simple score.
Let's quickly define those 4 pillars, because everything else flows from here. First, you have the wins, right?
Right, the correct predictions.
So true positives, TP, which is when the model correctly identifies a positive instance, and true negatives, TM, where it correctly identifies a negative instance.
Those are your wins. Then you have the mistakes. You have the false positive, FP, or type by error. We often call this a false alarm.
So the model said yes, but the reality was no, correct. And then you have the false negative, FN, or type 2 error, which is often called a miss. The model said no, but the reality was yes.
And this breakdown is what allows us to unpack the subtle, really strategic metrics derived from the matrix. Let's start with precision, because its business context is immediately vital.
Okay, so precision measures the reliability of your positive predictions. The question it answers is, out of all the times the model said yes, how often was it truly correct?
So the formula for that would be true positives divided by the sum of true positives and false positives.
That's it. And the strategic context is this. Precision is vital when false positives, those false alarms, are costly or really irritating.
Like an email spam filter. If the filter has low precision, it flags a critical work email as spam. That's a false positive. The cost is annoyance and maybe lost information.
Exactly. So in that scenario, we prioritize high precision to minimize those false alarms. Or think about a bank's anti-money laundering system. If it flags an innocent, loyal customer's transaction, that's a false positive that could lead to account closure and loss of reputation.
You need high precision there.
You absolutely do. The counterpoint to that is recall, which is also known as sensitivity.
Okay. And recall measures.
It measures the model's ability to identify the actual positives. So the question here is, out of all the events that should have been flagged, how many did our model actually catch?
And this is vital when missing a positive. A false negative is catastrophic.
Catastrophic. The classic example is an airport security scanner. If that scanner misses an actual weapon, that's a false negative. The cost is extremely high, lives are at stake.
So in that case, you design the model to maximize recall. You want to catch everything.
Right. Even if it means generating a few more false positives, a few more false alarms that require a manual check, the cost of the miss is too high to do otherwise.
And then there's the third one, specificity.
Right. Specificity is essentially the countermetric to recall. It's the ability to correctly identify the negatives. In a quality control scenario where 99% of manufactured parts are good, high specificity ensures that the model correctly confirms the overwhelming majority of those good parts, keeping the process running smoothly and efficiently.
What's fascinating and also a bit frustrating for analysts is that precision and recall often exist in this inverse trade-off.
They do. Improving one usually decreases the other.
We call this the precision recall trade-off. And analysts spend countless hours tuning the model's decision threshold to manage this balance.
And this is why merely looking at precision or recall in isolation just isn't enough when you have a mixed priority. This leads us to another metric, the F1 score.
The F1 score. I've heard this is the harmonic mean of precision and recall.
It is.
But why the harmonic mean? Why not just a simple average?
That's a great question. Because a simple average allows an extremely high score in one area to completely compensate for a catastrophic score in the other. The harmonic mean is much stricter. It penalizes extreme performance in either direction. If your precision is near zero, your F1 score will be near zero, even if your recall is perfect.
So the F1 score becomes the go-to metric when you need a general model that requires a high-quality balance between catching the event and ensuring the events you caught are real.
Yes, it's the default metric for many general classification problems because it enforces that necessary analytical compromise.
And it all comes from that confusion matrix, which lets analysts visualize and quantify this trade-off, moving us light years past the misleading simplicity of just raw accuracy.
Exactly.
Here's where it gets really interesting when we focus entirely on the problem of rare events. We touched on this with the 99% accurate failure, but let's drill down into the strategic implications.
Okay.
This is where the simple definition of accuracy completely breaks down and, well, becomes a liability, especially in high-stakes fields.
This phenomenon just dominates high-stakes business problems. We're talking about identifying high-risk clients for loan default, forecasting catastrophic machine failures in industrial settings, or, like we mentioned, rare medical diagnostics.
And the key feature is always that heavily imbalanced data set.
Always. The event of interest, the positive, might occur in less than 1% of the observations.
Let's use a financial example. Predicting customer churn. Suppose only 2% of your customers churn in a given month.
A very common business problem.
Right. A naive model that predicts no churn for every single customer achieves, 98% raw accuracy.
It does. And if you, the business leader, are presented with that 98% number, you might think you have a fantastic model.
But it's completely useless.
Utterly useless, because it failed to identify the only 2% of people you actually needed to intervene with. That high raw accuracy is achieved simply by predicting the majority class. This is the paradox of accuracy and imbalanced data.
So what's the analytical mandate in these rare event scenarios? When the thing you are looking for barely ever happens, how do analysts create a model that actually serves the business purpose?
Well, first, raw accuracy is banished. It's out. Analysts have to pivot immediately to the diagnostic metrics, specifically framed around that rare positive event.
And the first one they turn to is recall.
First and foremost, they rely heavily on recall. The goal is finding the rare event. If the mission is to catch catastrophic machine failures, how many of those actual failures did the model identify? We have to prioritize getting recall as close to 100% as is practical.
Because a missed failure A false negative.
is often exponentially more costly than a false alarm.
Okay, so that's number one. What's second?
Second, they use precision to gauge the utility of the flags. If the model flags something as a rare event, like potential fraud, we need a certain level of confidence in that flag, especially if intervening is expensive.
Right, shutting down a machine for maintenance or freezing a bank account, that comes with a real cost.
It does. And third, the highest level of analysis moves beyond mere statistics into cost-based evaluation. This is where data science meets finance. The analyst has to quantify the financial impact of each type of error.
Okay, let's walk through that. Imagine an industrial scenario. A false negative missing a catastrophic machine failure means, say, $1 million in lost production and repair costs.
A huge cost.
And a false positive, shutting down a healthy machine for an unnecessary inspection, costs maybe $5,000 in lost efficiency.
Given those costs, the analyst would overwhelmingly optimize the model for recall. They would be willing to tolerate 100 or even 200 false positives.
Which would be, what, $500,000 to $1 million in false alarm costs?
If it means driving that false negative rate down to zero and preventing that single $1 million catastrophe.
And that's the strategic decisions. The business relevance, dictated by the cost structure of the errors, always outweighs raw accuracy numbers.
Always. The metric you choose must reflect the operational risk and financial stakes of the prediction.
Which can be a tough conversation with non-technical stakeholders who just want to see the highest number possible on a slide.
It can be very challenging.
We've spent a lot of time on classification models that sort things into buckets. But as we know, many predictive models deal with continuous values, predicting a future sales volume, estimating a temperature curve for energy demand.
Or projecting the volatility of a financial asset.
Exactly. We are moving now to continuous variables, and the classification metrics we just discussed, precision, recall, the whole confusion matrix, they just don't apply anymore.
That's absolutely correct. When the model predicts a numeric continuous value, we don't care if the prediction was right or wrong in a binary sense.
We care about how far off it was.
We care about the size or the magnitude of the error. We need metrics that quantify how far off the prediction was from the actual outcome.
And we use 3 key error metrics here. Each one provides a slightly different lens on the error distribution.
Yeah.
And the choice between them really reflects the business tolerance for large mistakes. Let's start with the most straightforward one. Mean absolute error, MAE.
Right. MAE is simply the average absolute prediction error. You calculate the difference between the prediction and the actual value. You take the absolute value of that, so it doesn't matter if you overshot or undershot, just the distance, and then you average all those absolute differences across the entire test set.
And its main strength is that it's just so easy to interpret.
It is. If your MAE is 10 units, say $100,000 in sales volume, it means that on average, your forecast was off by $100,000. It's linear and easy for non-technical stakeholders to grasp immediately.
And treats all errors equally, right? An error of 10 contributes the same amount as 2 errors of 5 each.
Exactly. Which brings us to mean squared error, MSE. This metric introduces a mathematical change with massive strategic implications. Before you average them, the individual errors are squared.
So you're not looking at linear distance anymore.
No, the difference between MAE and MSE is essentially the difference between calculating linear distance versus penalizing distance exponentially.
So why do that? Why square the errors? What does that mathematical operation achieve for the analyst?
Squaring the errors achieves one goal above all others. It heavily penalizes large errors much more than smaller ones. This is the metric of choice when large outlying errors are particularly undesirable or even catastrophic.
Can you give us an example of how that penalty stacks up?
Certainly. Let's stick with simple numbers. An error of 2 is squared to 4. A large error of 10 is squared to 100.
Okay.
Notice that the large error of 10 contributes 25 times more to the total MSE than the small error of 2. If a model makes 10 small errors of 2, the cumulative squared penalty is only 40. But if it makes just one large error of 10, the penalty is 100.
Wow. So that means if you're building a model where a single massive miss could cause structural failure in engineering or market destabilization in finance, you absolutely must optimize for minimizing MSE.
You have to. It forces the model to prioritize avoiding those catastrophic outliers, even if it means slightly compromising its performance on smaller, more common errors.
It's a trade-off.
It's all about what kind of error you're willing to tolerate. MAE is excellent for, say, linear inventory forecasting, where the cost of being off by 10 units is literally 10 times the cost of being off by 1 unit. But MSE and RMSE are required when the cost of error scales nonlinearly, like in structural engineering or high-stakes financial volatility prediction.
But as you pointed out, the squaring creates an interpretability problem. If we were predicting sales in dollars, our MSE is now in squared dollars, which, I mean, that's analytically correct, but practically meaningless to a non-technical audience.
It's gibberish to them, and that's why we have the third metric, the one most commonly used in practice to retain the strategic benefit of MSE while regaining clarity. Root mean squared error, RMSE.
Okay, so RMSE is just the square root of the MSE.
That's all it is.
So we square the errors to punish the outliers, we average them, and then we take the square root to bring the unit of error back into the same scale as the predicted variable, back into dollars or Celsius or units of sales.
It provides the best of both worlds. You get to keep that heavy penalty on large errors, which is often what the business needs to avoid catastrophic failure. But the final number, the RMSE, is easily interpretable. You can tell a manager, our average error weighted against our biggest misses is $125,000. It represents a much better balance for communicating risk than raw MSE.
Right, that makes sense.
So once we've calculated these metrics, whether it's F1 score for classification or RMSE for numeric prediction, we can't just look at the raw number and declare the model good.
Not in a vacuum.
No, we need context. Which brings us to the crucial discussion of relative accuracy and baseline models.
I find this to be one of the most sobering and important sections of any data project.
Yeah.
Absolute accuracy is, well, it's meaningless without a point of comparison.
Completely. Predictive accuracy must always be evaluated relative to a benchmark.
This is the baseline requirement. If you walk into a meeting and claim your model has 80% accuracy, the first strategic question should be,
what would happen if we did nothing or used the simplest possible guess? The model needs to be compared against common, easy-to-implement baselines.
and we're talking about naive models here.
Exactly. In forecasting, a naive model might just assume tomorrow's sales will be identical to today's sales, or last month's.
Or it could just use the historical average or median value for all predictions.
Right. These models are simple, they require no machine learning sophistication, and they are essentially free to implement. They represent the absolute minimum hurdle that your complex, sophisticated model must clear.
So if your complex neural network model predicts sales with an RMSE of 100, but a simple model that always predicts a median sales volume achieves an RMSE of 105.
What is the value proposition of the complex model? Is that 5-point improvement worth the cost and complexity?
And that's the test of value. A complex model involving deep learning, hundreds of features, and expensive computational power is only valuable if it definitively and significantly outperforms these simple alternatives.
It has to. If your $500,000 model is only 1% better than simply using the average, the business justification just evaporates. You should use the average.
The sources emphasize that this required uplift over the baseline needs to be quantified and justified. If the lift is small, the trade-off in complexity, maintenance, and compute costs simply isn't worth it.
Not at all.
Okay. Now, beyond raw performance relative to a baseline, we have to look at consistency. A model isn't deployable if its accuracy is great one day and terrible the next. We need to talk about stability and robustness.
Yes. A robust model performs consistently across different data samples and across different time periods. If you sample a different 70% of your historical data to train the model, the resulting performance shouldn't drastically change.
And if it does,
That sensitivity to minor data fluctuations is a huge red flag. It's a sign of underlying fragility.
so how do we scientifically measure that sensitivity and stability before we deploy the model?
We rely on a technique called cross-validation, specifically K-fold cross-validation.
K-fold.
Instead of a single 70-30 split, K-fold cross-validation involves splitting the entire training data into, say, 10 equal segments, 10 folds.
And what happens then?
Yeah.
10 different splits.
Essentially, yes. We run the training and testing process 10 separate times. In the first run, we use the first 9 folds for training and hold out the 10th fold for testing. In the second run, we use folds 1 through 8 plus 10 for training and test on the 9th fold.
So you cycle through.
You cycle through until every single fold has been used exactly once as the holdout test set.
That sounds pretty intensive. What's the output? What do you get from all that work?
The output isn't a single accuracy score. It's a distribution of 10 different accuracy scores. And this is the key. If those 10 scores are tightly grouped, say between 84% and 86%, your model is stable and robust.
It means it's not sensitive to which 10% of the data you happen to hold out.
Exactly. But if those scores are wildly varied, 95% on one fold and 60% on another, you have an unstable model that is highly sensitive to minor changes in the input data.
And the risk implication of that instability is enormous.
Oh, it's huge. Unstable models are extremely risky when deployed in production environments because you have no reliable guarantee of their performance when a new, slightly unexpected batch of real-world data arrives. That instability can be catastrophic if the prediction drives automated high-volume decisions.
Right.
Which really brings us to the ultimate so what section connecting all these statistics to actual strategy. If we connect this to the bigger picture, accuracy assessment is not just a technical measurement. It is fundamentally a technical and a managerial decision.
Driven by the organization's priorities.
Absolutely. This is where the statistically best model often fails because it's not the business best model. You can have two models with identical 90% raw accuracy scores, but one is clearly superior based on context.
How so?
Well, it's because the selection of metrics and the final decision to deploy must align perfectly with three critical elements. First, business objectives. Are we trying to maximize growth, minimize risk, or optimize efficiency? Second, the cost of specific errors, which is that trade-off we discussed between false negatives and false positives.
And third, the company's own risk tolerance.
Yes. A pharmaceutical company predicting which drug candidates might cause severe side effects has an incredibly low risk tolerance for false negatives.
They can't miss one.
They cannot. They will prioritize recall and specificity above all else, even if it means rejecting some viable drug candidates along the way.
Contrast that with an aggressive e-commerce startup trying to personalize product recommendations.
Their risk tolerance is high. If they recommend a product you don't like, what's the cost? A fraction of a second of your time. It's nothing.
So their focus is on maximizing recall and overall engagement. They can tolerate a much higher rate of false positives because the errors are cheap.
Precisely. And so the bottom line is critical. Managers must drive the evaluation process based on these contextual factors. The analyst provides the technical metrics, the RMSE, the F1, the recall, but the manager dictates the thresholds and the relative weight of the errors based on strategic goals.
You can't outsource that strategic risk decision to the algorithm.
You absolutely cannot.
As we wrap up this deep dive, we need to briefly touch on how analysts communicate all of these nuanced decisions, especially the trade-offs we've discussed, to those managing the business and, holding the budget.
A critical skill.
Yeah, if you tell a VP of marketing you chose a model because of its F1 score versus its ROC AUC, you might just lose them.
You will definitely lose them. Absolutely. Visualization is essential for clarity here, for translating statistical performance into strategic value. While the confusion matrix gives you the hard numbers, visual tools support the communication and understanding of accuracy.
Especially when presenting to non-technical decision makers.
Especially then.
Specifically, the sources cite lift charts and gain charts as highly effective diagnostic tools. How do these help management understand performance in, actual business terms?
Okay, so these charts translate the model's performance into return on investment. For a classification model, say, predicting which 10% of customers are most likely to respond to a new promotion, the lift chart shows you how many more positive respondents you identified using the model compared to just choosing a group of customers randomly.
So if the model has a lift of 3.0 in the top decile,
it means that by targeting the top 10% of customers identified by the model, you will capture 3 times as many positive responders as you would if you targeted a random 10% sample.
now that speaks the language of marketing efficiency.
Exactly. Similarly, error distributions are crucial in numeric prediction. Instead of just giving the RMSE number, showing a visual distribution of the errors allows a stakeholder to see, are our errors concentrated near zero, meaning we are mostly accurate, or do we have a few massive high magnitude errors sitting way out on the tail of the distribution, which validates our need for a metric like RMSE to aggressively penalize them.
It bridges the gap.
It does. These visual diagnostics significantly improve the process of selecting the final model and bridge that gap between technical output and strategic deployment.
So what does this all mean? It means you now understand that evaluating a predictive model is far more nuanced than looking at a single number on a screen. It requires tremendous discipline in data preparation.
Especially the stringent isolation of the test set to prevent that information leakage.
It demands the use of diagnostic metrics like precision, recall, and RMSE to understand the nature and the magnitude of the errors.
Right. Not just that an error occurred, but what kind it was.
And ultimately, it requires a deep strategic understanding of the cost-specific errors and the company's tolerance for risk. Predictive accuracy is not a one-time measurement. It's an ongoing process of optimization that must align perfectly with strategic business goals.
And since stability is paramount, and an unstable model is a huge liability when market conditions change, businesses really must go beyond standard K-fold cross-validation. They should consider implementing specific stress tests, things like adversarial testing or drift detection. This ensures model robustness during periods of unexpected extreme market change or black swan events. For example, you could explicitly test the model using data from the 2008 financial crisis or a major global supply shock, even if that data isn't typical of your current operating conditions.
So you're testing for resilience against things that haven't happened yet but could.
Exactly. That level of scrutiny testing, not just against expected variations, but against systemic shocks, is what ensures the model's reliability truly holds up when the stakes are highest. That's the challenge that awaits every data-driven business. Welcome back to the Deep Dive. Today, we are cracking open the mathematical machine that drives almost every fundamental binary decision in modern data analysis. If you've ever had a loan approved or seen an email land in your spam folder, or even wondered if a customer was about to jump ship, well, you've seen this exact process in action. We're talking about the most fundamental question in predictive modeling: yes or no, success or failure, approve or deny. And if you need a model that's transparent, reliable, and just incredibly fast to deploy, you absolutely have to start here. We are doing a deep dive into binary classification, and specifically the statistical powerhouse that is logistic regression. So if you're preparing for a high-stakes meeting, or maybe you're catching up on predictive modeling techniques, or you just want that ultimate shortcut to understanding how major companies calculate risk and make these huge automated decisions, you are in exactly the right place. Our mission today is to cut through all the complexity and really understand the logic, the application, and of course, the necessary limitations of this approach.
That's precisely it. Logistic regression, or LR as we'll probably call it, it solves that core problem of predicting one of two possible outcomes. It is, the purest form of binary classification. You're looking at a system that's just designed for clear answers. Will they stay or will they churn? Is this transaction fraudulent or is it legitimate? Is the medical test positive or negative?
Right.
But here's the critical difference between LR and, say, just flipping a coin. The core function isn't merely to guess. It's to estimate the probability that an observation belongs to a particular class.
So it's not just the what, it's the how likely.
Exactly. It doesn't just categorize, it quantifies the confidence behind that category. It'll tell you, based on these 15 factors, there's an 85% chance this customer will default.
Oh, yeah.
And that is so much more powerful than a simple default label.
And what's fascinating in the sources we looked at is that we're not just talking about abstract Python libraries today. We are looking at this through a really specific practical lens: the tool Excel Miner. For the learner, for the business analyst, or maybe in teaching environment, Excel Miner is key. It's an Excel-based tool, an add-in, that makes building, validating, and interpreting these sophisticated models, well, it makes it accessible without having to wrestle with code.
It really is. You could call it the democratization of the predictive model, in a way.
Okay, so let's unpack this a little. The world of data science is, it's rich with classification methods. We have everything from simple decision trees to these giant black box things like deep neural networks. So why, in this really high-tech landscape, should we still prioritize and choose logistic regression, a model that's been around for decades? When is it the right tool for the job?
It really comes down to two things: suitability and necessity, especially when you're facing scrutiny. The suitability criteria are very specific. The response variable, so the thing you're trying to predict, it must be categorical and it must be binary. Just two outcomes.
So, yes or no. That's it.
That's it. Now, if you're predicting more than two things, like small, medium, large, you need a different tool, a multinomial extension. But for the fundamental binary problem, LR is purpose-built. But here's where its flexibility really shines. While the target is rigid, the predictor variables, the inputs you feed the model, can be incredibly diverse.
Okay.
They can be numeric, like age or credit score or days since the last purchase. And they can also be categorical variables, things like region, marital status, or product type. LR handles this mixed input beautifully as long as you do the prep work.
That's an important distinction, I think. A lot of people coming from, say, a spreadsheet background might assume a model only wants numbers. The fact that it can blend customer demographics, their transaction history, geographic location, all in one single equation, that really speaks to its power.
It does. And that flexibility, combined with the way it presents its output, is what makes it so robust, particularly in these high-stakes worlds. We talk about the dual benefits. the probabilistic outputs we've mentioned, and maybe even more importantly, the clear interpretability of the predictors.
The interpretability, the why.
The why, exactly. Think about regulated industries, banking, healthcare, insurance. They don't just need a fast prediction, they need an explanation, one that satisfies regulators, auditors, ethicists. They need a full audit trail. If you deny someone a loan, you have to be able to legally explain why. Not just my AI said so, but the applicant's debt-to-income ratio and their prior default history drove the prediction with this level of confidence.
So if I'm a compliance officer listening to this, what is that audit trail I need? Is it just the raw probability number, or is it something else?
It's the coefficients and the odds ratios, which we'll definitely dig into later. Those numbers provide the explicit quantified link between a person's data, their salary, their debt, and the final prediction. They explain the mechanism. A neural network might give you a slightly more accurate prediction, maybe, but it can't easily provide that clean, linear explanation of influence. And that's why LR is still the standard for transparency.
It's the simple geometry of the model that makes it so easy to reverse engineer the logic.
Exactly. And that simplicity feeds directly into its status as a robust baseline model. When you start any new classification task, analysts almost never jump straight to the most complex solution.
They start simple.
They build a simple, well-understood, and highly interpretable logistic regression first. And why? Because it provides a measuring stick. If a cutting-edge, super complex algorithm can only beat your simple LR model by, say, 0.5 percentage point in accuracy, well, the added maintenance costs, the computational expense, and the total loss of interpretability are almost never worth that tiny gain.
That's a critical point for anyone learning this. You're saying success isn't just about getting the highest accuracy score, it's about the optimal trade-off. If all that complexity only buys you a tiny fraction more accuracy, you should opt for the simple model you can explain in 2 minutes to the CEO.
The trade-off has to be justified. And in environments where transparency is a performance metric, where failing to explain a decision incurs legal or financial penalties, LR often wins. Even if it's technically a little less accurate than its competitors, it's reliable, it's predictable, and the math is transparently sound.
Before we move on, let's just circle back to that initial distinction you made. You talked about predicting a probability between 0 and 1 versus a simple linear model. So why can't we just use regular linear regression, which is even simpler, to predict that probability? Why did we even need this logistic function in the first place?
That's a great question, a really fundamental one. Simple linear regression works perfectly if the variable you're predicting is unbounded. Things like price or temperature or annual sales.
Things that can go up or down indefinitely.
Right. But probability, by its very definition, is bounded. It's stuck between 0 and 1. If you try to fit a straight line to a probability outcome, especially one driven by predictors that can range widely, you will inevitably predict illogical results.
What do you mean by illogical?
Well, imagine using a straight line to predict loan default probability based on someone's income. For very low income levels, that straight line might project a default probability of, negative 20%.
Which is impossible.
Mathematically impossible. And for very high income levels, it might project a 150% probability of not defaulting. Again, nonsensical.
So you get negative probability or over 100%, just mathematically broken.
Precisely. The core failure of linear regression here is that it assumes a straight line relationship across the entire spectrum of data. What we need is a function that, no matter how extreme the inputs are, will always gracefully curve and sort of level off towards 0 at the low end and 1 at the high end.
The S-curve.
That graceful S-curve. And that is exactly what the logistic function provides. And it's why it is so fundamental to this entire class of modeling.
Now we are moving into the practical phase. Our sources really emphasized Excel minor, and I think that's crucial for our audience, the learner, who might be coming from a business background and needs to get their hands dirty without getting bogged down in programming syntax.
Oh, the role of Excel minor for accessibility, it really can't be overstated. It just removes that initial barrier to entry. Because it's an add-in for Excel, it leverages a platform that millions of people are already comfortable with. It takes all this complex statistical computation fitting that S-curve, the iterative optimization, and it bundles it behind a simple user interface.
So you're not fighting with code libraries.
Exactly. For rapid prototyping, for teaching, for just testing a hypothesis quickly, this is invaluable. You can focus your energy on the science. Did I pick the right variables? Does this result actually make business sense? You're focused on the quality of the model and the data, not on debugging a memory error in a library you just installed. It really accelerates conceptual understanding.
Okay, so it removes the syntax barrier, lets us focus on the data science fundamentals. But whether we're coding in Python or clicking buttons in Excel Miner, model quality still lives or dies on the quality of our inputs. You mentioned earlier that data preparation is mandatory, and that LR is particularly sensitive. This is where the real work begins, isn't it?
It is, and it's often the least glamorous part of the job. Because LR assumes a degree of structural precision in the relationship it models, messy data is a real threat. So we should probably walk through the crucial steps that have to happen before you ever click run.
Let's do it.
First, you need absolute clarity on the binary target variable. This sounds trivial, but in real business data, definitions can be incredibly vague. If you're predicting successful sale, does that mean a customer completed a transaction over $100? Or just any transaction, regardless of the value? If your definition of the outcome, the 0 or the 1, is inconsistent, the model will learn a confused, meaningless pattern.
Garbage in, garbage out.
That's the one. Defining the target is the foundation of the entire predictive exercise.
So if the model is learning from a blurry photograph, it's going to produce a blurry prediction. What's next?
Second, systematically handling missing values and outliers. Missing data can bias your coefficients because the model has to make assumptions, or more often just drop those rows. So if 20% of your low-income customers didn't report their salary, dropping all of them might skew your model to look financially healthier than it really is.
Okay, that makes sense.
Outliers are even more dangerous for LR. Since the model is trying to fit that underlying linear line in the log odd space, one or two extreme outliers, say, a customer with $10 million in debt who still paid on time, can dramatically pull that line and skew the coefficients for everyone else.
Right.
You have to decide, do you remove them? Do you cap their values? Do you transform the variable? In Excel Miner, you'd likely use data transformation features before you even feed the data into the LR module.
So if I'm a business analyst running this model, and I see a customer who makes $20 million, but the average salary in my data is $70,000,
Yeah.
do I just cap that income at, say, $500,000 so it doesn't distort the whole curve?
That's a very common strategy, yes.
Yes.
It's often called winterizing or capping. You're acknowledging that while the extreme value is real, its influence on the model's generalizability is, well, it's toxic. You treat it as an extreme case, but you prevent it from warping the model's understanding of the average customer.
Got it. What's number 3?
Third, and this is absolutely non-negotiable for LR, appropriately encoding categorical variables.
Okay.
LR operates purely on numerical data. If you have customer type, gold, silver, bronze, you have to convert those text categories into a numerical format. The most common technique is using dummy variables or one-hot encoding. You basically turn one variable customer type into 3 new variables, is gold, is silver, and is bronze, where each of those new variables is just a 0 or a 1.
Right, that's the conversion step. You're turning a qualitative description into quantitative flags that the math can actually process. If we skip that, the model would treat gold and silver as if they were just arbitrary numbers that have some kind of quantitative relationship, which they don't.
Precisely. If you coded them as 1, 2, and 3, the model would assume that bronze, 3, is somehow quantitatively 3 times gold, 1, which is just false. Dummy variables solve that hierarchy problem.
Okay, what's the last prep step?
And fourth, this is more about real-world utility. You have to ensure that all your chosen predictors are actually available at the time of prediction.
The practical check.
Yes. It sounds obvious, but it's a common operational failure. If your model uses average account balance over the last 90 days, but your live system only records current balance, well, your beautiful, accurate model is useless for real-time deployment. You have to build your model using only the data streams that are accessible when you need to make that live decision.
That's the operational reality check. A perfect historical model that can't run on current data is just a very sophisticated report.
Exactly. So once that data is all prepared, the final mandatory step before training is the data split. We need a training set, typically 60 to 80% of the data, which is used to build the model and find the best coefficients. And then we need a separate validation or test set, the remaining 20 to 40%.
Why do we always insist on separating the data? Why not use all the data we've so painstakingly prepared? It kind of feels like you're throwing away valuable information.
We split the data to mimic real-world performance validation. If you only test the model on the data it was trained on, it's going to look flawless, inevitably, because it has essentially memorized the relationship between those specific inputs and those specific outcomes.
An open book test.
It's an open book test. It's learn the noise right alongside the signal. The validation set, which contains data the model has never seen before, is the true performance litmus test. It checks for generalization. If your model performs with 95% accuracy on the training set, but only 60% on the validation set, you have a huge problem. It's called severe overfitting. You've created the statistical equivalent of a student who memorized the textbook, got an A on the practice test, but then fundamentally failed to understand the concepts needed for the final exam.
And it won't generalize. It won't work in the real world on new customers.
It will not generalize robustly when exposed to new observations out in the wild.
Okay, so we've cleaned and we split our data. Now we're entering the engine room, the mathematical core of logistic regression. We've established that we need the S-curve of the logistic function to keep the results between 0 and 1. But to get there, we first have to go through this thing called log odds. That sounds like a mathematical detour. Why can't we just jump straight to the probability?
The term log odds is the ingenious mathematical trick that makes LR work. As we said, probability, P of y, is bounded. But standard, efficient, powerful algebra, your linear equations, operates best on unbounded numbers, numbers that can range from negative infinity to positive infinity.
Okay.
The model's goal is to find a simple linear relationship between the predictors, age, income, whatever, and the outcome. To do that, we have to mathematically transform the bounded probability into an unbounded measure. That unbounded measure is the log odds.
Let's break that down, starting with the odds itself. You defined it as the ratio of success probability to failure probability.
Correct. Odds are just the measure of success versus failure. So if an event has a 90% chance of success, so P equals 0.9, the odds are 0.9 divided by 0.1, which is 9.
9 to 1.
Right. It means you're 9 times more likely to succeed than to fail. If the chance is 50-50, P is 0.5, the odds are 1. Odds range from 0 to infinity.
0 to infinity is still only half a number line, so that's where the log comes in, right? To give us the full negative infinity to positive infinity range.
Precisely. By taking the logarithm of the odds, usually the natural log, then we achieve two critical things. First, we stretch that measure across the entire number line. An odds ratio of 1, your 50-50 chance, becomes 0 in the log odds space.
Yeah.
Odds less than 1, so a higher chance of failure, become negative numbers. Odds greater than 1 become positive.
And the second thing?
Second, and this is the most important part, this transformation allows us to use simple linear algebra. The linear combination of the predictor variables, the inputs multiplied by their weights, just like in linear regression, now equals the log odds.
So it's a simple formula again.
It's a simple formula. Log odds equals beta 0 plus beta 1 times x1 plus beta 2 times x2, and so on. This is the conceptual breakthrough. The relationship between the predictors and the final probability outcome is fundamentally nonlinear. That's the S-curve. But the underlying engine, the equation that combines your financial history and demographics, is perfectly linear in its parameters. It's a straight line in that mathematical log odds workspace.
That's a brilliant insight. It's like the model has found a secret linear dimension where this complex, messy probability problem just simplifies into basic addition and multiplication.
That's a great way to put it. That's exactly it. And once the model has found the perfect linear combination, the set of coefficients that best predict those log odds, we need the final step, translating that result back into human interpretable probability.
And that is the function of the S-curve itself, the logistic function. How does that final bridge work?
The logistic function is simply the inverse transformation. It takes that unbounded linear output, the log odds, which could be anything from -10 to +10, and it smoothly maps it back onto the 0 to 1 probability range. If the linear output, the log odds score, is highly negative, the logistic function converts that to a probability very close to 0. If the score is highly positive, it converts it to a probability close to 1.
And if it's 0?
If the score is exactly 0, it converts it precisely to 0.5. It ensures that the result is always a legitimate probability score, reflecting the confidence the model has in predicting the positive outcome. It's the crucial bridge between simple algebra and complex probability modeling.
Okay, we've established the why and the how the model calculates its score. Now let's look at the final product. We've used Excel Miner, we've selected our variables, chosen our training set, and we hit the run button. The output table, which is usually clean and structured, pops up. What are the key elements we need to focus on to turn these numbers into actual actionable decisions?
Right, the output sheet is where the rubber meets the road. An analyst needs to focus on 3 essential components: the coefficients, the odds ratios, and the statistical significance, which is represented by p-values. Right. Let's start with the coefficients, as we just discussed. These are the weights, the betas, that the model has assigned to each predictor variable. They are the currency of that log odds space.
Okay.
They indicate the direction and the strength of the influence that predictor has on the outcome.
Let's use a concrete example here. Say we're predicting the probability of a high-risk event, like an insurance claim. What would a positive versus a negative coefficient tell us about input variables like age or number of prior claims?
Good example. If number of prior claims has a large positive coefficient, it means that as the count of prior claims increases, the log odds of the positive class, a new high-risk claim, also increase substantially. A positive coefficient is a factor that pushes the probability towards 1.
It increases the risk?
It increases the risk. Conversely, if age has a negative coefficient, it means that as the subject's age increases, the log odds of a claim decrease. A negative coefficient is a factor that dampens the probability. And the absolute size of that coefficient tells you the strength of the push or pull. A coefficient of 0.5 has less influence than one of 2.0.
That makes the direction clear, but the raw coefficient number itself, like a 1-unit increase in X, increases the log odds by 1.2. That's still pretty abstract for a business decision maker. And that's why we need to move to the odds ratios, which are often automatically calculated right next to the coefficients in tools like Excel Miner.
Absolutely. The odds ratios are the essential interpretation bridge. They take that abstract log odds coefficient and transform it back into something intuitively understandable. They're just the exponentiated coefficients. And what the odds ratio represents is the multiplicative change in the odds associated with a 1-unit increase in that specific predictor, assuming all other variables stay constant.
Okay, let's take that perfect example from our source material again. If number of previous successful purchases has an odds ratio of 1.5, how does a marketing VP interpret that?
They interpret it as a quantifiable leverage point. An odds ratio of 1.5 means that for every additional successful purchase a customer has made, the odds of them responding positively to the current marketing campaign increase by 50%.
50%. 1.5 minus 1.
Exactly. If the odds ratio is 2.0, the odds would double. If it was 0.8, the odds would decrease by 20%. And this is immensely valuable because it quantifies the impact of changes in your inputs. If you can, through some policy or intervention, increase a key predictor by 1 unit, the model tells you exactly how much better your chances are. That ability to quantify the ROI of a policy change is why LR is so durable in business. It allows for straightforward, calculable, if-then scenario planning.
That is the true aha moment. It's not just a descriptive model, it's an optimization tool.
Precisely. Now let's bring in the final piece of this puzzle for this section, statistical significance, which is usually reported via p-values.
So how do p-values help us distinguish between a coefficient that's a true strong signal and one that's just, random statistical noise?
The p-value answers a very specific question. It asks, if this predictor variable truly had no effect on the outcome, so if its true coefficient was 0, how likely would we be to see a coefficient as large as the one we did, just by pure chance?
I see.
If the p-value is very low, typically we use a threshold of less than 0.05, it means the variable is highly unlikely to have a 0 effect. So, we conclude it is a statistically significant, meaningful contributor to the prediction. In your Excel Miner output, you'd immediately look for that p-value column, and you'd probably discard any variables whose p-value is above your threshold.
This sounds critical for building a lean, understandable model. If we have 50 predictors but only 12 are statistically significant, we should simplify the model down to those 12.
Absolutely. A model with fewer, highly influential, and significant predictors is more robust and much less likely to overfit. It's also easier to deploy and to maintain. But there's a quick but important caveat here related to the coefficients. We mentioned sensitivity to multicollinearity earlier.
Right, when predictors are too similar.
Yes. If you see the two predictor variables are, say, 95% correlated, like a customer's total balance and their maximum credit limit, the model will struggle to independently assign weight to them. This can lead to coefficients that are statistically significant but wildly inflated or even inverted, making them unstable and nonsensical to interpret. An experienced analyst would use a measure like the variance inflation factor, or VIF, to spot and remove those highly correlated variables before trusting the coefficients.
So even if the p-value is low, if the VIF is high, the model is essentially screaming, I can't tell these two variables apart, and you need to intervene. The transparency of LR demands that level of data hygiene.
It really does.
Building the model is one step. But validating its performance, ensuring it works reliably on that unseen data, is the crucial second step. So how do we, using the suite of diagnostics provided by a tool like Excel Miner, determine if our logistic regression is actually, yeah, fit for purpose?
We use a blend of technical and business-focused diagnostic measures. These diagnostics support key activities: deciding if LR is performing acceptably, comparing it to other models, and most importantly, optimizing the classification threshold. The outputs include some technical likelihood-based statistics, which tell us how well the model fits the training data compared to a null model, a model with no predictors. But for real-world impact, we look to the metrics that come from the confusion matrix. This matrix is fundamental.
Okay.
It breaks down all the predictions on your validation set into 4 simple categories. True positives, where you correctly predicted yes.
Yeah.
True negatives, where you correctly predicted no.
And then the mistakes.
And then the mistakes.
Yeah.
False positives, where you predicted yes, but the reality was no. False negatives, where you predicted no, but the reality was yes.
And that mapping of reality versus prediction, that forms the basis of all our performance measures. But before we get into those, let's just confirm the validation step again. We have to test on the unseen data. How does a tool like Excel Miner help guarantee this rigor?
Excel Miner supports 2 primary validation techniques. The standard one is holdout validation. That's the 70-30 or 60-40 split we talked about. The model coefficients are locked in using the training set, and performance is solely measured on that holdout set.
Okay.
The more rigorous method is cross-validation. Here, the entire data set is divided into, say, 10 equal folds. The model is then trained 10 separate times, each time leaving a different fold out for testing. This process generates 10 different performance metrics, which you then average. This dramatically reduces the chance that your high performance was just a fluke because you got a lucky or an atypical split of the data.
That makes the performance score much more reliable. So now let's go back to those metrics from the matrix. Accuracy is the overall correct rate, but why do we care so much about sensitivity and specificity?
They force us to consider the type of error we're making. Sensitivity, which is also called the true positive rate, is the model's ability to catch the positive outcome when it actually occurs.
Okay.
If we're predicting customer churn, high sensitivity means we're successfully catching a large percentage of the customers who are truly about to leave. High sensitivity means a low rate of false negatives, of missing the event.
Got it. And specificity.
Specificity, or the true negative rate, is the model's ability to correctly identify the negative outcome. It measures how well we identify the customers who are definitely staying. High specificity means a low rate of false positives, incorrectly tagging a loyal customer as a churn risk.
So we're constantly in this tug of war, balancing the ability to catch the signal, which is sensitivity, against the ability to ignore the noise, which is specificity.
Exactly. And the trade-off between those two is directly controlled by the classification threshold. This is the moment of truth. Taking the model's output probability like 0.72 and converting it into a definitive binary label, yes or no. The mathematical default is often 0.5.
But the sources we read make it really clear that treating 0.5 as sacred is a major mistake. The choice of threshold has to be guided by business costs and risk. This is where the math stops and the strategy begins.
This is arguably the most critical decision in deploying a model. You have to compare the real-world financial or maybe reputational cost of a false negative against the cost of a false positive. The threshold isn't a mathematical input, it's a policy lever.
Give us an example.
Let's consider the classic medical diagnosis scenario again.
Cool.
We're predicting a severe but rare condition. A false positive telling a healthy patient they might be sick costs the system money for follow-up testing, and it causes the patient anxiety. That's a cost. But a false negative missing an actually sick patient could lead to catastrophic health outcomes, severe liability, massive cost down the line. If the cost of that false negative is 10 times the cost of the false positive, you must dramatically lower your threshold, maybe down to 0.25. By doing this, you're explicitly accepting more false positives, so you sacrifice some specificity because you are prioritizing maximizing sensitivity. You want to catch every possible case, even at the risk of some false alarms.
Conversely, if you were screening for something trivial like sending out a coupon, a false negative, so missing a potential coupon user, is cheap. But a false positive, sending a coupon to someone who would never use it and wasting resources, is wasteful. In that case, you might raise the threshold to 0.75. You'd want to make sure you're only targeting the absolute most likely users.
Precisely. You are aligning the model's behavior with the organization's risk tolerance and its budget. The data scientist has to communicate this trade-off clearly to the business stakeholders so they can set the optimal operating point. Finally, we should just touch on lift and gain charts, which Excel Miner generates. These charts visualize the performance of the model compared to just a random guess.
Okay.
A lift chart might show, for example, that if you target the top 10% of customers ranked by the model's probability score, you capture 50% of all the churners. This metric is indispensable for direct marketing campaigns or collection agencies, where resources are limited and you really need to prioritize whom to contact.
So lift charts tell you the efficiency of your targeting. They prove the model isn't just accurate overall, but that it's effective at finding the needle in the haystack.
Well said.
We've gone from the fundamentals to the engine, and now to validation. Let's make this really concrete by reviewing the real-world use cases that were provided in our sources. Where is logistic regression actually being deployed today, making critical decisions?
Well, LR is foundational across several key industries, and it's specifically because of its reliability and its interpretability. First, customer churn prediction. This is just ubiquitous. LR identifies the key factors, whether it's contract duration, interaction frequency, changes in usage patterns, that are driving the probability of a customer leaving.
Right.
Second, credit approval and risk scoring. This is the classic application where interpretability is legally mandated. LR provides a transparent score and crucially auditable reasons for acceptance or rejection, linking back directly to those coefficients we talked about.
Makes sense.
Third, medical diagnosis and public health. Predicting the probability of a condition or assessing the risk factors for disease spread. Because LR is transparent, doctors and public health officials can better understand the primary drivers behind a prediction.
And fourth, marketing response modeling. This links directly to those powerful odds ratios we discussed. Will the customer click the ad? Will they respond to the promotion? The LR model clearly quantifies the leverage of each variable, allowing marketing teams to optimize their spending by focusing only on the factors that drive the highest odds of success.
And finally, just general risk assessment, whether that's financial, operational, actuarial, really any scenario where a clear, probabilistic assessment of binary risk is required and where the explanation is just as important as the answer itself.
That is a powerful list. It really demonstrates LR's continued relevance. So let's just summarize those advantages we've discussed. Why should the learner keep LR in their toolbox even as all these new techniques emerge?
Its popularity endures because of its core strengths. It's easy to use, it's highly transparent, and it's uniquely interpretable, especially through those odds ratios, which are very simple for business users to grasp. It also has a strong, well-understood theoretical basis, which makes it reliable in compliance-heavy fields. It's simply the best option when the explanation is prioritized over marginal increases in accuracy.
But every model is a compromise. We have to provide the necessary balance. Where does the logistic regression model start to break down, and when should the learner pivot to a different technique?
This is critical for responsible modeling. The primary limitation really stems from its greatest advantage, its structural simplicity. The linearity assumption can be its downfall. Remember, LR assumes a linear relationship between the predictors and the log odds. If the true underlying decision boundary in your data is complex and highly nonlinear, LR is going to fail. Imagine your data points for yes and no aren't separated by a straight line, but by a circle or a parabola. LR cannot draw a circle. It can only draw a straight line. It will desperately try to fit that line, leading to low accuracy and coefficients that are just misleading.
So if the data requires a complex curving boundary to separate the outcomes, LR is simply the wrong tool for the job. You need a tree-based model or maybe a support vector machine with a nonlinear kernel.
Precisely. Its performance may be inferior to those nonlinear methods when you're dealing with complex data that has intricate interactions between variables. And furthermore, we have to reiterate its sensitivity to data imperfections. We talked about it earlier, but it's worth dwelling on the two major structural vulnerabilities. First, multicollinearity. If two predictors are too highly correlated, LR's coefficient calculation becomes unstable. The model doesn't know whether to assign the weight to variable A or variable B, so it often assigns these ridiculously large weights to both, which then nearly cancel each other out in the overall calculation. This makes the individual odds ratios meaningless and the model unpredictable.
And if an analyst sees these wildly large coefficients, some positive, some negative, on variables that seem conceptually linked, that's the red flag for multicollinearity.
Absolutely. The mitigation is often simple. You remove one of the correlated variables or you combine them into a single composite feature. And second, its reliance on that underlying linear structure means it requires thoughtful feature engineering. You can't just dump raw, unscaled data into LR and expect a fantastic result.
Mm.
Variables might need scaling or transforming log or square root transformations, maybe, or combining before that linearity assumption holds true in the log odds space.
So there's an art to it.
There is. The quality of your pre-processing really dictates the quality of your LR output, which is a significant practical limitation compared to models like random forests, which often handle raw input data with a lot less fuss.
That brings us to the end of a deep dive that took us right to the heart of decision-making in data science. We cut through the noise to understand the fundamental purpose of logistic regression for binary outcomes, estimating that essential probability score.
We saw how a tool like Excel Miner can facilitate non-coding analysis for the business user and really accelerate learning. We decoded the output, recognizing that coefficients show the direction, and the odds ratios provide that crucial interpretable measure of multiplicative change.
And most critically, we understood the vital role of the classification threshold. We realized that converting a probability into a high-stakes decision is a policy choice. It's guided by business costs and risk tolerance, not just pure mathematics.
This model is powerful, transparent, and it often serves as the bedrock of predictive analytics all over the world. But before we sign off, let's leave our listener with one final provocative thought that ties everything together. Given that logistic regression is highly transparent, which is its greatest strength, but at the same time, it's simultaneously sensitive to data imperfections like multicollinearity and outliers. Consider this question. How much trust should you place in a model's elegant, transparent prediction if you didn't perform a thorough, rigorous job in the data preparation phase? The mathematical precision of the model is entirely contingent upon the messy, human decisions made during feature engineering and cleaning. The real deep dive often happens long before the model even runs. That is where true predictive power is ultimately built or broken.
Welcome back to the deep dive. Today, we are taking a massive leap forward in the analytical world.
A big one.
We're moving beyond just describing what happened, descriptive statistics, and diving headfirst into some truly exciting and I think challenging territory, predictive modeling. We're talking about moving from historical reports to using the enduring ghost of patterns past to forecast or at least highly inform the future.
That's our core mission for you today. I mean, if you are a manager trying to interpret what the data science team is doing or an analyst just learning how to structure your projects,
right,
you absolutely need to understand the indispensable, critical workflow required to build a reliable predictive model. This deep dive is all about that structure, the rigor that bridges, theoretical data science and those essential high-stakes business decisions.
And to guide us through this pretty intricate landscape, we are focusing on a tool that intentionally tries to democratize this whole process, Excel Miner. Now, we aren't talking about writing custom Python scripts or deploying vast cloud infrastructure here. Excel Miner is a proven, robust analytics and data mining tool that lives right inside Microsoft Excel.
And what's so fascinating here, I think, is that this specific choice of tool emphasizes a really crucial point.
What's that?
That analytical rigor doesn't have to be walled off by programming knowledge. Excel Miner is, it's purpose-built to provide a guided, user-friendly environment that basically forces you into good habits.
It forces the workflow.
Exactly. The workflow, which is what matters most at the end of the day.
Exactly. So why does this matter to you, the learner? Because this platform is, honestly, it's absolutely perfect for the business analyst, the marketing manager, or the curious student.
For sure.
It's designed for rapid prototyping and deployment, which lets you focus 100% on the analytical thinking, the structured process, and the managerial interpretation rather than, debugging code or wrestling with syntax. It just levels the playing field.
And if we connect this to the bigger picture, the fundamental purpose of this entire exercise is actually pretty simple.
Go.
We're learning patterns from historical data to predict future outcomes. But the application of that simple idea is just incredibly broad. It touches nearly every aspect of modern business operations, from finance to marketing to logistics.
And these models, they provide 4 critical support functions, which really define the scope of their usefulness.
Right.
You're talking about classification, which is that binary question. Is this email spam or not spam? Is this applicant a defaulter or not a defaulter?
Yes or no.
Then there's prediction, which deals with continuous values, like what specific dollar amount will this customer spend next quarter, or what will the temperature be tomorrow?
Beyond those basics, models handle ranking, which is I mean, it's essential in direct marketing. You might have 10,000 potential customers, but you only have a budget for 1,000 mailers.
So you need to know who to target first.
Exactly. The model ranks them by their probability of responding, ensuring you get the highest possible return on your investment.
And finally, these all feed into decision-making. Should we increase the credit limit for this account? Should we approve this specific loan application?
The model provides the data, that probability,
Mm-hmm.
that allows a human or an automated system to make that final binding decision.
This raises a really important question that is, I think, absolutely crucial to grasp before we get into the mechanics.
It is. The true crucial insight here is the difference between simply fitting historical data and what we're actually aiming for,
Which is,
out of sample performance.
and this is where so many aspiring analysts stumble. I mean, they build a model, they look at its performance on the data they use to train it, and they see this brilliant accuracy score, 98%. They think they've won the lottery.
Right. You can build a model that explains 99.9% of your past data perfectly.
It's just memorized it.
It has. It's a model that has essentially memorized the historical data points.
Hmm.
But if that model falls apart the second you feed it new, previously unseen data, it is worse than useless. It's actively misleading.
So the core focus, the constant North Star, must always be on how well the model works on data it hasn't seen. That's the real, unbiased test of its predictive power and its ability to generalize to the real world.
Mm-hmm.
If it can't generalize, you haven't built a predictor. You've built an audio recording of the past.
It's a great way to put it.
And that notion of generalization is what informs every single step of the XLMiner workflow we're about to unpack.
Okay, so let's unpack this structured process. If we're going to achieve reliable, robust, out-of-sample performance, we can't just throw data at an algorithm and, hope for a statistically significant result.
Yeah.
We need a methodology.
That's the core realization. XLMiner facilitates this structured 6-step process because it understands that even within a user-friendly environment, shortcuts in methodology lead to fundamentally flawed results. This structure is the safety net. It ensures rigor. So let's lay out this essential workflow, like a roadmap for our conversation.
Okay, the process starts with the high-level strategy and flows right down to the final interpretation. Step 1, define the analytical objective.
What are we actually trying to solve?
Exactly. What specific business question are you solving? Step 2, prepare and explore the data. This is the often gritty groundwork that determines model quality.
The unglamorous part.
Very. Step 3, select the modeling technique, choosing the right algorithmic language for the problem. Step 4, train the model, the actual estimation and optimization process.
And then?
Step 5, validate and assess performance, the critical check to ensure generalization, not memorization. And finally, step 6, compare alternative models, because the best model might not be the one you expected at the start.
That roadmap is excellent, and it immediately highlights why steps 1 and 2, defining the objective and preparing the data, are so vital. We hear that mantra constantly in the data world, garbage in, garbage out.
All the time.
But what does garbage actually look like in practice?
It looks like wasted effort and misleading predictions. And we have to stress this foundational truth. Poor data preparation leads to unreliable models, regardless of the method you choose.
Right. It doesn't matter how fancy the algorithm is.
Not at all. You could use the most sophisticated, large-scale neural network architecture. But if the data is messy, biased, or incomplete, the model will be fundamentally flawed. It won't be generalizable.
And here's where it gets really important, because data prep isn't just about spotting typos. It's a detailed, multi-layered process that requires real analytical thought.
It does.
So let's break down the essential preparation steps XLMiner guides you through. First up, you have to identify the target or output variable.
And this requires precision. You need to know, are you predicting a continuous number, say the next stock price, or are you predicting a categorical outcome, like whether a machine will fail in the next 30 days?
And that choice dictates everything that follows.
It dictates which family of models you can even use. Regression versus classification. If you misidentify the target variable, the entire project is instantly misaligned. It's dead on arrival.
So once the target is set, then comes the selection of relevant predictors. These are the input variables. And with the sheer volume of data available today, analysts often start with hundreds, maybe thousands of potential columns.
And very often, 90% of those columns are irrelevant or redundant or even harmful to the model.
Harmful? How?
They just add noise. The analyst must use domain knowledge and statistical exploration to whittle down that list. Are we using age, income, purchase history, website click-through rate. If a variable is only weakly correlated with the target, including it just adds complexity and noise, which increases the risk of overfitting.
Okay, that makes sense.
Right.
Then we have to handle the unavoidable, messy issue of missing values.
Right. Data is rarely pristine, particularly in large corporate databases.
So what do you do?
Well, Excel Miner provides built-in ways to address this, and the choice of technique is critical. Should you just delete the rows with missing data?
That sounds simple enough.
It's simple, but you lose potentially valuable information. Or should you use imputation? Imputation, like replacing the missing value with the mean or median of that column, is quick, but it artificially reduces the variance in your data.
So it makes your data look less spread out than it really is.
Exactly. More sophisticated techniques might involve building a separate model just to predict the missing values, recognizing that how you handle those gaps has a profound impact on the final model's stability.
Now, a critical step that often trips up beginners, especially those coming from simple Excel analysis to modeling, is the need for encoding categorical variables.
Oh, this is a big one.
If you have a column labeled region with values like north, south, east, and west, a mathematical algorithm can't process those text labels.
Right. I mean, if you try to feed text directly, the model just breaks. So we use encoding to translate those labels into numerical inputs. The most common technique is called one-hot encoding.
So how does that work?
Basically, the region column is replaced by 3 or 4 new binary columns. So you'd have, for example, is north, I south, I's east. If a row has a 1 in the I's north column, it represents the north region.
Ah, I see. And this prevents the model from assuming some kind of arbitrary numerical order.
Precisely. It prevents the model from thinking that west, which might be assigned a 4, is somehow mathematically greater than east, assigned a 3. Skipping this step, or encoding incorrectly, introduces mathematical bias based purely on the alphabetical order of the labels. It can skew the entire analysis.
And finally, data preparation involves detecting and managing outliers. These are the data points that sit way outside the standard expected distribution.
Outliers are dangerous because they wield undue leverage. Think of building a model to predict the average duration of customer support calls. If 99.9% of calls average 4 minutes, but one call was an administrative error that lasted 8 hours.
Oh, wow.
That single 8-hour outlier can drag the entire central tendency of your model away from what is true for the vast majority of your data. Excel Miner helps you visualize these points. Identifying them and deciding whether to mitigate them by transforming the data or capping the extreme values ensures the model learns the predictable trend, not the statistical anomaly.
That preparation stage is intense. But even once the data is perfectly clean, we still face the single largest problem in predictive modeling, ensuring the model will generalize.
Right.
This brings us to a concept that is absolutely non-negotiable for reliable modeling: data partitioning.
This is the essential firewall. Partitioning means separating our clean dataset into distinct, non-overlapping groups. Excel Miner supports the industry standard of 3 sets, and understanding their individual roles is essential to avoid, well, analytical malpractice.
Let's define them clearly and their typical weighting. First, the largest set, usually 60 or 70% of the data, is the training set.
This is the classroom. The training set is used for model estimation. This is the data used to teach the model the patterns, to calculate the specific coefficients in a regression, or determine the optimal decision split points in a tree, or tune the weights in a neural network. It's where all the initial learning happens.
Okay, that makes sense. Second, we have the crucial intermediate set, typically 15 to 20% of the data, the validation set.
The validation set is the internal testing ground, the weekly quiz.
I like that analogy.
It's used constantly for model tuning. As we develop the model, say, we try to decide if a classification tree should be pruned back to 10 nodes or allowed to grow to 50. We check its performance against the validation set. This set allows us to refine the model's complexity and parameters during development, ensuring we don't just optimize for the training data.
So it guides the internal development process.
Exactly.
And third, the most guarded set, often another 15 to 20%, is the test set.
The test set is the final objective grade. It must be reserved solely for the final, unbiased evaluation. It is the data the model never sees during training or tuning. When we claim, post-development, that a model has 85% accuracy,
that claim has to come from the test set.
It must come from the performance on the test set. If you use the test set prematurely, your entire performance metric is inflated and useless in the real world.
I have to ask, as the host guiding our learner here, Why go through all this trouble? I mean, why not just use the validation set as the final test? What are we fundamentally protecting ourselves from?
We are protecting against two major analytical pitfalls that destroy generalization. The first one is overfitting.
Overfitting is a great concept to visualize. We often think of it as memorization versus actual learning.
Precisely. Imagine a student is given a list of 100 math problems and memorizes the answer to every single one. That student achieves 100% on the training exam. But if you give them a new problem that requires applying the underlying rules, the pattern, they fail completely.
Because they didn't learn the concept.
They didn't. They learned the noise and the idiosyncrasies of the specific training data, not the fundamental predictive relationship. A model that is overfit will have near-perfect performance on the training set, good performance on the validation set,
And then it falls off a cliff.
catastrophic failure on the test set. Partitioning prevents the model from learning the noise of the data.
And partitioning protects against the second issue, which is much more subtle and often happens by accident: information leakage.
Yes, information leakage occurs when information from the validation or test sets inadvertently influences the training phase. For example, if you decide to exclude certain predictors after reviewing the performance of your initial test set results.
You've peeked at the answers.
You've peaked. You've allowed the test set data to influence your feature selection. You are essentially giving the model a peek at the final exam answers, even if it's indirectly. This leads to an artificially inflated performance metric that will collapse the minute you put the model into production with truly new data.
So partitioning is the firewall.
It is the firewall. It maintains the sanctity of that final test set grade.
With our data clean, encoded, outliers managed, and most importantly, properly partitioned, we arrive at step 3, selecting the right tool. This is where the mathematical engine comes in. Excel Miner, despite being user-friendly, gives us access to a wide array of powerful techniques.
And this variety is critical because the mathematical approach you use must perfectly align with the target variable and the business goals you're solving.
You wouldn't use a bulldozer to plant a garden. Excel Miner supports foundational models like logistic regression for classification and linear regression for continuous prediction, which are highly interpretable, great baselines. But it also includes nonlinear techniques, which are vital for complex patterns, classification trees, the versatile k-nearest neighbors, and even sophisticated methods like neural networks.
And when we talk about neural networks, for the learner who isn't, coding them from scratch, the conceptual difference is really key.
Okay.
Unlike a linear model, which fits a straight line or a plane, a neural network uses interconnected layers of mathematical functions to capture highly complex nonlinear relationships in the data. They're designed to model patterns that are just too intertwined for a simple regression to ever spot.
That variety allows the analyst to tackle so many different types of problems, but the choice is never arbitrary, is it? It's always driven by 3 major factors that define the project requirements.
Always. First is the nature of the target variable, which we already established.
Right. Categorical targets demand classification. Continuous targets demand regression.
Simple alignment. Second, you have business requirements. If you are designing a high-frequency trading algorithm or a real-time website personalization tool, speed and scalability are paramount.
So in those cases,
A streamlined linear model might actually be superior to a massive, computationally expensive neural network, even if the latter is marginally more accurate.
And the third factor is arguably the most important for managerial and audit contexts: interpretability needs.
This is the constant trade-off in predictive modeling.
It really is. A complex neural network might achieve 95% accuracy, but when you ask why it denied a loan application, the answer is just the weighted result of 50,000 internal mathematical nodes.
It's a black box.
A total black box.
And if your business requires you to legally or ethically justify every single decision, say demonstrating fair lending practices or complying with consumer privacy regulations, you must choose a simpler, often slightly less accurate model.
Like a regression or a classification tree.
Exactly, because they are inherently transparent. You can point to the exact coefficients or decision splits and say, the model decided this because the applicant's debt-to-income ratio exceeded 40%.
Right.
In high-stakes environments, interpretability often wins over marginal accuracy every single time.
Moving into step 4, we enter the core execution phase, model training in Excel Miner. This is where the chosen algorithm actually does its work using the training set.
Right. Training is the process of using that training set to iteratively estimate and refine the model's parameters. If we're building a regression, we're estimating the coefficients that minimize the error. If we're building a neural network,
You're adjusting all those connection weights.
exactly, you're adjusting the connection weights across all those layers to find the optimal arrangement that minimizes the predictive error.
Excel Miner makes this incredibly straightforward because it automates the highly complex mathematical optimization.
It does. For the learner, you don't need to understand the mechanics of, say, gradient descent, the iterative process used to find that minimum error value. Excel Miner handles the complex mathematics of parameter estimation. It provides built-in defaults that are suitable for beginners, allowing someone who understands the workflow to quickly generate a working model.
But it's not just for beginners.
Not at all.
Yeah.
Critically, it also offers advanced settings, like specifying the number of neighbors in k-nearest neighbors, or the learning rate in a neural network for experienced users who need that fine-tuning.
So the underlying goal of providing these structured automated features is ensuring consistency and repeatability in model estimation.
Yes, that's crucial. If you run the training phase again, you need to be confident you can recreate the same model parameters. It's absolutely crucial for auditing, for deployment, and for ensuring stability in production environments.
And that consistency leads us directly into step 5, validation. This is the moment of truth. We have to assess how well the model generalizes outside of that training environment using the held-out validation set. Excel Miner provides a whole suite of evaluation tools designed to give a comprehensive picture of performance, not just a single, often misleading, overall accuracy number.
And we start with the fundamental diagnostic tool for classification, the confusion matrix.
The confusion matrix?
It's the foundational report card. It's a simple table that summarizes the model's performance on the validation or test set by classifying every single prediction. It breaks down the results into 4 key counts.
Let's hear them.
First, true positives, TP, correctly predicting yes. Second, true negatives, TN, correctly predicting no. Third, false positives, FP, predicting yes when the actual outcome was no. That's a type I error.
And fourth,
false negatives, FN, predicting no when the actual outcome was yes. That's a type 2 error.
from this matrix, we calculate overall accuracy, but that's rarely the most useful metric, is it? Much more critical are the derived metrics that speak directly to business risk, like sensitivity and specificity.
Absolutely. Sensitivity is the true positive rate, how good the model is at catching the events you want it to catch. If you're building a model to predict critical equipment failure, high sensitivity is paramount.
You want to catch every machine that's about to fail.
You want to ensure the machine that will fail is predicted to fail.
And specificity, conversely, is the true negative rate. How good it is at correctly identifying the non-events.
Right. In the equipment failure example, this is correctly predicting that the healthy machine will not fail.
So the importance of balancing these two depends entirely on the business context.
Entirely. Consider a system designed to flag potential insider trading. High sensitivity means you catch all the true instances of trading, but it might mean a lot of false positives flagging legitimate transactions and irritating your employees.
Whereas high specificity.
High specificity means very few false alarms, but potentially missing a catastrophic true positive.
Let's use another example to really hammer this home. Spam filtering versus a medical diagnostic test for a serious disease.
Perfect contrast.
For a spam filter, high specificity is often what you want. You want to ensure you don't falsely classify an important email as spam. That's a false positive. The cost of a few missed spam emails, the false negatives, is pretty low.
But for a potentially lethal disease, the priority flips entirely. You want extremely high sensitivity. You would rather endure several false positives, telling a healthy person they might be sick, requiring follow-up testing, than accept a single false negative.
Missing a truly sick person.
Exactly. The business objective minimizing cost, or minimizing human risk, dictates which metric you prioritize.
Excel Miner takes this a step further by providing visualization tools like lift and gain charts. For the manager who doesn't live in the confusion matrix, these charts are essential. They translate statistical performance directly into return on investment.
They do. A lift chart shows how much better your model is at identifying target customers compared to a purely random selection.
Can you give a concrete definition for the listener?
Sure. If your model provides a lift of 3x in the top decile of predicted buyers, it means that by targeting the 10% of customers your model ranks highest, you will capture 3 times the number of buyers you would expect if you just targeted any random 10% of customers.
That is actionable insight. That tells the marketing team, instead of sending out 10,000 costly mailers, send 1,000 to this high-lift segment and get the same or better return.
Precisely. The takeaway here is that validation metrics have to align perfectly with business objectives, not just abstract mathematical excellence.
That necessity to align technical performance with business costs and strategy brings us to the final, crucial steps in the workflow: comparison and interpretation.
Right. Step 6 is acknowledging the reality that analysts rarely stop at one model.
You don't just build one and call it a day.
Almost never. You might run a logistic regression, a classification tree, and a neural network, all on the exact same partitioned dataset. Comparison is absolutely essential to finding the right fit for deployment.
And we compare them side by side, again using those 3 major criteria, but with a refined managerial perspective. First, naturally, is predictive accuracy on the test set. Which model has the best overall performance?
Second is stability. Does the model give consistent results when you run it multiple times, or if you make small changes to the input data?
Or slightly change the data partitioning?
Exactly. A model that performs brilliantly one day but poorly the next, or one that changes its key predictor variables dramatically based on minor changes, is highly unstable. That instability is a clear indicator of subtle overfitting or reliance on statistical noise.
Which makes it dangerous to deploy.
Very dangerous. And third, back to that critical business priority, interpretability. Can the business team easily understand, trust, and audit the mechanics of the model?
And here's the key takeaway for the listener.
The best model is not always the most complex one. The analysts who succeed in business are those who understand that an interpretable model with 92% accuracy that the business can trust and defend is vastly superior to a black box model with 94% accuracy that management won't deploy.
Because they can't explain its decisions to stakeholders or regulators.
Right.
This successful comparison feeds directly into the final and most crucial analytical phase: interpreting model results. This is the transition where we move from math coefficients to business strategy.
Yes. When the math is done, interpretation focuses on translating the model structure into understandable insights. We identify the key predictors. Was income the primary driver for predicting customer lifetime value, or was it the frequency of website visits?
We also look closely at the direction of influence. Does an increase in factor X increase or decrease the predicted outcome? For example, in a credit model, does higher credit card debt increase the probability of loan default?
As you would expect.
Right. And by how much? And then we look at the relative importance of variables. Which factor is the single most powerful driver?
This transparency is vital. Excel minor outputs are deliberately designed to be transparent for non-technical users. They provide summarized coefficient tables and visual charts that clearly show variable importance.
Which allows managers to act on the model's insights.
Yes, like realizing their current ad campaign targets the wrong demographic, not just blindly apply the model's final output number.
Knowing the why allows for proactive strategic adjustments. It turns a prediction engine into a strategic asset. Before we wrap up the workflow, there's one deep, fascinating point that really illustrates the profound link between modeling and business strategy:
What's that?
the critical role of threshold selection.
Ah, yes. This only applies to classification models. Remember, the model outputs a probability, say a 75% chance of fraud. We then have to convert that probability into a concrete class label, fraud or not fraud.
And that decision point is the classification threshold.
It is.
So if the model predicts a 51% probability of default, and our default threshold is set at 50%, the application is rejected.
But if you raise the threshold to 60%, that same application is approved. That one adjustable decision point changes the real-world outcome.
And that threshold choice directly affects the business trade-off between false positives and false negatives.
It does. The mathematical accuracy of the underlying probability distribution is fixed by the training process, but the operational decision boundary is entirely flexible based on cost.
Let's revisit the example of fraud detection. If we set a very low threshold, say 10% probability, we maximize our chances of catching fraud. We get high sensitivity.
But you'll also generate massive numbers of false positives, blocking legitimate customer transactions, which creates customer friction and high operational costs for investigation.
Conversely, if we set the threshold very high, say 90% probability, we minimize false positives and reduce those investigation costs.
However, you dramatically increase false negatives. You miss real instances of fraud, leading to potentially catastrophic financial losses.
So the business relevance here is that XL Minor allows analysts to adjust this threshold after the model is trained. explicitly to reflect real-world business trade-offs and costs.
Exactly. This is where the analyst acts as the economic decision maker. You don't aim for the threshold that gives the highest overall mathematical accuracy, where false positives and false negatives are generally balanced. You aim for the threshold that minimizes the total expected business cost.
Can you give us the numbers on that?
Sure. A false negative, like a missed security breach, is valued at $1 million, and a false positive, a harmless alert, is valued at $100.
You're going to make a very different choice.
You will dramatically lower your threshold, accepting 10,000 false alarms to prevent $1 million disaster. The final decision is driven by human and financial risk tolerance, not pure math. So to synthesize what we've discussed, having walked through this whole structured process, it's worth summarizing Excel Miner's specific place in the broader predictive ecosystem.
For our learner audience, the business analyst or manager, what are the key strengths of Excel Miner that make this complex process accessible and, effective?
The top advantages are pretty clear. First, its ease of use, and crucially, its seamless integration with Excel. Since Excel is the lingua franca of business, the learning curve for data handling is minimized. It allows for rapid adoption across organizations.
It also provides clear visual diagnostics, those charts for lift, gain, and variable importance that are immediately digestible and managerial.
Right, and it aligns strongly with educational and managerial contexts because it facilitates understanding the concepts in the workflow without getting bogged down in programming specifics. It ensures that business knowledge remains the priority.
So in short, Excel Miner is ideal for business-focused analytics, where the goal is rapid insight, robust methodology, and models that are inherently explainable.
Exactly. Explainable and deployable rather than necessarily developing highly custom, bleeding-edge algorithms.
But to maintain a balanced view, as good analysts should, we have to acknowledge the limitations of the tool. Where does Excel Miner hit its boundaries?
Well, if we compare it to programming-based environments like R or Python, Excel Miner is less flexible. If you need to build highly customized ensemble models, or if you need to handle unstructured data like text documents, images, or audio, Excel Miner is not the tool for that job.
It's built for structured, tabular data.
Exactly. It's also not ideal for very large data sets. When you start talking about terabytes of continuous stream data or massive historical warehouses, an Excel-based system simply cannot handle the load or the complex processing speeds required.
You need dedicated cloud-based platforms for that kind of scale.
You do. Therefore, it is best suited for three specific areas: structured data, moderate-sized problems, and models where interpretability is key. It excels in business departments, analyzing customer churn or credit risk on contained data sets.
And finally, we have to reinforce the most important philosophical lesson embedded in this entire workflow.
The iterative nature of model building.
This is not a start-to-finish project where you get it right on the first try. It is a loop.
Absolutely. The results from step 6, the comparisons and the interpretation, will frequently necessitate iteration. You might look at the variable importance report and realize a predictor you thought was irrelevant is actually a key driver.
Forcing you to go back to step 2, data preparation, to refine the feature engineering around that variable.
Right. Or perhaps the initial classification tree you selected proved unstable on the validation set, forcing you to try an alternative method like logistic regression, returning to step 3. The model is a mirror reflecting the patterns in your data. Sometimes that mirror shows you that your data setup was imperfect.
And the ultimate goal of this iteration isn't just about achieving a slightly higher accuracy number, though that is important.
It's about gaining deeper insight into the data and the underlying business process. Every iteration refines your understanding of the business problem and the complex relationships between your variables. Modeling is a persistent feedback loop designed to increase both accuracy and business insight.
What an illuminating deep dive. We've mapped out the entire predictive modeling journey, using the Excel Miner framework as our guide, stressing process over programming. We started by defining the true goal, out-of-sample performance.
Which means focusing on generalization, not just fitting the past.
We walked through the critical preparation phase, detailing why data must be clean, why categories must be carefully encoded, and why partitioning the data into training, validation, and test sets is the only way to prevent the career-killing pitfalls of overfitting and information leakage.
We looked at the critical trade-offs in model selection, choosing between speed, complexity, and explainability. And finally, we spent significant time on that essential managerial choice.
Adjusting the classification threshold to minimize total business cost, balancing false positive and false negatives based on real-world risk tolerance.
Successful predictive modeling focuses relentlessly on realistic performance assessment, using data the model hasn't seen, and making sure that final decision boundary, that operational threshold, reflects the financial and operational realities of the business problem you're trying to solve.
That reality leads us to our final provocative thought for you to consider. We talked extensively about the trade-offs in threshold selection, false alarms versus missed disasters. If you were tasked with building a model to detect a rare but absolutely catastrophic event,
Like a major factory meltdown.
or a critical system failure that costs lives or millions in damage, which error type, false positive, a warning that turns out to be nothing, or false negative, no warning, resulting in disaster, would your organization be willing to pay the higher cost for, and why?
That's a great question.
Because that answer, driven by risk tolerance and potential damage, tells you more about your organization's ethical and financial structure than any raw accuracy number on a spreadsheet.
Food for thought indeed. We hope this structured approach helps you bring analytical rigor to your next predictive undertaking.
Until next time, keep digging.
Welcome to the deep dive. Our mission here is pretty simple, really. We take these huge, complex topics, strip away all the noise, and try to hand you the core insights. The surprising bits of knowledge that let you feel like you're truly well-informed. Today, we're doing a really focused exploration of a concept that is, well, it's absolutely critical to any data-driven company, but it often stays completely opaque to the rest of us. We're talking about binary decision analytics. It's the process that converts all that messy, continuous output from predictive models, probability scores, into simple, executable, and often very high-stakes business choices.
A simple yes or no.
Exactly. The stack of sources we analyze for today, they detail the essential machinery that makes this happen.
Yeah.
We're not just looking at how models make predictions.
No, that's almost the easy part now.
Right. We're looking at the really critical steps between the prediction and the final decision, and how companies use economics, really, to set the rules of the game. So our mission for you is to walk away understanding precisely why, in this world of high-stakes automation, model accuracy is just. It's a step along the way. It's not the goal.
The real finish line is always maximizing business value. And that distinction right there, the difference between a prediction and a decision, that's the intellectual chasm we really need to bridge today, because the vast majority of consequential automated actions that we all encounter every day, approve, reject, buy or don't buy, act or do not act, they're all binary.
They have to be.
They have to be. And we've gotten incredibly good at the prediction part of it. I mean, we can calculate the likelihood of some event happening with just stunning precision. But as the sources we read make so clear that high prediction accuracy means absolutely nothing until you've successfully mapped that likelihood onto a decision framework.
A framework that has to account for the real-world costs.
Exactly. The cost of acting when you shouldn't have versus the cost of failing to act when you absolutely needed to. We are moving from the realm of statistical possibility into the brutal reality of economic consequence.
Okay, so let's unpack this a bit.
Yeah.
I think we have to start with the fundamental simplicity of the outcome itself. Why binary? I mean, when we have access to such nuanced data, these incredibly complex modeling techniques, why do we still boil down so many major corporate commitments to just a simple yes or no?
Well, the material we looked at suggests it's because the inherent risk, the transactional nature of it, it just necessitates this simplification.
It forces your hand.
It forces your hand completely. All the complexity, all the nuance that happens before the decision gets made. The decision itself has to be a commitment. It's a line in the sand.
That's a great way to put it. You can't, half approve alone.
You can't half approve alone, and you can't sort of flag a transaction for fraud. It's either flagged or it's not.
Right.
And this sharp edge of commitment, that's what defines the entire scope of binary decision analytics. It forces an organization to define its risk appetite in really absolute terms.
What's fascinating here, and what our sources really highlight, is just how this straightforward dichotomy, this constraint of having only two options, is applied across such incredibly complex, high-volume sectors.
Oh, absolutely. Let's start with the examples that are just constantly running in the background of our lives. In financial services, I mean, the volume of binary decisions being made every second is just staggering.
Unbelievable.
Credit underwriting is the textbook example, right? The prediction is the probability of default on a loan. The decision is approve or reject, simple.
But then you have fraud detection.
Right, and that's happening in real time. Does the system automatically block your card purchase, or does it let the transaction go through? Block or allow? This is a decision where mere seconds can translate into hundreds of thousands of dollars in loss. Or, on the other hand, immense customer frustration. The cost sensitivity there is just extreme.
And we see it extending deep into marketing and customer retention too. It's not just about, creating a profile of a customer. It's about tactical expenditure. It's about spending real money.
Mm-hmm.
Do we send that $50 personalized incentive to this specific customer or not? That yes decision is triggered because a model predicted a risk of them churning.
But the analytics, the decision part, has to answer a slightly different question than the model did. The model just says how likely.
The decision has to ask, is the $50 cost actually justified by that customer's predicted remaining lifetime value? And what's the likelihood that the incentive will even work to stop them from leaving?
Exactly. That's a much more complex business question.
And we also see this in crucial operational functions. I found this part really interesting, specifically in optimizing how you deploy resources.
Like predictive maintenance.
Exactly. Predictive maintenance in a huge factory. The model predicts the probability of failure for, say, a critical gearbox in the next month.
So it spits out a number, 72% chance of failure.
Right. And the decision is, do we schedule costly disruptive maintenance this week we act, or do we wait and risk a catastrophic failure? We don't act.
And the sources detail how that decision threshold, that tipping point, is highly dependent on the cost of downtime versus the cost of, doing the service too early.
If that downtime costs the company $50,000 an hour.
Yeah, your tolerance for risk goes way down.
Right. Your decision threshold for intervention is going to be dramatically different than if the downtime is just a minor inconvenience.
It's a great point. It shows how that constraint of act or not act forces a kind of economic discipline on the entire process.
And this even happens in healthcare. Our sources mention how this framework is used to guide things like initial triage and screening.
Mm-hmm.
Based on a whole battery of tests, a model might assign a risk score for a particular disease.
Mm-hmm.
And then comes the binary decision. Do we immediately move to an invasive treatment or, say, a high-cost diagnostic image? Or do we just hold on?
Treat or observe.
Treat or observe. And that binary choice has to balance the terrifying risk of delaying treatment, which is a catastrophic false negative, against the cost and the physical impact of an unnecessary intervention, which is a pretty significant false positive.
The ubiquity of this is it's everywhere. It means that virtually every automated interaction you as a listener have as a consumer,
Right, from getting an insurance quote online,
to your email getting a spam filter decision.
it's all governed by one of these carefully calibrated decision rules. It really is the invisible mechanism that companies use to define and manage their exposure to both risk and opportunity.
And the simplicity of that final outcome, that yes or no, it completely hides the enormous analytical complexity that goes into setting the trigger point.
Precisely. And that rigorous structure is absolutely essential.
Mm-hmm.
Because when you're dealing with millions of transactions every single day, you just cannot afford to have ambiguous outputs.
No, you need a clear rule.
Decision analytics provides that structured toolkit. It's what ensures those automated switches are flipped, not just according to some statistical likelihood, but according to optimized, quantifiable organizational goals.
So now we arrive at the core intellectual challenge. This is the thing that really separates, let's say, data science from decision science.
Okay.
And it's this huge misconception that high predictive accuracy automatically delivers good business results. Our sources are they're emphatic on this point.
They are not the same thing.
Prediction and decision are fundamentally different processes. Full stop.
So let's define them again really clearly, because this is so important. Prediction is purely descriptive.
Mm-hmm.
It's just answering the question, what is the likelihood this event will happen? That's it. The model produces a continuous score, from 0.0 to 1.0. A credit model produces a score of, say, 0.82.
Which means an 82% likelihood of repayment. That's the prediction.
That's the prediction.
Yeah.
But decision?
That's prescriptive.
Completely different. It answers the question, what action must we take, given that likelihood, to maximize our value?
Mm-hmm.
The decision translates that 0.82 likelihood into a single enforceable action, approve or reject.
And the moment you commit to that action, you've left the world of statistics.
And you've entered the world of economics.
Exactly. And we connect this to the bigger picture. The reason prediction does not equal decision is actually quite simple. The predictive model is context blind.
What do you mean by that?
It operates purely on historical data pattern it was trained on. It knows what it has seen before. A good decision, however, has to incorporate the real-world context of consequences.
Ah, I see.
This is why the decision framework requires factoring in these essential externalities that the model itself just cannot compute.
And those essential factors, which are highlighted all throughout our source material, are the things we have to assign a value to. They are costs, benefits, risks, and constraints. And let's maybe break down just how hard it is to quantify these, because this is where the real analytical work, the human work, truly begins.
It really is.
So let's start with costs. These are the expenditures you incur when you choose the yes action. Sometimes this is straightforward, right?
Sure. If it's a direct monetary expense.
Like the cost of mailing an expensive promotional package, or the cost of the raw materials for a new order, or, the salary cost of a technician performing that preemptive maintenance we talked about.
But you also have to factor in opportunity costs. And that's where it gets tricky. If we decide to shut down a machine for service, the cost isn't just the technician's time.
Right. It also includes the lost potential revenue from that machine being idle.
And that is often much, much harder to pin down precisely.
Okay, so that's costs. Then you have benefits.
Right. These are the desired positive outcomes you get from taking the correct action.
So if we approve a loan to a reliable borrower, the benefit is the interest we earn over the life of that loan.
And if we successfully retain a customer who is about to leave, the benefit is their projected lifetime value. Analysts have to assign a hard dollar value to these benefits.
And that's not simple.
No, these are often highly complex calculations that require forecasting and discounting future cash flows back to the present day. And if you miscalculate that benefit, you will absolutely set your decision threshold incorrectly.
This is where we run into that inherent difficulty of the quantification exercise. As an analyst, how do you quantify the true benefit of, say, avoiding a total system collapse?
It's a massive challenge. You have to build scenarios.
Okay.
For instance, the benefit of avoiding a failure is often calculated as the cost of the failure minus the cost of prevention. But the complexity deepens when we get to the third factor.
Which is risks.
Right. And this is the potential negative consequence associated with either acting or not acting.
And we should be clear here. We're not talking about the statistical probability of the event happening.
No, that's the model's job. The model gives you the probability.
We are talking about the severity of the consequence if it happens.
The impact. If we fail to stop a fraudulent transaction, so inaction, the risk is a direct financial write-off, plus maybe regulatory penalties.
But if we incorrectly flag a legitimate transaction, so we take action, the risk is customer annoyance.
And that translates into an intangible risk, right?
Yeah.
Reputation damage and the potential for future churn. The decision framework forces you, the business, to place a dollar value on that intangible risk.
That sounds incredibly difficult.
It is. It's often where most of the arguments happen in the room when you're building one of these systems.
And that brings us to the final piece, constraints.
These are the non-analytical limits that are imposed by the real world, and these are often the ultimate arbiter of the decision.
So these are the factors that can just overrule an otherwise profitable decision.
Absolutely. This includes things like legal compliance. For example, there are requirements governing lending practices that prohibit certain kinds of risk filters, even if they're predictive.
So the law trumps the math.
The law always trumps the math, or you have contractual obligations. But the constraint that often sneaks up on optimization teams is just sheer logistical limitation. Capacity. Let's say your perfectly optimized decision rule identifies 10,000 high-value customers who need a high-touch intervention to prevent them from churning. And the expected benefit from these interventions is massive on paper.
Sounds great.
But if your call center can only physically handle 1,000 calls per week,
Then the model is useless.
well, not useless, but the constraint of capacity forces the decision team to dynamically raise the action threshold. They have to make it harder to qualify for the call until they hit the maximum number of people they can actually handle. The optimal analytical answer is instantly constrained by reality.
I think the weather analogy we saw in the source material really crystallizes this separation perfectly.
It's a great one.
The prediction is the 90% chance of rain. That is a fact provided by the model.
But the decision to carry an umbrella, that depends entirely on these externalities we just talked about.
Right. If you're preparing for a week-long backpacking trip, the cost-risk ratio, the inconvenience of carrying the umbrella versus the risk of being soaking wet and miserable for 7 days, it pushes the decision to yes.
Of course.
But if you're just moving from your office building to the attached parking garage, the cost-risk ratio pushes the decision to NO, even with the exact same 90% probability.
The decision framework provides that crucial weighting mechanism. It gives you the context.
And this separation is so critical for you, the listener, to grasp, because it shows that a model builder can achieve, I don't know, a Giannani coefficient of 0.85, a brilliant statistical achievement.
Top of the leaderboard.
Right. But if the decision maker incorrectly quantifies the cost of a false positive versus the benefit of a true positive, the entire deployment will lose money.
Yeah.
Shifting from likelihood to economic value is the essential task.
Okay, here's where it gets really interesting, because now we move from the theory, this separation of prediction and consequence, to the actual mechanics of how you bridge that gap.
Right. How do you make it work?
We have a predictive model. It's giving us a continuous score. And we need a surgical way to convert that into a definitive yes or no action. This conversion is handled entirely by what's called the decision threshold.
So the model outputs a probability, let's call it Scholar's dollars, that ranges from 0 to 1.
Correct.
And we have to define a threshold, let's call it $2.
Yeah.
So the formal decision rule is just, if the dollars is greater than dollars, take the action. If polos is less than or equal to dollars, don't take the action.
That's it. That one single number, $2, is the most powerful lever an operations manager has in the entire system.
Why?
Because it encapsulates the organization's entire risk tolerance into a single operational value.
And I think the emphasis has to be placed here.
Yeah.
Selecting that threshold, $2, is fundamentally a decision problem.
Yes, it is not a modeling problem.
The model builder, their job is to separate the true positives from the true negatives as cleanly as they can. But the optimal threshold selection, that depends entirely on external business objectives and cost considerations.
To illustrate this, let's go back to that classic problem. Targeted retention marketing. We want to spend money on customers who are most likely to leave, but only if they're actually worth saving.
Right.
So let's say we have two primary values. We have the cost of the false positive, let's call it CFP doll. That's the price of the incentive we send to someone who wasn't going to leave anyway.
Wasted money.
Wasted money. And then we have the benefit of the true positive by BTP. That's the retained profit from a successful save. The customer stays, we keep their business.
Now, if we only cared about model accuracy, we might just pick the threshold where the true positive rate and the true negative rate are equal, or maybe just default to a threshold of 0.5.
Which is incredibly naive.
Right, because if the incentive costs, say, $50 and the customer's lifetime value benefit is $1,000,
Yeah.
we can afford to spend that $50 much more often, even if we're wrong half the time, to catch that $1,000 prize.
This is where the technical mechanics really come in, and it's essential for our audience to grasp this. Analysts actually use a relative cost ratio to dictate what the optimal threshold should be.
So it's not a guess.
It's not a guess at all. In a simplified scenario where the costs are purely monetary, the optimal threshold dollars is mathematically derived by balancing the costs of the errors against the benefits of the correct decisions.
Okay.
Now, the exact formula can get pretty complex depending on the scenario, but the intuitive relationship is the key thing. The threshold is set where the expected net profit, or the cost from a marginal decision, switches from being negative to being positive.
So you're finding the exact tipping point.
You're finding the tipping point. The business has to first define that relative cost ratio. How many unnecessary $50 incentives, the false positives, are we willing to tolerate to catch $1,000 save, which is our true positive?
I think that's where I need to push back a little bit. If the threshold is determined entirely by this cost ratio,
Right.
does that make the model's absolute accuracy kind of irrelevant?
Yeah.
For example, if we have a model that's statistically mediocre, but the cost ratio is just so skewed, like missing a single instance of fraud costs $10 million and a false positive costs 10 cents, shouldn't we just set the threshold incredibly low to capture almost everything, regardless of what the model says?
That is a fantastic point, and it perfectly highlights the dynamics here.
Yeah.
Yes. In extreme cases of cost asymmetry, the model's predictive power becomes less critical than the accuracy of your cost assignment.
So the costs are more important.
The optimal threshold is always determined by the cost-benefit structure. Always. The model's quality simply dictates how much value you can extract at that optimal threshold.
Okay, say more about that.
A better model will result in a higher net expected value at whatever the optimal dollars is. A poor model will result in a lower net expected value, even if you're using the same optimal dollars. The cost ratio defines where you should look on the probability scale. The model quality determines how high the value is at that point.
I see. So a better model makes the peak of the profit curve higher.
Exactly. Let's talk about the impact of threshold changes from an operational perspective. Because altering $2 from, say, zero point 0.7 down to zero point 0.5 doesn't just change the numbers on a spreadsheet. It fundamentally changes the day-to-day work of the organization.
How so?
Well, if we drop the threshold in a fraud detection system, what happens?
You're going to get a lot more alerts.
A lot more alerts. You suddenly increase the volume of transactions that require a manual review by a human. That's a massive increase in operational cost for your call center. The threshold choice is a direct translation of your risk policy into an operational budget.
So this forces all the operational trade-offs right out in the open. You're balancing the costs of overreaction against the costs of underreaction.
Precisely.
So when we talk about making aggressive decisions, what we're really saying is we're setting a low threshold, maybe 0.3.
Right, you're casting a wide net.
We're increasing the action rate significantly. And this maximizes the potential benefit because we're capturing those marginal cases. The customers who are maybe only 35% likely to churn, but whose retention is still highly valuable to us.
But the immediate consequence of that
Is a sharp rise in false positives.
a huge rise. You're spending a lot of money unnecessarily. You're intervening in cases that would have resolved themselves happily without you.
Okay, so conversely, you have conservative decisions.
This means a high threshold, maybe zero point 0.8 or even higher. You are only acting when the model is extremely confident that something is going to happen.
And this minimizes the risk of wasting resources, right?
Yeah.
You'll have a very low false positive rate.
You will. But the massive danger here is the huge population of false negatives you're creating. You are missing enormous opportunities or exposing yourself to major risks because those critical cases scored 0.79.
Just below your arbitrary high bar.
Exactly. You lose the customers who really needed that intervention, or you fail to stop the fraud that was 79% likely.
And decision analytics provides the structured methodology,
Yeah.
this expected value calculation, which I think we should detail next to navigate this trade-off.
Yes, to find that mathematically optimal pivot point where the cost ratio is perfectly satisfied. That threshold, $2, is the single analytical expression of the company's financial risk philosophy.
Okay, so we've established that simple accuracy metrics are just. They're insufficient. They're not the right tool for the job.
Right.
If you're reporting 95% accuracy, but the 5% of cases you missed all involve the complete failure of your main manufacturing line, your decision system is worse than worthless.
It's actively harmful.
So now we have to shift entirely into the language of business, which is dollar value. This is the heart of what's called cost-sensitive decision-making.
And to structure this properly, we need to rigorously define the 4 possible outcomes of any binary decision, but in terms of their economic impact. This is what forms the cost matrix, or sometimes a profit matrix, that every serious decision analyst has to build.
Okay, so let's redefine the successful outcomes first, but in financial terms.
Good idea.
Number 1 is a correct yes or a true positive TP. The model correctly predicts an event, like fraud, and you take the correct action, you block it. This generates a benefit.
And that benefit is the loss you avoided.
Right. Then number 2 is a a true negative, TN. The model correctly predicts no event will happen, no churn, and you correctly take no action. This also generates a benefit.
Which is the cost you saved by correctly avoiding an unnecessary intervention. You didn't spend money you didn't have to.
Okay, so those are the 2 good outcomes. Now for the high-stakes error outcomes. Number 3, an incorrect yes or a false positive, FP. This is when you take action unnecessarily. You send that expensive incentive to a loyal customer who is never going to leave. It's a costly error.
The cost is the resources you wasted on that unnecessary intervention. We call that CFP.
And then the 4th and final outcome, an incorrect no or a false negative, FN. This is when you fail to take a necessary action. You fail to stop a major instance of fraud. This is the major risk error.
And the cost is the loss incurred by missing that event, which we'll call CFNR.
Now, the core insight here, and this is the one that really separates amateur modeling from professional decision science, is that different errors often have drastically unequal consequences.
Right. CFN rarely, if ever, equals CFP.
In medical screening, the cost of a false negative missing a lethal disease diagnosis is exponentially higher than the cost of a false positive, which might be requiring a patient to undergo further, ultimately unnecessary testing.
It's life and death versus inconvenience and a few $100s. The costs aren't even in the same universe.
So let's really drill down on the fraud example deep dive here, because this one requires quantifying both hard dollar loss and that squishy intangible risk, which is a key technical challenge for any analyst.
Okay.
So if the model produces a false negative, it misses a major fraudulent wire transfer. The resulting cost is a direct charge-off of, let's say, $50,000, plus maybe compliance fines. That is a hard, measurable negative cost. That's CFNL.
$50,000. Got it. Now, if the model produces a false positive, it flags a customer's legitimate high-value purchase of, I don't know, a boat.
Okay.
The cost is often much lower in raw dollars. It's the 2 minutes of the call center agent's time and maybe a small fee to clear the transaction.
It's a few bucks.
But, and this is the key part, the analyst must also assign a dollar value to the intangible consequence.
The customer's frustration.
The high-value customer's frustration and the potential risk that they get so annoyed they switch banks next year. This requires the business to make an executive decision. They have to say, okay, we estimate the average long-term damage of a single false positive is, say, $50.
So you had to put a number on it.
You have to. The analyst's task then is to determine the ratio. If CFN is $50,000 and CFP is $50, the institution should clearly prioritize minimizing those false negatives.
Even if it means generating a ridiculously high number of false positives.
Exactly. Your overall accuracy might drop dramatically, but your net financial performance skyrockets.
This leads us directly to the core analytical tool for this, which is the expected value calculation, or sometimes expected monetary value, EMV.
Right. The goal is to move beyond just counting right and wrong, and instead to either minimize your expected total cost or maximize your net expected value.
And the EMV for any single decision rule, so for a specific threshold, $2, is calculated by summing up the value of all 4 of those outcomes, but weighted by the probability of landing in each quadrant.
Right. So the total expected cost isn't just, say, the cost of a false negative multiplied by the number of false negatives you observed. It's the probability of false negative even occurring multiplied by the costs associated with that outcome.
So mathematically, for a big population, we can calculate the overall EMV by summing up the count of each outcome multiplied by its assigned monetary value.
That's the formula. It's EMV counts BSP times BTB plus count me times CFP. But the analyst doesn't just calculate this once. They iterate. They calculate this value across every possible threshold, $2, from 0.0s all the way to 1.0. And what this generates is a profit curve or a value lift curve.
And this curve charts the total expected profit against every possible threshold, so the decision manager's job becomes easy.
They just pick the threshold that corresponds to the peak of that curve.
And what's absolutely crucial for everyone to understand is that the peak of this profit curve very rarely aligns with the peak of the accuracy curve.
Almost never.
The most accurate threshold might sit at $1.55. But if the cost of false negatives is extremely high, the peak profit might be generated at a much lower, more aggressive threshold, like $2.40.
Because at 24, you capture vastly more of those valuable true positives, and the small cost of the extra false positives you generate is a price well worth paying.
So therefore, the evaluation metrics have to be entirely financial.
They must be.
We abandoned standard classification metrics, F1 score, recall, precision. They're useful for the modeler, but they are not primary decision metrics. Instead, we used total profit, total cost, net expected value, or return on investment.
The model's success is measured exclusively by its bottom line impact after you apply that cost matrix.
This brings us to the ultimate conclusion of this section, and it's a big one. The best decision rule may, and very often does, not correspond to the most statistically accurate model.
It's a non-intuitive but vital point. If you are comparing two models, Model A with 90% accuracy and Model B with 92% accuracy, you might assume Model B is better.
Of course.
But Model A, paired with a perfectly optimized cost-sensitive threshold, might deliver 20% higher net expected value than the slightly more accurate Model B running on a default naive threshold. Understanding the cost matrix is what generates the impact.
Okay, so once the analytical team has done all this work, they've built the cost matrix, they found the optimal cost-sensitive threshold, that peak on the profit curve. The final challenge is operationalization. How do we make sure this mathematical insight becomes a reliable, scalable business process that actually performs out there in the real world?
This starts with defining the formal decision rules. These rules have to be incredibly simple, they have to be actionable, and most importantly, they have to be machine readable.
So they're the explicit instruction set.
They're the instruction set that operationalizes the analytical insight. It's a simple statement. For customer X, if their predicted probability of churn exceeds 0.43, then you initiate the high-touch call script and send retention offer Y.
And that ensures consistency across millions of automated decisions.
Exactly. And this requires some pretty sophisticated integration into systems. The sources we read detail that these yes-no decisions need to be fast, often real-time,
Like with fraud detection.
like with fraud or high-frequency trading algorithm or even a real-time credit check at a point of sale. The entire prediction-to-decision cycle might need to execute in under 50 milliseconds. So for this high-speed automated integration to be successful, the analytical deployment has to satisfy three really rigorous operational requirements. First, it has to be reliable.
Meaning the scores are consistent and the system basically never fails.
Right. Second, it must be transparent. This means the entire logic chain, the model weights, the input features, and that all-important decision threshold, it all has to be auditable and explainable.
And transparency is just non-negotiable in regulated industries, right? Like finance and insurance.
Absolutely non-negotiable. And third, and this is crucial.
The decision system has to be aligned with business policies.
Yes. This is where the complexity of your organization feeds back into the automation. A decision system that optimizes for short-term profit, but in doing so, violates the company's long-term customer satisfaction policy. That's a failure.
So the model predicts, but the business policy defines the boundaries of what is acceptable action.
Precisely. But this discussion can't just end with perfect automation. We have to address the persistent need for constraints and managerial judgment.
Right? No amount of data can fully automate strategy.
This is particularly true when you're dealing with legal constraints. Decision analytics often butts up against these non-negotiable policy walls.
We talked about this a bit before.
Right. A credit model might calculate that rejecting all applicants from a certain neighborhood maximizes profit. But if that decision violates fair lending laws, the legal constraint just supersedes the profit optimization. Full stop.
So the system has to include filters or post-model constraints that can override the analytical answer to make sure you stay compliant.
And managers have to monitor the outputs to make sure the system doesn't accidentally wander into legally restricted territory.
Then you have the purely logistical capacity limitations.
Which we touched on, but it is the most common real-world impediment to perfect optimization. If the optimal threshold generates 10,000 yes decisions for a marketing campaign.
But the marketing team's budget can only afford to mail 5,000 expensive packages.
The manager has to use their judgment. They effectively use that optimized profit curve we built to set a secondary threshold, one that ensures the 5,000 most valuable interventions are selected.
Even though the overall analytically optimal threshold was actually lower?
Right. It makes the manager's role less about defining the math and more about managing the resource allocation based on the math.
Managerial judgment also becomes essential when you're dealing with things like changing base rates or model drift.
Oh, hugely important.
If the underlying population behavior changes drastically, say a sudden economic downturn hits, the optimal threshold you calculated 6 months ago might lead to catastrophic risk today.
And the manager has to have the authority and the insight to adjust that threshold dynamically, even if the model itself hasn't technically failed yet by its own metrics.
So the overall conclusion for operationalization is really clear. Decision analytics provides structure, it quantifies risk, and it guides the optimal action. But it doesn't provide absolute, unmonitored answers.
The determination of the cost matrix, the definition of the policy boundaries, the integration of real-world capacity constraints. All of that requires informed human judgment to ensure the analytical system serves the organization's overall strategic goals. Automation is powerful, but governance is paramount.
So after all that, what does this all mean? Let's try to recap the key takeaways we've gathered from this deep dive into binary decision analytics.
Let's do it.
First, we've established that these simple yes-no decisions are the high-stakes, fundamental actions that are driving automated business outcomes all over the world.
And, crucially, we learned that the conceptual divide between a prediction, which is just a likelihood, and a decision, which is an action, is vast. And a good decision has to incorporate those four externalities: costs, benefits, risks, and constraints.
We then saw how the decision threshold is this single, powerful analytical link. It acts as the economic control lever for the whole system.
And its selection is not a statistical problem. It is purely an economic one, designed to balance aggressive action against conservative avoidance.
And finally, we detailed that the performance of a decision system is judged not by simple classification accuracy, but by maximizing its net expected value.
This is because that cost matrix, where different errors have highly unequal dollar values, it completely overrules raw statistical performance.
This raises, I think, a really important question for you, the listener, that we hope sticks with you long after this.
When you encounter news about the impressive accuracy or performance of some new AI model being used in banking or medicine, you should ask yourself, how much do I truly know about the underlying cost-benefit structure it's optimizing for?
Are they just minimizing the total count of errors?
Or are they specifically minimizing the dollar cost of the most catastrophic false negative error? Because that difference is everything.
That distinction changes the entire perceived value of the system. The focus should never be just on the score. And I think that leads us to our final provocative thought for this week.
The most statistically accurate predictive model might actually be the one that delivers the least net expected value.
If the decision threshold is set incorrectly, based on a naive or a faulty cost matrix.
The true skill in analytical deployment is not in building the prediction engine itself anymore. It's in rigorously defining and designing the consequence structure.
So we encourage you to consider the hidden, calculated costs behind every automated yes or no decision you interact with this week.
We'll be back soon for the next deep dive.
Welcome back to the Deep Dive. Today we are wrestling with a magnificent paradox of modern decision-making.
Yeah.
We're talking about massive, multi-million-dollar business strategies, global logistics, intricate resource challenges, and how the solutions to these huge problems often rely on reducing everything down to the simplest possible choices.
Yes or no?
Yes or no. Select or do not select. 1 or 0.
And that reduction to binary simplicity, that's exactly what gives these systems their extraordinary power. But it's also, like you said, the paradox.
Right.
I mean, when you are tasked with selecting the optimal portfolio from hundreds of thousands of interconnected decisions, let's say choosing which 20 out of 500 possible new product features to fund, or which 10,000 customers in a database of 1 million to target, the ability to find that single best combination while respecting every single real-world limitation, that dictates success. The margin between a good intuitive selection and the mathematically proven optimal one can be worth, well, immense value.
Okay, so let's unpack this. Our mission today is to give you, the listener, a clear, deep understanding of the mathematical framework that underpins these system-level choices. We're talking about binary optimization modeling, or BOPs. We've cracked open the fundamental sources that define not just the variables and the objective functions, but the mechanics that allow these models to consistently outperform human intuition and, simple linear decision-making.
It's truly an engine for strategy. At a high level, a binary optimization problem requires you to choose the best combination of those binary decisions, those yes, no, select, do not select choices, and you're making them all simultaneously across the entire system.
Okay.
The goal is always to maximize a specific objective, like profit, or to minimize something like cost, all while you're operating under extremely strict and formalized constraints.
So we're not just looking for a single good decision. We're searching for the single best mix of thousands of decisions. It's the ultimate strategic balancing act, and I think we need to understand exactly how the engine room of this process works if we're going to trust its output. All right, let's start with the basics. When we use the word binary, we're defining the decision space as, well, absolutely discrete. Every potential choice has only 2 states.
Exactly.
There's no middle ground. You can't allocate, say, 30% of a resource to option A. It's either 100% in or 0% out.
Precisely. The language of mathematics handles this with the variables 1 or 0. But in business terms, this applies to choices where a continuous allocation is either impossible or just irrelevant.
Like what?
Well, we're selecting products for a promotion, choosing which suppliers to contract with, deciding whether to activate a physical location, or selecting whether to approve a specific capital project. Each of those options has to be sorted into one of 2 boxes. Yes, select, which is a 1, or no do, not select, a 0.
And it's the sheer scale that makes this so difficult. I mean, if I'm a manager, I can probably handle, 5 or maybe 10 of these choices in my head. But when a decision involves thousands or even millions of these independent variables, suddenly the complexity just explodes.
That scale is both the challenge and the opportunity. Think about resource allocation in a major pharmaceutical company. They might have 2,000 potential R&D projects globally.
Wow.
Each one of those projects is a variable, and $6. Fund it 1-1 or don't fund it. And if they only have the budget and the staffing capacity for, say, 50 projects, the goal is to find the single combination of 50 chosen projects that gives them the highest total expected strategic return for the entire organization.
That immediately implies there has to be a single overarching goal. You can't just pick projects that look good on their own.
Exactly. You have to pick the combination that maximizes the objective. The objective function is absolutely critical here. It must be measurable, and it must encompass the entire scope of the problem.
So you're asking, what are we maximizing the net present value of the selected portfolio?
Or are we minimizing the logistical risk across the supply chain nodes we've selected? Or are we maximizing the customer lifetime value from the marketing targets we've chosen? Whatever the goal is, the model ensures that every single selection, every single one, feeds into optimizing that single defined metric.
So it sounds like these BOPs are fundamentally about managing massive trade-offs under scarcity, which, explains why our source material really emphasizes that these problems are foundational in managerial and operational decision-making. I mean, if you have limited capital or limited resources, you're constantly solving a BOP, whether you know it or not.
That's a perfect way to put it. And to really grasp the power of this, we need to make a very sharp distinction, because people often confuse a simple binary decision with a binary optimization problem.
Okay, so if I am deciding whether to approve one singular purchase order, that's just a binary decision. I check the rules, I check the budget, I say yes or no. That seems pretty straightforward.
It is straightforward because it's isolated. The outcome of that single decision doesn't really alter the feasibility or the profitability of other unrelated decisions within the system.
Yeah.
The criteria are usually just simple pass-fail metrics.
So where does the leap happen? When does it become an optimization problem?
The leap occurs the moment you introduce multiple interconnected decisions that are all subject to a shared constraint. This is where the complexity just explodes.
Okay.
Let's imagine you're managing a portfolio of, say, 6 potential software upgrades. Each one is a yes-no decision. If you say yes to the big flagship financial system upgrade, that one project alone might consume 90% of your annual IT maintenance budget.
Right.
And it requires your top 2 security architects for 6 months straight.
So that single yes decision, which might be an excellent choice on its own, now forces you into no decisions across 5 other projects.
Precisely. And those 5 other projects, they might individually be less valuable than the financial system, but taken together, they might offer higher cumulative security benefits or maybe greater stability across the rest of your platform. The decisions interact. They compete for the same pool of scarce resources: money, time, expert labor.
So it's not about judging the quality of Project A in isolation anymore, is it? We are forced to shift our focus entirely to the quality of the overall system performance that results from the entire portfolio of selections we make.
Absolutely. The decision maker is no longer asking, is this one project profitable? But rather, is the total outcome, the combination of selected projects, the ones, and the foregone projects, the S's, is that the single highest possible strategic value we could extract from our limited resources?
That's a big shift.
It's a huge shift from evaluating local quality to maximizing global performance. And this is where intuition fails. Humans are generally quite poor at evaluating thousands of complex, interacting trade-offs all at the same time.
So the BOP framework just forces us to manage those trade-offs mathematically. It ensures the final portfolio is the best systemic choice, even if it feels counterintuitive to skip that one massive, shiny project.
Exactly. Hashtag tag 1.3, real-world applications, why you should care.
The moment you realize this framework is simply about allocating scarce resources to maximize value, you start seeing it absolutely everywhere. Let's look at the immediate, practical scenarios from our source material, maybe starting with marketing.
In marketing, you are just swimming in data. You have a massive list of potential customers, maybe 10 million individuals.
Okay.
You want to run a personalized mail campaign, but printing and postage costs, say, $2 per piece, and you have a budget cap of $2 million. That means you can only select 1 million customers.
That is 10 million potential yes-no decisions, but you're constrained to only 1 million yes votes.
Right. And for each of those 10 million customers, your predictive model has generated an input, an estimated expected revenue if they convert. The BOP has to select the 1 million customers who, collectively, promise the highest overall revenue while making sure the total cost of selection, that $2 million budget, is not breached.
So it's ruthless.
It has to be. It will ruthlessly cut high-cost, low-return prospects, even if they looked good on paper, if including them prevents the selection of a more profitable cluster of low-cost prospects.
This applies directly to financial strategy too, right? Specifically project funding. When capital budgets are set, they are hard constraints.
They are. Management typically faces a pipeline of potential initiatives, upgrading facilities, pursuing mergers, developing new product lines. Let's say we have 15 distinct initiatives, and we can only spend $50 million. The model determines the optimal portfolio of investments, which combination of ones and zeros that maximizes expected return or aligns best with long-term strategic value, all while staying within that $50 million CapEx limit. And crucially, the model can spot redundancy or synergy between projects and factor that into the overall score.
And operationally, this has to be vital for, like, footprint management. I'm thinking of global retailers constantly facing binary location decisions.
Absolutely. Think about a retail chain that's reevaluating its regional presence. Every single store is a variable, open 1 or close 0.
Right.
The objective might be to maximize market coverage while minimizing operational cost and staying below a preset logistics capacity limit. The optimization model might suggest closing a profitable store in one location if that closure frees up key distribution resources needed to service 4 new stores in a high-growth region, which leads to a higher overall net profit for the whole system.
This all boils down to that final application, resource allocation. You have limited inputs, whether it's specialized talent, manufacturing capacity, or raw materials. The BOP forces an explicit trade-off.
If we allocate our limited supply of rare earth minerals to product A, we simply cannot build product B. The model ensures that the chosen allocation maximizes value across the entire system, forcing departments to share and compete for resources based on overall organizational benefit, rather than, whoever shouts the loudest. If you care about maximizing value under conditions of scarcity, this is the framework that dictates strategic success.
Okay, now we go under the hood. How does the model translate the complexity of a real managerial decision like which supplier contract to renew into pure mathematics?
It's through the elegant simplicity of the formal binary variable. Each decision point, let's call it $E, is assigned a variable $6. If we have 1,000 potential suppliers, we have variables x to the 1 through 6 demandas. That translation is the first critical step.
So $6 is our managerial lever.
Exactly. When the solver runs, it is simply trying to decide the value for every single one of those levers. 1 equals. We select this supplier, we launch this product, we fund this project. 0 equals we do not. This standardization is crucial because it allows all these complex, very different decisions, from hiring a person to launching a rocket, to be fed into the exact same mathematical system.
So that reductionist approach brings immediate clarity. There's no ambiguity about the decision space. And what's fascinating is that the final output, it isn't some complex report, it's just a massive list of ones and zeros.
And that list is the action plan. If you are solving a facility location problem involving 50 cities, the solution is 50 binary values. It might look like 100, 110, and so on, telling you precisely which cities to open facilities in. It formally dictates the choices that must be executed to achieve the defined maximum objective value. Without this formal translation, the optimization can't even begin.
Okay, so once we have the choices formalized as variables, we need to guide the engine. And that's the job of the objective function. This is basically the mathematical definition of success itself.
It is the single metric the system is striving to optimize. It's usually stated as maximize Z, where Z is our total system outcome. And this function is typically linear, meaning it's just a sum of the contributions of all our chosen variables.
And the contribution in each binary decision is weighted, I assume.
Precisely. Each potential choice $6 comes with an associated coefficient, let's call it 70. If $6 represents the expected profit of project dollar, then the objective function just sums up the expected profits of all selected projects. Z of Z equals C1x1 plus C2x2 plus C3x33 and so on.
Right.
So if we select project 1, $6 becomes 1, and we add C dollars to the total profit Z. If we skip project 2, X2 is his dollars, and C.2 times dollars means we add nothing.
I see. So the binary variable acts like a gate. It either lets the full potential value of that choice flow into the system's total score, or it blocks it completely.
Yes, and the solver's job is just relentless. It's to test combinations of ones and zeros until it finds the configuration that produces the largest possible z value, subject to the constraints, of course.
Of course.
And we aren't just maximizing raw profit either. This is where strategic nuances come in. The objective could be maximizing a risk-adjusted expected value, where those coefficients such dollars already incorporate the potential downside or the volatility of that choice. The better defined your objective function is, the more aligned the mathematical output will be with your true strategic priorities.
So if the objective function defines success, the constraints must define reality. You can't just pick everything that makes money.
Constraints are the absolute rules of engagement. They translate real-world limitations, whether they're physical, financial, or managerial, into mathematical inequalities that the solution absolutely must satisfy. If a solution violates even one constraint, it's thrown out. It's infeasible, regardless of how high its objective value z is.
Let's delve into the specific types, starting with the most intuitive one, budget limits.
Budget constraints are usually simple totals. If project I costs $8, then the sum of costs for all the projects you collect must be less than or equal to the total allocated budget, B. Mathematically, it looks like sum of AGI is less than or equal to B.
And if you have multiple budgets?
If you have, say, a capital budget, an operational budget, and a marketing budget, you'll have separate constraint equations for each one. The model will have to satisfy all of them at the same time.
That makes perfect sense. Okay, next up, capacity restrictions. This moves beyond just money and into physical limits.
Right. Capacity is about physical or logistical limitations. For instance, if you're optimizing product mix in a warehouse, the volume dollars of each selected product, $60, must not exceed the total available storage space, S.
Okay.
So sum of dollars is less than or equal to S. And this forces a really crucial trade-off. Do you fill your capacity with a few very large, high-value products or a high volume of small, maybe lower-margin products? The model will find the configuration that maximizes Z within that physical box.
This leads us to policy rules. This feels like where the human element enters the math, even before the final managerial review. These rules impose an intent that isn't purely financial or physical.
Policy rules are fascinating because they often involve interlocking decisions. We can use them to enforce dependencies. For example, a policy might state, if we select the new financial system upgrade, which is projects X dollar, $1, we absolutely must also fund the associated security audit, project text $2. This creates a constraint that looks like X dollars is less than or equal to text title dollars, meaning it's selected, then X dollars has to be 1. If X dollars that does dollars it skip, then text dollars can be either 0 or 1.
That's a powerful way to embed strategic logic right into the system. You can force the model to include certain things that are necessary for compliance or synergy, even if the model might have preferred a slightly different, more profitable path without that rule.
Absolutely. You can also impose minimums like, we must select at least 3 projects focused on R&D to maintain our competitive edge. That might look like $6 plus XB plus XCO and so on is greater than or equal to 3. These policy constraints are key to guaranteeing the solution is strategically aligned, not just monetarily maximized.
And finally, resource availability. This seems like it could be the most complex constraint because resources are limited across so many dimensions.
Indeed. It could be engineering hours, access to specialized equipment, or key people. The amount of a resource R consumed by all the selected options must not exceed the total supply you have. So if your total supply of senior data scientists is 1,000 hours this quarter, and Project A requires 500 hours and Project B requires 600 hours.
The model knows you can't do both.
It knows you can't select both. The constraints are what guarantee the final list of ones and zeros is actually implementable in the real world. They provide the necessary friction.
The BOP engine is only as good as the fuel it runs on. The mathematics of optimization might be perfect, but the outputs, the expected revenues, the probabilities, the costs, all of that has to come from somewhere.
It does.
And that source is high-quality predictive analytics.
That's the critical link. Optimization models don't generate these coefficients, the solos or the costs, the A's themselves. They rely entirely on the quality of the inputs provided by parallel predictive systems, machine learning, statistical forecasting, simulation models.
So what specific kind of data is flowing into the BOP model?
We're talking about data that quantifies the future impact of a decision. So first, probabilities. the likelihood of a specific outcome, like the probability of a new product reaching market success or a targeted customer converting.
Okay.
Second, expected revenues, which are essentially those profit coefficients we talked about. This is the model's estimation of the upside. And third, risk estimates, which quantify the potential downside or the volatility associated with a decision.
And if the predictive model gets it wrong, say it overestimates the return on investment for Project X by 50%, the optimization model, being ruthlessly rational, will prioritize Project X.
And in doing so, it could potentially consume all the scarce budget and exclude projects that would have actually offered a far superior return in reality.
So it's the classic garbage in, garbage out.
It's the textbook definition of garbage in, garbage out, or GI-GO. The optimization model is a powerful amplifier. If the data quality is poor, the perfect mathematical rigor of the BOP just amplifies that initial error. The decision flow has to be robust. Predictive models tell the system what the outcomes might be. The optimization model then decides where to commit resources. If those input estimates are volatile or inaccurate, the resulting optimal portfolio becomes incredibly fragile.
So a highly complex model requires an equally sophisticated data pipeline feeding it. Otherwise, you're just optimizing noise.
You're just optimizing noise. Exactly. Hashtag 3.2. Managing trade-offs and opportunity costs. The primary function of the BOP is managing the unavoidable reality of trade-offs. And this brings us right to the concept of opportunity cost. When resources are constrained, every yes is an implicit, forced no somewhere else.
The beauty of the BOP is that it manages this opportunity cost explicitly, not just intuitively.
Precisely. Let's use the capital funding scenario again. You have a budget of $100 million. Project A requires $90 million and offers an expected return of $150 million.
Okay.
Then you have Project B through K, which are 10 small projects, each costing $10 million and offering an expected return of $20 million each.
Right, so if I pick Project A, I have $10 million left. My total portfolio value is $150 million, plus whatever tiny projects I can squeeze in with that remainder.
And that's what most managers would instinctively do, grab the largest individual return first. But the optimization model looks at the remaining opportunity cost. If you select Project A, the opportunity cost is the foregone total value of projects B through K.
And the total return for B through K, if they were all funded, is 10 times 20 million. $200 million.
$200 million.
Wait, so the portfolio with Project A yields $150 million, but the portfolio with just B through K would yield $200 million, while still using the full $100 million budget.
The BOP would ruthlessly select the B through K portfolio and set the variable for Project A to 0, because including Project A, despite its high individual value, consumed the constrained resource, the budget, so inefficiently that it prevented the system from achieving its higher overall maximum. The model understands that the efficiency of resource utilization is paramount.
That's the counterintuitive core of optimization, isn't it? The best solution requires you to exclude individually high-value options if they are resource hogs that starve the rest of the system. It's about maximizing the system's return on every single dollar spent. Hashtag 3.3. Optimization versus the greedy approach.
And this leads us directly to the pitfall we have to avoid. The greedy approach. This is the common simplified decision method people use when they don't have an optimization solver.
So how does the greedy approach typically work?
It's simple. You rank all your options by their individual score, highest profit, highest ROI, lowest risk, whatever, and then you sequentially select them down the list until your resource is fully depleted. It's intuitive, it's easy to defend, and it's mathematically naive.
Let's create a concrete example to really solidify why this fails systemically. Let's assume a $1 million budget constraint, and we're evaluating 4 projects. We've got P1, P2, P3, and P4 with different costs, profits, and ROIs.
A great illustration. So if we rank by the highest individual ROI, which is the standard greedy method, the list order would be P3, then P2, then P1, and P4 are tied.
Okay, so greedy starts by selecting P3. Cost is $250,000, remaining budget, $750,000, profit so far, $450,000.
Next, greedy selects P2. The total cost is now $550,000, remaining budget, $450,000, total profit, $950,000.
With $450,000 left, greedy looks at P1, which costs $800,000, and P4, which costs $200,000. It can't afford P1, so it has to select P4.
Right.
So total cost is now $750,000. Total profit becomes $1,250,000.
And the greedy approach stops there. It has used $750,000 of the budget, leaving $250,000 unused, and it's achieved a total expected profit of $1,250,000.
So the optimization model, it just ignores that greedy ranking entirely and looks for the combination that maximizes total profit. So what would the optimal solution be?
The optimal solution, which is not at all obvious from the ranking, is to select P1, P3, and P4.
Wait, P1, P3, and P4? The costs are $800,000, $250,000, and $200,000. That's $1,250,000. That's over budget. That's not feasible.
You are absolutely right. My mistake. That combination is infeasible because it exceeds the $1 million budget. Let me re-examine the optimal selection given that constraint.
The optimizer has to use the available funds as efficiently as possible without going over that $1 million mark.
Let's see. The greedy outcome we found was P2, P3, and P4 for $1.25 million in profit. Okay, so let's look for a better combination.
What if the model skipped the highest ROI project, P3, and instead went for, say, P1 and P2?
P1 at $800,000 plus P2 at $300,000. That's $1.1 million. Still infeasible. The only other path might be to select P1 alone, which uses $800,000 and yields $1.2 million.
So the greedy outcome of $1.25 million is actually better than P1 alone. But can we beat the greedy outcome? Is there another combo?
We have to check every permutation. The greedy solution, P2, P3, P4, is $1.25 million.
Okay.
What about P1 and P4? The cost is $800,000 plus $200,000. That's exactly $1 million.
Right to the budget limit.
And the profit is $1,200,000 from P1 plus $300,000 from P4, which is $1.5 million.
$1.5 million. That's 20% higher than the greedy outcome of $1.25 million.
Exactly. The optimization model skipped the individually highest ROI projects, P2 and P3, entirely. Instead, it chose the specific combination of P1 and P4 because they perfectly exhausted the budget and by doing so, maximized the total objective value. The greedy approach failed because it didn't look at the entire capacity usage. It just prioritized the immediate local return, which led to an inefficiently used budget.
That's the aha moment. It's not about being individually good. It's about being the perfect piece in the overall puzzle. We've established that BOPs offer a superior strategy, but they introduce a significant real-world challenge: computational complexity. These problems can become mathematically, well, almost impossible to solve in a reasonable time frame.
This is the practical barrier that often separates academic theory from deployable business models. The reason lies in the exponential growth of the solution space.
Can you explain that scale for us?
Sure. If you have n binary decisions, n possible projects or customers or locations, the number of possible combinations is 2 to the power of n. So with 10 decisions, it's 1,024. That's manageable. With 30 binary decisions, you're already at over 1 billion possibilities. Now, let's go back to that marketing problem with 50,000 customers. 2 to the power of 50,000 is a number so vast that simply enumerating all possibilities, brute forcing the solution, would take longer than the current age of the universe, even on the fastest supercomputer we have.
So we can't just check every single combination of ones and zeros. That method is dead on arrival for any real-world managerial problem.
Absolutely. And this is why we need specialized solution methods. We rely heavily on mathematical optimization solvers, which use incredibly sophisticated algorithms designed to find the optimal solution without checking every single path. The most common technique is called branch and bound.
That sounds dense. Can you simplify what branch and bound is actually doing?
Think of the solution space as a massive branching tree. If you start at the top and have billions of branches to follow, branch and bound uses logical mathematical steps to intelligently prune that tree. If the model determines that an entire section of branches, say, all scenarios where project A is selected, cannot possibly lead to an objective value higher than the best solution it's already found, the solver mathematically ignores or bounds that entire section. It just cuts off millions of possibilities instantly without ever checking them.
So it's smart elimination, not brute force checking. It eliminates huge swaths of the problem space because it proves they are either infeasible, meaning they violate a constraint,
Right.
or they are guaranteed to be suboptimal.
Exactly. But even with these techniques, very large or very tightly constrained problems can still take hours or even days to solve to absolute optimality. And this forces a trade-off, especially in time-sensitive situations.
And that's where heuristic methods come into play. Right?
Yes, heuristics are basically approximation techniques. If Branch and Bound is focused on finding the single, mathematically perfect 100% optimal answer, heuristics are focused on finding a 99% or 99.9% optimal answer, but in milliseconds or seconds.
It's like a good enough, fast enough solution.
It's like using a sophisticated GPS. You might want the absolute fastest route, but if the calculation takes 3 hours, you're better off taking the very good route the GPS spits out in 2 seconds. Managers have to balance that desire for absolute optimality against the computational effort and the time required to achieve it. Hashtag 4.2. Evaluating results and sensitivity.
Once the engine provides its optimal list of ones and zeros, management can't just blindly implement it. They need a system for evaluating its quality and its robustness. What metrics do the sources suggest we use?
The evaluation process has to confirm 3 things. First, the total objective value achieved. This is just the score, did we hit the target profit? Second, and most importantly, constraint satisfaction. This is the feasibility check. We have to verify that the selected solution strictly adheres to every single budget, capacity, and policy rule we defined. A solution is useless if it requires resources we don't have.
And the third criterion, practical implementability. This takes us outside the pure math.
Correct. The model might provide a solution that requires highly fragmented selections, like opening 15 tiny microstores across 4 different logistics regions. While that might be mathematically optimal on paper, the sheer complexity of managing those fragmented operations might negate the marginal profit gain in reality. This is where human experience critiques the mathematical optimum.
This leads us into the critical concept of sensitivity analysis. How robust is the solution to real-world uncertainty?
Sensitivity analysis tests the resilience of the recommendation. We have to acknowledge that the inputs, those expected profit values, the centers, are just predictions, not facts. So we systematically change those key input parameters, or we relax or tighten constraints slightly to see if the recommended selection of ones and azeri fundamentally changes.
For example, if our estimate for the cost of raw material for Project A goes up by just 2%, does the entire portfolio strategy collapse and shift to projects B, C, and D?
Exactly. If a small, reasonable fluctuation in cost or expected revenue causes the optimal solution to pivot wildly, that solution is deemed highly sensitive or brittle. A robust solution, on the other hand, should remain largely stable when the inputs vary within an acceptable range. If the solution is brittle, it signals a high-risk strategy because reality will inevitably diverge from our predictions.
So managers should be wary of those solutions.
Very wary. They often prefer a slightly lower scoring but much more robust portfolio. Hashtag 4.3. Managerial interpretation and the human element.
We've saved the most complex part for last. The boundary between the algorithm and human leadership. The optimization model is a ruthlessly rational calculator of value based on its inputs, but it is not a CEO.
And it is absolutely vital that the listener understands that optimization results are sophisticated recommendations, not mandates. The model provides the mathematically superior path to the defined goal, but management has to integrate that result with broader strategic and organizational realities that often cannot be translated into simple ones and edgery or constraint equations.
Let's focus on those strategic priorities that might override the math.
Imagine a scenario where the model recommends closing a division because it consistently yields a 5% suboptimal return compared to others. Purely mathematically, that's the right choice.
Right.
However, strategically, that division might be the only foothold the company has in an emerging geographical market, or it might hold a unique patent that's vital for future product lines. That long-term strategic value, which might be hard to quantify financially today, has to override the short-term cost minimization derived from the model.
Or what about organizational readiness? An optimal solution might require a massive logistical shift closing facilities and relocating inventory across 2 continents at the same time.
The math says it's cheaper and faster. But if the organization lacks the managerial capacity, the IT infrastructure, or the skilled labor force to execute that rapid, complex change without a major failure, then the mathematically optimal solution is practically infeasible. It has to be downgraded or maybe phased in. The human element assesses the organization's ability to actually absorb that change.
This all boils down to transparency, doesn't it? If a manager is being asked to accept a counterintuitive recommendation like skipping a profitable project, like P3 in our example, they need to understand the trade-off.
Transparency and explainability are crucial for organizational buy-in. The managers have to be able to trust not just the objective function, but the constraint structure and the trade-offs the model made. If the analyst can explain, look, we skipped P3 because its $300,000 cost would have made the P1, P4 combination, which yields an extra $250,000 in total profit, infeasible. That fosters trust. Without that transparency, the model just becomes a mysterious black box, and managers will default back to their intuitive and often suboptimal, greedy decisions. Hashtag 4.4. Common pitfalls to avoid.
For our final warnings, let's summarize the common failure modes. Think of it as a checklist for anyone adopting BOP systems. The first one is foundational. Garbage in, garbage out.
This cannot be overstated. GI-GO is often the result of poor communication between the data science team and the managerial team. If the expected revenue estimates are based on overly optimistic market forecasts, or if risk estimates ignore known operational weaknesses, the resulting optimization will be precise, but precisely wrong. The model will find the optimal path through a fantasy landscape, not reality.
The second pitfall is ignoring reality. We touched on this with constraints, but I imagine it often manifests in more subtle ways.
It does. Often logistical or even political constraints are omitted because they're difficult to formalize mathematically. Perhaps there's an unwritten rule that a certain high-profile supplier must be maintained, or a particular state must be serviced for regulatory reasons, even if it's unprofitable. If those human-level constraints are left out, the mathematically optimal solution will immediately run into organizational politics or regulatory law, reducing its real-world value to zero.
And finally, over-engineering. The temptation to make the model infinitely precise and perfectly reflective of every single micro detail in the business.
That temptation is strong, but it creates a maintainability nightmare. Overly complex models require massive computational resources. They take forever to rerun, and they become impossible to audit or explain to stakeholders. If the model takes 6 weeks to update because one tiny parameter changed, it's useless for operational decision-making.
Right.
You have to strike a balance. The model needs enough detail to be accurate, but simple enough to be adopted, maintained, and explained quickly to the people who actually need to use it. If the complexity prevents organizational buy-in, the project fails. Hashtag outro.
So we've completed our journey from the simple yes-no choice to a complex system-level strategic framework.
Yeah.
We've seen how binary optimization modeling uses objective functions, variables, and constraints to maximize strategic outcomes, ensuring that every decision is made in concert with all others, consistently beating that intuitive but flawed, greedy approach.
The ability of this framework to eliminate inefficiency and force explicit resource trade-offs is, well, it's unparalleled. It ensures that when you choose when you select something, you are doing so because that decision contributes to the highest cumulative value across the entire portfolio, not just because it looks good in isolation.
The model provides that verifiable, higher overall value. It provides a kind of certainty in a world of complex trade-offs.
But here's the final provocative thought for you to carry forward. We've demonstrated how sophisticated the optimization model is at calculating profitability, minimizing cost, and allocating capital perfectly. It provides the mathematically superior path to a predefined objective.
But that's the limit.
That's the limit. The model can only calculate value based on the financial and logistical metrics we feed it. It cannot independently weigh strategic risk that hasn't been formalized. It can't assess the human cost of a decision or determine if a cost minimization strategy aligns with the company's long-term brand identity. The ultimate power of binary optimization lies not just in the rigorous mathematics of the solver, but in the intelligent integration of its results into the bigger human and strategic picture. The final yes or no decision, the one that decides whether to follow the algorithm's perfect mathematical recommendation, that is where true leadership and organizational strategy really begin.
Welcome to the Deep Dive. Today we are strapping in for a journey right into the heart of modern decision-making. We're talking about a realm that is so complex, so interconnected, that finding the mathematically perfect answer isn't just difficult, it's often computationally impossible.
Right. We're talking about the problems that, basically run the world. Organizing billions of shipping containers, scheduling millions of airline routes.
Or optimizing a financial portfolio with, thousands of variables?
Exactly. It's what you might call the wall of complexity. When the number of options in a decision space exceeds the number of atoms in the observable universe, and that happens surprisingly fast in real-world logistics or financial modeling, you just need a new strategy.
It's a completely new way of thinking.
Yeah. Traditional, exact methods, they just seize up. They can't handle it.
So our sources for this deep dive focus on the foundational principles and the advanced applications of what's called meta-heuristic optimization. Our mission today is to give you a really crystal clear, structured understanding of this field. We want to highlight exactly why these approximate solutions aren't just compromises, but are often, the most valuable assets a modern organization can have.
I think if you've ever tried to manage a massive project timeline, you get it instinctively. Where every single task depends on 3 other tasks and you're juggling budget limits, people being available.
Right. It's a nightmare.
It is.
Yeah.
So meta-heuristics are a high-level class of general-purpose optimization methods. They're specifically designed for these complex decision problems where the solution space is, as the research always emphasizes, extremely large and highly discontinuous. They're really an acknowledgement that in these high-stakes environments, practical speed has to trump theoretical perfection.
So we're no longer hunting for that single perfect needle in a haystack. We're, building a sophisticated compass and a map to reliably find the best neighborhood of needles.
And you have to do it on a deadline.
On a tight deadline.
Yeah.
And this inherent trade-off, this idea of sacrificing perfection for speed and scalability, that's really the defining feature here, isn't it?
It is. It's the ultimate statement on computational reality. Look, if finding the optimal scheduling solution for a manufacturing plant takes 2 weeks,
It's already useless.
it's obsolete before you can even implement it. The input conditions, a machine breaks down, a material shipment is late, have already changed. So meta-heuristics intervene to find a good, near-optimal solution in minutes, not weeks.
So it delivers 99% of the value, but it does it right now.
Immediately.
Okay, let's unpack this. What does it fundamentally mean to accept and really to embrace that sacrifice of mathematical perfection? It seems to mean we are prioritizing actionability and scalability above all else.
Right. You're recognizing that in these dynamic, changing systems, a timely, actionable decision is just exponentially more valuable than a perfect decision that arrives way too late.
Or never arrives at all.
Or never arrives at all.
So let's start with that big picture then. Why do we even need this whole class of methods? I mean, why can't we just rely on the traditional deterministic techniques? Things like linear programming, which, they guarantee you'll get the optimal answer. What's the specific pain point that forces us into this world of approximation?
Well, the pain point, it comes directly from the inherent messiness of real-world decision problems. They just defy the neat mathematical structures that traditional solvers need. The sources really highlight 3 factors that combine to make those exact methods, impractical, if not completely impossible.
Okay, what's the first one?
First, many of these systems are profoundly nonlinear. In a linear system, it's simple. If I double the input, I double the output. The relationship is predictable, it's clean.
A straight line on a graph.
Exactly. But in real life, biology, finance, logistics, the relationships are complicated. You have feedback loops, emergent behaviors. For instance, a shipping company adds 1 new depot. The cost savings might be minimal. But if they add a second depot in a really strategic location, suddenly the network effects could drop costs by 30%. The relationship is just wildly unpredictable.
And that immediately introduces a level of complexity that, standard calculus just struggles with. If the performance landscape isn't smooth, if it's full of sudden drops and peaks, then those deterministic methods, which rely on finding the slope to guide their search,
You get lost.
they get lost or they just fail to converge. I mean, you can think of a chemical process. Increase the temperature by 1 degree, you might get a slightly better yield. Increase it by 2 degrees, and the entire reaction could fail catastrophically. That's a huge, non-proportional outcome from a tiny change.
Exactly. And that nonlinearity is then compounded by the second factor, which is that these problems involve many constraints and highly interdependent decisions. Think of a large manufacturing firm planning its weekly production. You have constraints on raw materials, machine uptime, labor union rules, environmental regulations, energy costs. The list goes on.
And on top of that, every decision affects every other decision.
That's the interdependence. The decision to produce product A impacts the feasibility of producing product B because they both need the same constrained resource, say a specific high-precision milling machine.
It's a massive interconnected spiderweb.
It is.
You pull on one strand, like a sudden rise in the cost of one raw material, and the whole web vibrates.
Yeah.
You'd be violating 100 constraints downstream without even realizing it.
And traditional optimization, it prefers problems you can break down, where you solve a series of smaller, independent problems.
But you can't break this down.
When everything is interdependent, that decomposition becomes impossible. And this combination, the nonlinearity, the constraints, the interdependence, it leads directly to massive scaling issues. The core limitation of traditional exact methods is their runtime. They promise you that mathematically guaranteed optimal solution.
But there's a catch.
There's a huge catch. The time required to compute that precise solution grows exponentially as the number of variables and constraints increases.
And exponential growth is, as you said, the ultimate system killer. Let's use the classic example of binary optimization, right? Where every decision is just a simple yes or no. If you have, say, 10 decision points, you've got 2 to the power of 10 or 1,024 possible combinations. That's manageable. The computer can do that.
Sure.
But if you increase that to just 50 decision points, like deciding whether to include 50 different stocks in a portfolio, you have 2 to the power of 50 solutions.
And that number, 2 to the 50, is already approaching 1.1 quadrillion.
It's mind-bogglingly huge.
And that's still a small problem. Scale that up to a real-world scenario, a utility company, deciding which 1,000 potential maintenance projects to approve this quarter. You're now dealing with 2 to the power of 1,000 solutions.
Which is a number that's meaningless to us.
It is. It's orders of magnitude larger than the estimated number of atoms in the observable universe.
Wow. Okay,
Yeah.
that really puts the problem size into sharp perspective. You cannot literally enumerate every possible combination,
Yeah.
not even with the world's fastest supercomputer.
The time required would exceed the age of the universe.
So the traditional methods just hit a wall.
Precisely. They either take far too long to compute a precise solution, or they fail to scale when the problem size increases dramatically, which, given the volume of data in modern decision analytics, is the norm, not the exception.
So the meta-heuristic promise is essentially a practical, scalable, and immediate escape from this computational impossibility. They accept that demanding mathematical perfection is actually counterproductive at this scale.
They provide a pragmatic and scalable alternative. They shift the focus from mathematical elegance to, well, utility. They prioritize the speed and practicality needed for real-time decision-making, acknowledging that in these complex systems, a timely, good decision is often far more valuable than a perfect decision that arrives too late.
Or never arrives at all.
Or never arrives at all. The marginal gain of that final 0.01% of optimization is just utterly overwhelmed by the cost of waiting for it.
Okay, now that we understand the absolute necessity, let's break down the mechanics. What are the core characteristics, the foundational DNA, if you will, that define a meta-heuristic method and, differentiate it from a simple deterministic algorithm?
Yeah, the field is really built upon 4 defining pillars. These give the methods their power and their flexibility.
Okay.
First, they are problem independent, and this is a huge design advantage. Unlike an algorithm that's tailored specifically for scheduling nurses, for example, a meta-heuristic provides a high-level framework, a strategy that you can apply to vastly different problems.
So you can use the same underlying structure for completely different things.
That's right. You can use, say, a genetic algorithm to optimize flight schedules one day and circuit board layouts the next. You just have to change the objective function and the constraints.
So it's transferable technology. The power isn't in solving one specific math problem, but in providing a sort of universal framework for navigating these enormous search spaces.
That's it, exactly. The second characteristic is that they are iterative. They don't just jump straight to the answer. They start with an initial guess, they evaluate it, they refine it slightly, evaluate the new one, and just repeat this cycle over and over.
And they improve gradually.
They gradually improve solutions over successive cycles until a stopping criterion is met.
What would that be? A time limit?
It could be a time limit, or it could be realizing that no further significant improvement is possible.
This iterative nature, it makes a lot of sense for complex landscapes. It's like a gold prospector, right? They start digging where the ground looks promising. And with every shovel of dirt, they check the quality and they adjust their next dig based on what they just found.
That's a great analogy. And this leads directly to the third and maybe the most fascinating characteristic. They are stochastic. They intentionally incorporate randomness into their movement.
Okay, wait.
And this isn't a sign of weakness. It is a critical design feature used to explore the vast solution space effectively.
Randomness as a core feature. That feels so counterintuitive if your goal is optimization. I mean, if the goal is to find the highest point, why would you ever take a random step down?
That's a fantastic question, and it really speaks to the sophistication of the approach. If the algorithm were purely deterministic, if it always took the step that looked best locally, it would quickly and reliably get stuck in a rut. stochasticity, that randomness, it allows the algorithm to occasionally take a non-optimal, risky jump.
So it can escape those ruts.
It can. This controlled randomness is the tool it uses to break free from comfortable, mediocre solutions and explore areas that might look unpromising at first, but could hide the global optimum.
So it's not just pure randomness, it's guided randomness.
Precisely.
It's not throwing darts blindfolded. It's making a calculated risk that a brief, non-optimal detour might lead you to a vastly superior area you didn't even know existed.
Exactly. And the degree of randomness is very carefully tuned. It often starts high to encourage broad exploration, and then it slowly decreases as the algorithm starts to converge on a good area to focus more on local exploitation. And that brings us to the final pillar. They are approximate. They explicitly aim for near optimality. They prioritize speed and practicality. They trade the certainty of the best solution for the speed of a really good solution.
So those 4 pillars: problem independent, iterative, stochastic, and approximate. That's the meta-level strategy.
That's what guides the underlying search, yes.
Let's discuss that search in detail, because this is where the algorithmic intelligence really shines. Since we can't examine every single point on this continent-sized solution landscape, the algorithm has to be smart about how it moves.
And that search process is fundamentally driven by this constant internal struggle. It's a balance between exploration and exploitation. This is the central critical trade-off that dictates the quality and the stability of the final result.
Okay, here's where it gets really interesting. Let's define those 2 forces. What is exploitation?
Exploitation is the intense, localized refinement phase. So once the algorithm stumbles upon a promising peak, a relatively good solution exploitation means making small, incremental changes to improve that specific solution.
It's like digging deeper into a known gold vein.
That's it. Meticulously extracting maximum value from a resource you've already identified.
So if the algorithm finds a schedule that's, say, 90% efficient, exploitation would be tweaking the start times of a couple of tasks to push that to 91 or 92%. It's local maximization.
Yes. But if you only exploit, you risk what we talked about earlier, getting stuck in a local optimum.
Right.
If the algorithm spends all its time refining a hill that only reaches 92%, it will never find the mountain peak over there that reaches 98%. And that's where exploration comes in.
Okay.
Exploration is the search for entirely new, potentially distant regions of the solution space. It means the algorithm has to sometimes ignore the immediate reward and deliberately make a long, non-optimal jump to a completely different area of the landscape.
Checking for higher ground somewhere else.
Exactly. And this is where that stochastic, that random element is deployed most aggressively.
And the consequence of an imbalanced search is that really troublesome phenomenon.
Yeah.
Getting stuck in a local optimum. This is the failure mode of optimization, right?
It is. A local optimum is a solution that is, undeniably better than all of its immediate neighbors. So if an algorithm is only capable of exploitation, of only climbing uphill, once it reaches this small, satisfying peak, it looks around and finds every possible next step goes downhill.
And so it stops. It thinks it's done.
It concludes it has found the best solution and it terminates prematurely.
But the reality is that the true global optimum, the highest possible peak, is hidden behind a valley or a ridge. It requires the algorithm to take a few steps down first to get to the path that leads up the higher mountain.
That's the exact challenge. The primary goal of balancing exploration and exploitation is to make sure the algorithm has enough energy or enough controlled randomness to jump out of those deceptively good local optima. If an algorithm is too focused on exploitation, it converges too fast to a mediocre result.
And if it's too focused on exploration,
it just wanders aimlessly, it wastes computational cycles, and never properly refines a good solution it might stumble upon. The tuning of this balance is genuinely an art form. It relies heavily on the structure of the metaheuristic you choose. So moving from that abstract strategy to the concrete implementation, we have to talk about how the algorithm actually judges its own progress. I mean, how does it know what better actually means? And this is entirely defined by what we call the guiding light, the objective function.
This is the engine's dashboard. It's the sole measure of success or failure.
Precisely. The objective function is the mathematical definition of the goal. It has to encapsulate everything we're trying to maximize, like profit or efficiency, or minimize, like cost or risk. So every time the algorithm generates a new candidate solution, a slightly different schedule, a new portfolio mix, it runs that solution through the objective function to get a score.
So if we're optimizing a complex delivery route, The objective function might be minimizing total fuel cost plus driver hours, but subject to certain delivery windows. Every new proposed route gets instantly scored by that function.
And that score is the feedback loop that guides the iterative search. Metaheuristics repeatedly evaluate this function to figure out the best search direction. But critically, the quality of the final result depends entirely on properly defining that objective, on ensuring a meaningful cost-benefit representation.
And this is where the human element comes in.
This is where human bias and human error enter the system. If you fail to account for the true cost of, say, customer dissatisfaction or regulatory risk,
The algorithm doesn't care.
the algorithm will ruthlessly optimize for maximum short-term profit, even if that means destroying long-term brand equity.
And that's a really profound point for you to think about. If your initial definition of value is flawed, the entire exercise, no matter how powerful the algorithm, yields a misleading or even dangerous result. It's that concept of garbage in, optimal garbage out, but realized through very sophisticated math.
Absolutely. If a financial algorithm optimizes only for high historical returns, but ignores sudden massive liquidity risks because the objective function didn't properly penalize them.
Then the optimized portfolio is just a high-risk time bomb.
Exactly. The human element of correctly defining the objective function is the non-negotiable prerequisite for any successful metaheuristic deployment.
Okay, so once we have that guiding light, we have to deal with reality. Constraints. Real-world problems are never free-form. They are bound by hard limits, budget limits, time windows, capacity restrictions, strict policy rules. The algorithm has to respect these, or the solution is useless.
Right. If the optimization suggests a flight path that requires more fuel than the plane can carry, or a scheduling arrangement that violates mandatory labor rest periods, that solution, no matter how high its objective score, is called infeasible. Managing that infeasibility is a core design step.
So how does an algorithm handle a move that, by all its metrics, looks great, but it violates a budget limit?
Well, our sources detail 3 main design choices for handling these infeasible solutions, and the choice you make heavily impacts the search behavior.
Okay, what's the first one?
The first is penalizing. This is the most common method. If a solution violates a constraint, a significant cost or penalty is applied directly to its objective function score.
So that just makes it look worse to the algorithm.
It effectively lowers the score of that solution. So if your goal is to maximize profit, say $100,000, but the proposed solution exceeds the budget by $5,000, you might subtract, I don't know, $50,000 from the profit score as a penalty.
And that mathematically just shoves the algorithm away from that infeasible region. It teaches it that the cost of breaking the rules is way higher than any marginal gain it thought it was getting.
Correct. The algorithm will quickly learn that a feasible solution with a score of $90,000 is preferable to an infeasible one with a pre-penalty score of $105,000 that gets penalized down to $55,000.
It seems simple and flexible.
It is, but it requires very careful tuning of that penalty factor. If the penalty is too small, the algorithm might just decide to violate constraints whenever it feels the reward is high enough.
Okay, what's the second strategy?
The second is repairing. So instead of just punishing an infeasible solution, the algorithm actively adjusts it until it satisfies the constraints. For instance, if the optimization suggests assigning a driver 70 hours of work, violating the 60-hour rule, the repair mechanism would automatically reduce the assigned hours to 60. It makes it feasible before its new adjusted score is evaluated.
That sounds really practical.
Yeah.
It ensures the solutions being evaluated are always grounded in reality,
Sure.
and you get to keep the good parts of the generated solution. You just trim off the parts that break the rules.
It is practical, but it's much more complex to implement because the repair mechanism needs deep domain knowledge. And also, repair mechanisms can sometimes introduce a local bias. The way you choose to fix the problem might inadvertently guide the search to a suboptimal area. The repair step itself is a form of local exploitation.
I see. And the third strategy?
The third is restricting search. This is the most aggressive approach. Here, the algorithm is designed from the very beginning, in its movement operators, its generation methods, to only search within the feasible regions.
So it's literally impossible for it to even generate a solution that violates a constraint.
Exactly. If the capacity limit is 100 units, the mechanism that generates the next candidate solution cannot propose 101. It saves computational time by ignoring the impossible space entirely.
But I can see a downside there. It could be very rigid.
It can create significant rigidity. If the constraints define a very narrow, complex, feasible region, restricting the search can severely limit the algorithm's ability to explore. It might prevent it from moving from one feasible area to a distant, superior feasible area because the path between them might require temporarily stepping into an infeasible zone.
A detour that's forbidden by design.
Right. So constraint handling isn't just a technical choice, it's a strategic decision about how the algorithm will perceive and interact with reality.
That complexity makes a lot of sense. So let's synthesize these elements: the objective function, the exploration-exploitation struggle, the constraint handling into the two common high-level architectural approaches that we see. First, we have the local search-based methods. As I understand it, these start with just one initial solution, and the whole process focuses on improving that single solution. It's like a lone hiker, right? They only care about their current coordinates and their immediate surroundings.
That's a great way to think about it. Methods like taboo search or simulated annealing operate this way. They focus intense exploitation on a single point until it can no longer be improved.
Okay, and the other approach?
And then we have the much more complex population-based methods. These methods maintain multiple solutions simultaneously: a swarm, a team, a colony. They work by combining, mutating, and evolving these solutions over time. So solutions compete, but they also collaborate by sharing information about the good areas they found.
The population-based methods, things like genetic algorithms which mimic natural selection, or particle swarm optimization which mimics bird flocking, they intrinsically promote exploration, don't they?
Absolutely. Because you have multiple solutions actively searching different parts of the landscape at the same time, the likelihood of all of them getting trapped in the same local optimum is just drastically reduced. If one individual finds a small peak, it exploits it locally, but the rest of the population is still free to explore for a globally superior solution.
That's distributed knowledge.
Which makes them exceptionally robust against local optima. Local search is the specialist, population-based methods are the generalists, covering more ground simultaneously.
Let's pivot now to actionability. We've established the technical necessity, but how does this advanced framework actually bridge the gap into the decisions that managers have to make every day? What's the vital, actionable role of metaheuristics in the modern decision analytics pipeline?
Their role is to turn abstract data into concrete strategy. They are absolutely critical when, as the foundational texts always stress, binary optimization becomes too large, or when the decision interactions are highly complex. When a business has thousands of potential levers, yes-no choices to pull, the traditional methods break, and the system just reverts to, gut feel heuristics.
And metaheuristics provide a mathematically guided, scalable way out of that problem.
They do.
So this is the bridge that transforms predictive insights into executable strategy. If I have a sophisticated model that predicts consumer risk, that's great, but I still need a tool to tell me which loans to approve and how much to lend across my whole portfolio to maximize my profit while respecting my risk limit.
Precisely. Predictive models tell you what might happen: the probability of default, the expected return of an asset, the likelihood of a machine failure. Metaheuristics take those probabilities and expected values and convert them into the concrete decision. In order to meet objective X, you must take actions A, B, and C. They answer the "what should we do next" question.
Okay, let's look at some specific applications. Where might someone listening encounter these methods, maybe without even realizing it?
Sure. A great one is marketing campaign selection. A large retailer might have 5 million customers and, say, 100 different promotional offers. The goal is to decide which customer gets which offer to maximize the overall response rate and total revenue.
While also minimizing the cost of printing and mailing.
Exactly. This is a massive binary optimization problem. Should customer X get offer Y? Yes or no? Metaheuristics can find the near optimal matchings in minutes, rather than the days it would take otherwise.
Another powerful example has to be resource allocation. That's core to supply chain and logistics.
Oh, absolutely. Think of a major utility company needing to allocate 500 repair crews across a huge metropolitan area. They have to consider travel time, the specific expertise needed for each job, the severity of the outages, contractual limits on overtime.
It's not a linear process.
Not at all. It's a massive, multi-dimensional allocation puzzle, perfectly suited for metaheuristics.
And then there's complex scheduling problems. Airline fleet scheduling is the textbook example, isn't it?
It is. You have to optimize crew assignments, aircraft routing, maintenance schedules, gate assignments, all while respecting FAA regulations, union contracts, and minimizing delays.
And everything is connected. Delaying one plane messes up the whole network.
And solving this daily optimization is really the only way modern airlines can operate efficiently.
And in finance, the well-known application is portfolio selection.
Right. An investor isn't just seeking high returns, they're balancing. They want the optimal mix of investments that maximizes return subject to strict regulatory capital requirements, market liquidity limits, and a defined acceptable volatility level.
And that complex balancing act is just too intricate for simple rule-based systems. It demands a sophisticated meta-heuristic search to find that optimal balance point.
Right, on the efficient frontier. So the structure of modern analytics is really defined by this integration. It's a linear three-stage process. Prediction feeds optimization, which yields the decision.
So the first stage is the predictive models. Machine learning, statistical techniques. They crunch the historical data, market trends, risk profiles. Their output is the raw input for the next stage.
It is. It's the probabilities of success, the expected profits, the risk estimates associated with various potential decisions. They tell us what might happen in the future under certain conditions.
Then stage 2 is the optimization engine, powered by our meta-heuristics. It takes those predicted inputs, the expected profit of assigning crew X to route Y, and starts its iterative search.
Right. It explores the solution space, constantly evaluating the objective function and respecting all the constraints. It finds the highest scoring set of actions possible within the time limit.
The result is stage 3, a decision recommendation, the tangible output, the specific optimized schedule, the precise allocation plan, the exact recommended portfolio mix.
And that full pipeline prediction optimization decision is how organizations scale business strategy. It allows them to automate and optimize decisions that were once just too slow or too large for human teams to handle.
And that provides a measurable competitive advantage through both speed and scale. As we start to wrap up, we have to return to the central human challenge of this field. Since we are acknowledging that these solutions are approximations, how do we confidently evaluate them? And maybe more critically, how do managers who are ultimately accountable for the outcomes learn to trust decision recommendations that are rooted in intentional randomness?
And that brings us right back to the trade-off, which has to be managed transparently. Meta-heuristics explicitly sacrifice guaranteed optimality for faster solutions, scalability, and flexibility. And trust, it relies on robust, quantifiable evaluation metrics.
So if we can't compare the result to the mathematically perfect answer, what yardsticks do we use?
Well, we rely on three primary criteria. First, the most straightforward one, the objective value achieved. This tells us the score, the magnitude of profit maximized or cost minimized, based on the definition we built into the objective function. This gives us the absolute benefit.
Okay, that makes sense.
Second, and this is crucial because of the stochastic nature, we examine stability across runs. If you run the same algorithm 10 times with identical inputs, you will get 10 slightly different near-optimal solutions. A successful meta-heuristic shouldn't produce wildly different results.
You're looking for tight clustering.
Exactly. Meaning all 10 solutions reliably land in the same high-value neighborhood of the solution space. High stability confirms that the algorithm is robustly identifying the best areas of the landscape.
Because if the algorithm sometimes lands on a 95% efficiency solution and sometimes on a 60% efficiency solution, that instability is a huge red flag.
It's a major warning sign that the tuning is incorrect or the algorithm is failing to manage that exploration-exploitation balance.
So the random element is overpowering the guidance system.
Exactly. And the third criterion, simple but vital, is constraint satisfaction. Was the solution actually feasible? Did it stick to the budget limits and policy restrictions? We have to always ensure the recommended action is practical.
Beyond the algorithm's own performance, we also have to account for the reliability of the inputs themselves. I mean, the predictive insights feeding the optimization are just estimates. They have their own uncertainty. How do we make sure our final decision holds up if those predictions are slightly wrong?
That's where you need to do a deep sensitivity analysis. This process systematically assesses how robust the proposed optimal decision is to variations in the input data. We might deliberately perturb the input parameters, increase the predicted cost of fuel by 10%, or decrease the expected demand for a product by 5%, and then rerun the optimization.
And what are you looking for?
You're looking for brittleness. If a small change in an input causes the recommended decision to dramatically flip, say, changing the optimal portfolio mix from 80% bonds to 80% stocks, then that solution is extremely brittle. It carries a high inherent risk.
Whereas a robust solution adjusts gracefully.
Right. And sensitivity analysis gives the technical team and management a critical understanding of the decision's risk exposure.
And this moves us firmly into the human realm, the managerial interpretation. The results are recommendations. They're not divine mathematical truths. For these powerful tools to move beyond being a technical curiosity and actually get integrated into business strategy, managers have to trust them.
And that trust is forged through radical transparency and education about the inherent limitations. Managers have to understand 4 critical factors to feel comfortable. First, they must fully know the underlying assumptions used in the model. Were market conditions assumed to be stable? Was labor supply assumed to be infinite?
You have to make simplifications, but they have to be documented and understood.
Right. Second, they need to grasp the inherent trade-offs that were made. The manager has to be comfortable with the fact that they traded that final marginal increase in profit for the speed and agility of getting the answer this afternoon.
If they think they're getting a perfect solution, their expectations are misplaced, and trust will eventually break.
Third, they must also grasp the uncertainty surrounding the result, which is why stability analysis is so important. Instead of presenting a single recommended number, the technical team should show the manager the distribution of the 10 best solutions, that cluster of high-quality outcomes.
Which allows the manager to choose. They could pick the most risk-averse option or the most aggressive one within that validated high-performance neighborhood.
And that leads to the final point. That transparency in explaining these factors, assumptions, trade-offs, and uncertainty is the absolute key to increasing adoption. If the technical team can't clearly articulate why the stochastic method arrived at this solution and what risks are inherent, the manager will just treat it like a dangerous, unpredictable black box.
And they'll revert to simpler but suboptimal rule-based decision-making.
Yeah. But we should also be candid about the limitations and risks inherent in the approach. First, we have to accept that results will vary across different runs due to randomness. This requires a communication shift away from deterministic thinking.
Which is a major change from traditional systems, where the result is always the same. It requires managers to accept a bit of calculated uncertainty.
It does. Second, these methods require extremely careful parameter tuning by experts. The performance of, say, a particle swarm optimization algorithm is acutely dependent on its internal settings, the inertia weight, the acceleration coefficients, the population size.
You can optimize the optimizer poorly.
You can, and that can lead to wildly unstable solutions or convergence to a poor local optimum, even if the underlying problem definition is perfect.
And
third, we have to reiterate the critical dependency. If the objectives are poorly defined, if critical elements of cost or benefit are missing or misrepresented, the resulting solutions will be misleading no matter how powerful the algorithm is.
the complexity of the algorithm just magnifies the initial flaw in the problem statement.
Exactly. And ultimately, they are often harder to explain to non-technical stakeholders compared to simple rules. Explaining why a truck routing system chose route A is easy if the rule is choose the shortest distance.
But explaining why a simulated annealing algorithm chose route B.
That involves discussing randomized uphill moves, temperature schedules, and objective function penalties. It's a much harder conversation that demands a higher degree of trust and technical literacy from the management team.
What an illuminating exploration. To briefly summarize our deep dive then, meta-heuristics are not just a technical optimization tool. They are the fundamental necessity for navigating the kind of immense computational complexity that's inherent in modern logistics, finance, and resource planning.
Right. They utilize iterative, stochastic, and general-purpose methods to convert raw, predictive data risk estimates, probabilities, expected costs into fast, scalable, near-optimal decisions. And by mastering that delicate balance between exploration and exploitation, and by rigorously defining the objective function and the constraint handling, they provide the practical solutions that keep these massive, complex systems running efficiently every single day.
And the core takeaway for you, the listener, is that in environments where computational impossibility is the reality, the timely good decision, the meta-heuristic recommendation, is just exponentially more valuable than the perfect solution that remains forever out of reach. These methods are what enable complex strategic decision-making in the age of big data.
Now, for a final provocative thought for you to consider. Given that metaheuristics intentionally prioritize speed and scalability over guaranteed mathematical perfection, and knowing that their results will inherently vary across multiple runs, what minimum threshold of stability, that tight clustering of high-quality solutions, must a decision recommendation meet before a manager can ethically deploy it? And if that threshold is met, how does the organization ensure continuous human monitoring is integrated into the system? How do you effectively build a safety net around intentional randomness to ensure that the system never converges and gets stuck on an undiscovered, disastrously poor local optimum?
How do you build a safety net around intentional randomness? That is a deep question indeed. Thank you for diving deep with us into the world of metaheuristic optimization. Until next time.
Welcome back to the deep dive. Today, we are tackling really the fundamental challenge of decision-making, which is that the future is uncertain.
It always is.
Always is. And when the stakes are massive, and we're talking about, huge stakes like trillion-dollar investment portfolios, global supply chain integrity, or even the design of macroeconomic policy, you just can't rely on gut feeling.
No, or even on certainties, because there are none.
Right. You have to rely on the cold, hard logic of probability.
Exactly. I mean, when we talk about optimizing decisions, making the best choice possible given a set of constraints, we just can't assume a single known outcome. It's impossible.
So what's the alternative?
The core of decision analytics is making optimal choices under uncertainty. And since almost all advanced economic forecasts, financial models, operational projections, they only provide probabilistic information.
They give you a range of outcomes, not a single point.
Precisely. They never give you ironclad certainties. So risk isn't something you can just ignore or, vaguely factor in. It has to be quantified. And then it has to be incorporated explicitly right into the rules we use to figure out what optimal even means.
Okay, so I think that really sets up our mission for today. We're going to unpack how sophisticated decision analytics takes these broad, messy probability distributions.
All these possible futures.
Right, these predictions of what could happen and turns them into actionable, concrete rules that govern massive systems.
Right.
The goal is really twofold, isn't it? We need to control risk on the operational side, and we need to balance expected returns against the, frankly, terrifying prospect of downside losses on the financial side.
That's it.
And we're going to do that by looking at two essential analytical tools that let organizations do this. Chance constraints, which are all about managing the likelihood of failure, and then value at risk, which is about managing the magnitude of that loss.
In short, yeah, we're exploring the formal difference between asking two very different questions. First, can we design this system so that it only fails, let's say, 1 day out of 20?
Okay, the probability of failure.
Right. And the second question, if it fails on that 1 day, what's the maximum amount of money we can reasonably expect to lose? These two questions, they drive institutional behavior across the entire globe.
Okay, let's unpack this. Let's start with that first idea, with chance constraints. We're starting with this fundamental concept of allowing for a controlled amount of risk tolerance.
A structured measure of wiggle room.
Exactly, wiggle room, right in the optimization model itself. Because I guess if we insist that systems be 100% robust against all known uncertainty, well, they become too expensive or too slow.
Or just too conservative to be competitive. That's the pivot point. We start with the definition of chance constraints, or CCs, as they're often called. They are, at their heart, probabilistic constraints inside an optimization problem.
And to understand them, you have to contrast them with the standard deterministic kind of constraint.
You have to. In a deterministic model, if you state, the weight limit on this fridge must be less than 10 tons, that has to hold true 100% of the time. There is zero tolerance for failure.
A hard line. Dictated by physics or maybe by a regulation.
Precisely. CCs, they throw that deterministic mindset out the window when your inputs are uncertain. The crucial point here, really, is that they require a constraint to hold true, but only with a specified high probability.
Not 100%.
Never 100%. It's a formal mathematical acknowledgement that in complex real-world systems, where you're dealing with uncertain inputs like future commodity prices or volatile demand curves or, unpredictable weather patterns demanding 100% certainty, actually forces the system to operate suboptimally.
Okay, let's try to make that definition really concrete. Let's use a familiar scenario, maybe in infrastructure planning. So imagine a city is planning its water supply system.
Okay.
A deterministic constraint would be something like the reservoir capacity must always meet peak summer demand.
Which Sounds reasonable, but
It's incredibly expensive to guarantee that for the absolute worst-case heat wave that might happen once a century. So a chance constraint changes that. It would say something like, ensure the total reservoir capacity is sufficient to meet peak demand with, let's say, at least 99% probability.
and that 99% is the absolute heart of the decision. It means the planners have explicitly accepted a controlled 1% risk of a water shortage violation.
A 1% chance they might have to ask people not to water their lawns.
Exactly. That 1% is the mathematically useful tolerance for failure. And why is it useful? Because seeking the system design that guarantees 100% compliance might require doubling the construction budget and delaying the project by years.
Which has its own costs.
Huge cost. By accepting that small calculated risk, the decision maker can find the most optimal, often the cheapest or fastest or most resource-efficient solution that still respects a very, very high safety margin.
So that gets to the why. Why are CCs used? What's the core utility that makes accepting a 1% risk of failure, better than demanding 0% risk?
It's largely a matter of efficiency and scope. First, they allow decision makers to explicitly control risk levels. They do this by selecting the alpha level, 90%, 95, 99.
So you can dial the risk up or down.
You can dial it up or down, and this can be directly tied to an organization's actual risk appetite. Second, by allowing you to tolerate small probabilities of constraint violation, you massively, and I mean massively, increase the solution space.
The number of possible good answers.
Right. Think of it geometrically. Strict constraints define a tiny, often unrealistic area of feasible solutions. CCs open that area up, making more efficient, more profitable, and just more real-world applicable solutions possible.
Because if the constraints were strict, if we demanded 100% certainty that, for instance, a manufacturing plant never runs out of a key component,
You'd go broke.
the constraints would just be so restrictive, the capital investment needed would be too high to ever generate a positive return. You'd have to build these massive, inefficient inventory buffers, redundancy in every single supplier route.
You'd operate in constant fear of the worst-case scenario.
Yes.
And that's no way to run a business. CCs move the optimization problem out of the world of perfect, known data and into the probabilistic world of real commerce, where inputs are dynamic, they're uncertain, and they're probabilistic. We're not optimizing based on an average anymore. We are optimizing based on an entire range of forecasted possibilities.
And illustrating where this idea gets applied, this concept of probabilistic feasibility is. It's incredibly relevant for you, the listener, because it really underpins massive organizational decisions. Let's start with the obvious one, investment and portfolio optimization.
A classic case.
A portfolio manager isn't just trying to maximize return. They are maximizing return while ensuring their risk exposure, usually measured by things like drawdowns or volatility stays within a regulatory or maybe an internal limit 99% of the time.
And it stretches so far beyond finance, it goes deep into core operations. You can consider capacity planning under demand uncertainty.
Okay, like a big retailer.
A major retailer, yeah. They don't know precisely how many units of a specific seasonal product they're going to sell next quarter, but they have a robust forecast distribution.
A range of possibilities.
A range of possibilities. So a CC might be set to ensure that their warehouse and delivery capacity meets demand with 95% probability. That 5% chance of a stock out is a calculated commercial risk.
And it allows them to avoid, costly overcapacity.
Massive, costly overcapacity that would just eat into their profits.
And we see it in supply chain management all the time. If you need to source critical microchips from a global supplier, you just can't guarantee a delivery date 100% of the time.
Not with geopolitics, logistics, choke points, port congestion.
Impossible. So a CC allows the company to select the supplier and the transit route that ensures delivery by the deadline with, say, 98% certainty. And in doing so, they avoid the immense costs and time penalty of choosing some ridiculously slow but theoretically 100% safe routing option.
Absolutely. Yeah. And you can extend that to large-scale system reliability. If you're designing an interconnected power grid, you cannot ensure 100% uptime, especially not against a catastrophic failure of a major generator or a transmission line.
The costs would be astronomical.
Unthinkable. So you use CCs to design maintenance schedules and redundancy buffers that ensure the grid remains operable and can satisfy demand with, say, 99.9% probability. That tiny 0.1% chance of a blackout is modeled and it's quantified. This is how sophisticated engineering balances resilience with cost.
So what's the core benefit here? Why choose CCs, which sound like they require some pretty complex mathematical assumptions, over simpler approaches like, I don't know, just using a worst-case scenario buffer?
Well, the primary advantage is the explicit incorporation of uncertainty into the decision itself, rather than handling it as some kind of error term or an afterthought. CCs force the decision maker to confront the entire probability distribution right up front.
And they're better than worst-case planning because
Because worst-case scenarios are often statistically so improbable, they're economically paralyzing to plan for. CCs allow for those efficient, slightly risky, optimal solutions we talked about. They just fundamentally align better with the reality that, in the modern world, inputs are probabilistic.
But this power, it has to come at a cost. When we were discussing the importance of the model's assumptions, you mentioned this massive reliance on accurate probability distributions. Let's really delve into that trade-off. Why does the math suddenly get so complex when we introduce probability?
It gets very complex.
And maybe more importantly, what happens if our statistical model is just wrong?
The trade-offs are significant, and that's probably the most critical point. Let's start with the math. Why are CCs computationally complex? Well, when you introduce uncertainty, your constraint is no longer a simple linear inequality like x is less than 10. It becomes an expected value or an integral over a distribution. To solve this problem using standard optimization algorithms, you have to somehow transform that probabilistic statement, the constraint must hold 95% of the time, into a solvable deterministic equivalent.
So you have to translate it back into a hard line.
Exactly.
In a hard line that already has the distribution of uncertainty sort of baked into it.
Precisely. And this often requires complex mathematical techniques, which can result in nonlinear or non-convex optimization problems. These are notoriously difficult to solve, especially when you have hundreds or thousands of decision variables.
So you need special tools.
Highly specialized algorithms and immense computational power. A simple deterministic linear optimization problem might solve in seconds. The same problem with CCs might take hours or even days, which makes them less accessible for smaller organizations or for any kind of real-time decision-making.
That immediately implies a real-world cost. You need time, specialized software, and expert modeling talent.
Absolutely. But the second, and I'd argue far more insidious, trade-off relates to the assumptions. CCs require assumptions about probability distributions. You have to assume, for example, that the future return on a particular asset is normally distributed.
The classic bell curve.
The classic bell curve.
But we know, especially in finance, the normal distribution is often a really poor fit for reality.
It's a dangerous simplification. In real life, particularly in finance and in extreme operational scenarios, distributions have what we call fat tails.
Meaning extreme events are more common than the model predicts.
Much more common. Imagine if human height followed a perfect normal distribution. The chances of finding someone 10 feet tall are practically zero. But in financial markets, the chances of a massive 10 standard deviation market crash, a black swan event, they happen far, far more frequently than the normal distribution would ever predict.
So you're building this sophisticated operational plan based on the neat and tidy bell curve, but the actual real-world volatility behaves more like a monster truck rally.
That's a great way to put it. If your assumption about the probability distribution is wrong, if the true distribution has fatter tails, your entire model just collapses. That CC you set to ensure success 95% of the time might, in reality, only be ensuring success 70% of the time.
Wow.
You've dangerously underestimated your risk exposure because your foundational statistical assumption was flawed from the start.
And finally, let's circle back to that sensitivity. You mentioned it earlier. If I'm a manager and I switch from a 90% confidence level to a 99% confidence level in my capacity planning, am I just tweaking a single number in a spreadsheet, or am I potentially changing the entire optimal physical design of my system?
Oh, you are changing the entire solution set. You could be mandating a complete operational overhaul. Moving from 90% to 99% radically restricts the feasibility space.
How so?
Well, if 90% confidence allows you to rely on a single, efficient shipping route, 99% might suddenly force you to purchase contingency insurance, maintain redundant inventory buffers on 3 different continents, and secure 3 backup suppliers.
Wow.
That single percentage point increase in required confidence radically shifts the optimal solution toward conservatism. It highlights just how extraordinarily sensitive these models are to the risk manager's initial decision. The choices being made, the capacity being built, the capital being allocated, are precise mathematical reflections of those chosen probabilities.
So to sum up this first part, chance constraints are this powerful but mathematically demanding tool. Therefore, managing feasibility, ensuring we meet our operational requirements most of the time, while allowing for a controlled, small, and calculated probability of failure. But it's all based on these complex distributional assumptions that you have to get right.
That's the heart of it.
Okay, so now we need to shift focus entirely. If chance constraints are about optimizing feasibility under uncertainty, now we need to talk about measuring the magnitude of the loss if things do go wrong.
Right.
We are transitioning to value at risk, or VAR. And this is probably the most globally recognized metric of institutional risk out there.
VAR is absolutely the ubiquitous language of risk, especially in finance and regulation. The core definition is this. VAR is a quantitative risk measure that estimates the maximum expected loss over a given time horizon at a specified confidence level.
And critically.
Critically, it translates all the complexity of market volatility, correlation, and probability into a single, straightforward dollar figure.
And that VAR interpretation is what gives it its immense power. Let's take that specific phrasing from the source. There is a 95% probability that losses will not exceed X over the next month. It's so direct.
It is.
It provides that single, easily interpretable number, X, which represents the downside risk. So if my portfolio's monthly 95% VAR is $10 million, the institution knows that, 19 out of 20 months, they shouldn't expect to lose more than $10 million.
It's the ultimate metric for communication and for compliance. It allows executives, boards, and regulators to ask a simple, understandable question. What is our maximum probable loss in dollar terms? And get a single, digestible answer.
And I imagine that standardization and ease of interpretation is what drove its adoption.
Completely, especially in the wake of all the financial instability in the 1990s.
So for you to calculate that single number, X, there are 3 non-negotiable components that you absolutely have to specify. What are those?
Absolutely. Without these 3 components, the VAR number is completely meaningless. First, you need the specified confidence level. That could be 95%, 99%. It's the percentage of outcomes you are trying to capture or, well, survive.
Okay, so confidence level, what's second?
Second is the specific time horizon. Is it daily, 10-day, monthly? VAR is time dependent. A loss measured over a year will always be larger than a loss measured over a day, all else being equal.
And third?
Third, and this is the most foundational, is the loss distribution. This is the range of possible profit and loss outcomes that you derive from either your economic forecasts or your historical data.
It really seems like that single interpretable measure of downside risk is its killer application. Why did VAR become the global standard, especially in the regulatory environment?
Well, its importance really stems from its widespread adoption by institutions and, critically, by regulators, especially following frameworks like the Basel Accords. Regulators are tasked with ensuring that financial institutions can withstand volatility.
And VAR gives them a number to work with.
It gives them a number. They often mandate that banks hold capital reserves sufficient to cover their calculated VAR at a very high confidence level, typically 99 or even 99.9%.
So it's not just a descriptive measure of risk, it's actually a prescriptive measure that dictates mandatory capital requirements.
Precisely. It allows for regulatory oversight, and importantly for the firm itself, it facilitates the comparison of risk across wildly different asset classes or decision alternatives.
How so?
Well, if investment strategy A has a 99% VAR of $5 million and strategy B has a 99% VAR of $8 million, the risk manager can immediately quantify and compare the relative downside exposure inherent in both of those choices.
Okay. So to calculate this X figure, institutions rely on statistical models and forecasts. Our source outlines 3 primary estimation methods. We should probably go into some detail about how these work, and I think critically their inherent reliance on assumptions.
Yes, the 3 common methods differ primarily in how they generate that critical loss distribution.
Okay, what's the first one?
The first is historical simulation. This is the easiest one to grasp. You simply look at what happened in the past and assume the future will look pretty much like it.
So you just look backwards.
You look backwards. If you want a one-day 99% VAR, you might analyze, say, the last 500 days of your portfolio's returns, rank them from best to worst, and identify the 5th worst daily loss. That dollar amount becomes your 99% VAR. It relies purely on past observed data.
And the benefit is simplicity, I assume.
Simplicity. It makes no complex distributional assumptions.
But the drawback seems pretty obvious. If the last 500 days were, I don't know, unusually calm, your VAR is going to look deceptively low.
Exactly.
If the last 500 days failed to capture a period of systemic financial distress, like 2008, your calculated risk will be totally blind to it.
That's the fundamental weakness. It assumes market dynamics and correlations just remain static, which they don't.
Okay, so that leads to the second method.
The second method is parametric or variance-covariance methods. This approach moves away from relying exclusively on historical observation by assuming specific mathematical distributions for returns.
Here comes the bell curve again.
Here comes the bell curve. This is where that normal distribution assumption comes right back into play. If you assume normality, you only need 3 inputs: the mean return, the standard deviation or volatility of the returns, and the correlation between the assets. With those 3 inputs, you can mathematically derive the loss threshold X using statistical tables.
This sounds far faster and more elegant than historical simulation, but it carries a huge conceptual risk, doesn't it? If returns are not normally distributed, and we know they aren't because financial markets have those fat tails we discussed,
Right.
then that mathematically derived var number X is going to fundamentally underestimate the probability of extreme losses.
That is the crucial trade-off. Parametric VAR is computationally quick. It requires minimal data, which makes it very popular, but it often fails, sometimes catastrophically, during periods of high market stress because those extreme events are precisely the ones it mathematically minimizes or just plain ignores.
Which leads us to the third and most computationally sophisticated method, Monte Carlo simulation. How does this one attempt to solve the problems that we see in the first two?
Monte Carlo simulation is an attempt to create a more realistic, a more custom-built loss distribution. So instead of looking at past data or just assuming a simple mathematical curve, the analyst builds a complex model of the financial system.
A model of everything.
Well, a model of how assets interact, how volatility changes over time, how interest rates or inflation might behave. They then run thousands, sometimes millions, of simulated future days or future paths using random inputs drawn from the assumed distributions of those underlying variables.
And then they just watch what happens.
You watch what happens, and they observe the distribution of the resulting simulated losses to find the VAR threshold.
So it offers greater flexibility than the first two methods because you can explicitly model non-normal distributions and changing correlations.
You can.
But it seems like it introduces a massive dependence on the expertise of the modeler who's building that system.
Absolutely. The quality of the Monte Carlo VAR is 100% dependent on the quality of the stochastic model that was built. If the modeler designs a poor relationship between variables, or if their distributional assumptions for the underlying random inputs are wrong, the resulting VAR number will be precise, but it will be precisely inaccurate.
And the common thread across all three of these is undeniable. They all depend critically on the quality of the economic and statistical forecasts. It really turns VAR into a projection, not a certainty.
Never a certainty.
And that forecast dependency is a crucial insight we have to drill into. It shows that VAR isn't some objective, immutable truth. It's a consequence of the modeling assumptions used to create it.
Yes.
Our sources stress that VAR depends critically on two forecasted elements in particular: forecasted volatility and correlations among variables. Why are those two elements so central to the risk calculation?
They are the twin engines of portfolio risk. Volatility is pretty straightforward. It dictates the breadth of the expected loss distribution.
How wide the outcomes could be.
Exactly. If your forecast predicts a quiet market, the distribution will be narrow and your calculated VAR will be small. If volatility is high, the distribution spreads out and VAR increases. The model is highly sensitive to even minor changes in the volatility forecast.
Correlations, though, seem far more dangerous because they involve multiple assets and they're often the source of systemic failure.
They're insidious. And that's because the primary benefit of holding a diversified portfolio is the assumption that your assets do not move in lockstep.
They balance each other out.
Right. VAR models typically assume that assets behave independently, or at least according to stable historical correlation patterns. When one asset performs poorly, the lack of correlation means another asset might hold steady or even increase, which offsets the loss.
But history shows us that during systemic crises, that diversification benefit it evaporates.
It completely evaporates. We see what is often called correlation collapse or correlation contagion. During periods of panic like the 2008 financial crisis, correlations often collapse toward +1.
Meaning everything goes down at once.
Everything. Everything suddenly moves down together. Your assumed benefit of diversification is gone. So if your VAR model assumed historical low correlations, but in a crisis, all your assets suddenly move in lockstep towards zero, the entire portfolio loss distribution shifts dramatically.
And your VAR number is useless.
It's worse than useless. It's dangerously obsolete. It grossly underestimates the true risk.
And that leads directly to the consequence of poor forecasting. If the model poorly forecasts the volatility, or if the assumed correlations break down, what's the immediate tangible danger for a bank or a large financial institution?
The danger is immediate and profound. Risk is either underestimated or dangerously overestimated. If volatility is underestimated, the firm believes its assets are safer than they are. This leads them to hold insufficient capital reserves against potential losses, which exposes them to unexpected insolvency during a sharp downturn.
And if correlations are underestimated,
which is a common failing preceding major crises, then the diversification benefit is overstated, and the risk manager believes their large, complex portfolio is far safer than it proves to be. So accurate forward-looking forecasting, it's not an academic exercise, it is absolutely essential for the reliability of the entire VAR structure.
Okay, so let's address the central critique of VAR, the one that really gained prominence after the 2008 meltdown. Our source material highlights VAR's major limitation. It does not measure the severity of losses beyond the VAR threshold.
Correct.
It's completely silent on what happens in the tail risk, that worst extreme 5% or 1% of outcomes.
This limitation is not a footnote. It is the source of profound systemic risk if VAR is used in isolation. Let's use an analogy. Imagine VAR is like a flood defense system.
Yeah.
If you calculate a 95% VAR of $10 million, you've effectively built a dam wall that's 10 meters high. It's sufficient to stop the vast majority, 95%, of storms. But VAR tells you absolutely nothing about the height of the flood if the storm is a catastrophic 1-in-100-year event.
So you could have two different towns, let's call them Portfolio A and Portfolio B, that both have a 95% VAR of $10 million. Their dams are the same height.
Right.
But for Town A, the worst 1% of floods only slightly tops the dam, maybe causing $11 million worth of damage. But for Town B, the worst 1% is a catastrophic tsunami causing $100 million in losses.
That is the perfect illustration.
Right.
VAR treats both of those portfolios as equally risky because it only looks up to the 95th percentile, or 99th, whatever is chosen. It focuses on the likelihood of the constraint being breached within the main body of the distribution.
Not the magnitude.
Not the magnitude of losses in the extreme tail. The failure of VAR is that it cannot distinguish between a merely large loss and an existential loss that threatens the entire institution.
And this blindness to the tail risk has to have profound consequences for risk management behavior, which brings us to this issue of sensitivity and false security. If VAR is overly sensitive to model assumptions and it ignores extreme events, what's the resulting behavioral consequence of using it as the primary risk metric?
The consequence is a dangerous false sense of security and, critically, a distortion of incentives. When a risk manager reports a VAR number, it provides comfort. It's a clear metric for compliance. We know what we can lose, and we have the capital reserves to cover it.
But if you know that regulators or your board are only looking at the 99% line, why would you ever spend money protecting against the 99.9% line?
You wouldn't, exactly. It implicitly encourages decision makers to optimize their portfolio structure to pass the VAR test, to make their portfolio look safe up to the 99th percentile, while potentially increasing their exposure to those rare but catastrophic 1% losses that VAR is statistically designed to ignore.
So it's a kind of regulatory arbitrage.
It's the definition of regulatory arbitrage. The risk manager might structure derivatives or use financial engineering to shift risk just outside the measured confidence boundary, making the model look safer than the underlying economics would suggest.
So they are essentially building a portfolio that is optimized for efficiency and compliance under normal conditions, but is dangerously fragile when it's faced with extreme systemic shocks. That sounds like a perfect description of the fragility that was exposed in 2008.
It is. Many institutions, relying heavily on parametric VAR or historical VAR models that were based on pre-crisis, tranquil data, they were confident because their calculated risk numbers were low. The models failed catastrophically when the underlying assumptions, especially stable correlation and non-fat-tailed distributions, broke down under the stress of the market. The very act of reporting and relying on a single VIR number masks systemic fragilities that were hiding in that unmeasured tail.
And to try to address this, I know regulators and practitioners now often turn to a sibling metric. I think it's called conditional value at risk, or CVR.
CVR, or expected shortfall, yes. It specifically measures the expected loss within that extreme tail region, which gives a much better picture of the severity of the disaster. But that's probably a conversation for another deep dive.
It is. So let's zoom out and try to put the pieces together. We've got chance constraints on one hand, focusing on operational feasibility under uncertainty.
Yeah.
And on the other hand, we have value at risk, focusing on financial loss magnitude.
Right.
They are both probability-based risk controls, but they serve different yet highly complementary functions in the decision analytics framework.
That's the core synthesis. Their functionalities are distinct, but they inform the same final decision. Chance constraints are fundamentally centered on the feasibility of decisions.
The operational side.
The operational side. The question the CC asks is, given that our inputs like demand or price or delivery time are uncertain, can we construct a solution that meets all specified operational requirements, delivery time, inventory levels, supply assurance, with a high degree of confidence? It defines the space of allowable, functional solutions.
So CC is the tool used by the operations manager, the supply chain lead, or the engineer.
Exactly. Whereas VAR focuses entirely on the magnitude of potential losses, the financial outcome. VAR asks the finance and risk officer, if we choose this particular solution, the one the operations manager optimized using CCs, how much capital must we set aside?
Or what's the worst we can lose?
What is the absolute worst dollar loss we can expect at this confidence level over the next quarter? It's a direct quantification of the financial downside risk that's inherent in the operation.
Which implies they aren't mutually exclusive at all. They're often used together to provide a comprehensive, sort of 360-degree risk management strategy. Can you walk us through a specific integrated use case, maybe in a large corporation planning a major project?
Yeah, let's take the case of a major automobile manufacturer. They're planning to invest billions in a new electric vehicle platform and the associated manufacturing capacity over the next 5 years.
Okay, huge, uncertain project.
Huge uncertainty. First, they use chance constraints to design the production schedule and the supply chain. They know future battery material costs are volatile, and future demand for specific models is uncertain.
Right.
So they use CCs to find the optimal manufacturing capacity level, how many lines to build, how much raw material to contract for, such that they meet forecasted customer demand, for example, 97% of the time, while keeping their operational costs within budget 95% of the time. The CC framework guides the physical, the operational structure of the investment. So CC is defining the structure that maximizes efficiency while respecting these probabilistic limits of failure. Correct. Now, once the CC model delivers that optimal physical plan, the financial risk team steps in. They take that plan with its associated inventory, its commodity contracts, its capital expenditure, and they apply value at risk.
And what do they ask?
They ask, given the volatility and correlation assumptions associated with that 3% chance of a demand shortfall, the risk allowed by the CC, what is the 99% maximum expected loss in terms of capital write-downs or unexpected commodity price swings over the next 2 years.
So the VAR then determines the financial cushion that's required. It tells the CFO exactly how much contingency capital they need to secure, or maybe how much hedging they need to execute to ensure the overall stability of the firm, even if the operational chance constraints are breached.
The integrated use ensures the decision is operationally feasible, thanks to CC, and financially sound, thanks to VAR. The CC minimizes operational waste by accepting calculated risk. The VAR protects the firm from insolvency by quantifying the downside cost of that calculated risk.
And this really highlights the broad, diverse use of these tools in the real world. We've talked about portfolio allocation under uncertainty, which is sort of the classic use case. But we also see them critically applied in capital budgeting and investment planning, really any time a company commits major funds to a project with uncertain returns.
Absolutely. When you're assessing a massive mining operation or the R&D budget for a decade-long pharmaceutical trial, you use these probabilistic tools to model the expected payoff versus the maximum potential capital loss. It transforms what is a qualitative business gamble into a quantifiable, structured bet where the risk is managed mathematically.
Another key application mentioned in our sources is stress testing and scenario analysis. And this seems to be where the structural limitation of VAR, its blindness to the tail, is deliberately addressed.
It is.
You use VAR to define the normal risk boundary, and then you use stress tests to explore the unmeasured domain beyond that boundary.
Stress tests are essentially manually forcing the system into that 1% tail that VAR ignores. You simulate extreme, non-historic events, a global pandemic, a sudden 50% drop in housing prices, a major war, and you see what happens to the capital position.
And this is mandatory for regulators now, right?
It is. The VAR tells you the risk you expect. The stress test tells you if you can survive the risk you don't expect.
And finally, these tools guide policy decisions involving fiscal or financial risk. When governments are creating national budgets or setting monetary policy, they're using probabilistic modeling to ensure outcomes like debt-to-GDP ratios or inflation targets remain within acceptable bounds with a high level of probability.
Definitely. A central bank might use CC-like principles to ensure inflation remains within a target range, say 2% plus or minus 1%, with 90% certainty. And then they'd use VAR principles to quantify the maximum capital injection required to stabilize the banking sector in the event of a sudden severe recession. These aren't just tools for traders, they are tools for managing national stability.
Okay. Lot to process there.
So I think the final takeaway today is that decision analytics transforms the ambiguity of uncertainty, all the maybes and the what-ifs, into manageable, quantifiable parameters. By utilizing probabilistic constraints like chance constraints and loss metrics like value at risk, organizations move beyond simple expected averages to make informed choices that explicitly manage and control downside potential.
And for you, the listener, you now understand the language of institutional risk. You know how decision makers define operational feasibility and how they use these single-dollar figures to incorporate true, quantifiable downside risk into every major decision they make. This is really the difference between just hoping for the best and actually planning for the worst.
But let's return to that limitation we developed in detail. The regulatory dependence on VAR and its inherent blindness to the extreme tail. If VAR models are sensitive to extreme events, and they do not capture the severity of losses beyond the defined confidence level, that critical tail risk. And if these models rely entirely on assumptions about probability distributions, which are, let's be honest, often simplistic,
Then what?
then does the widespread regulatory reliance on VAR actually encourage systems that are highly optimized for likely events, but dangerously fragile during unprecedented shocks? Should we, as a global financial and operational community, be optimizing our systems more for that 1% failure state that VAR explicitly ignores, even if it means sacrificing some of the enormous efficiency gained by using chance constraints at the 95% level? Something to consider the next time you hear a news report about an event that was unforeseen by the experts.
If you are running a business, maybe managing a massive supply chain, or even just trying to decide the capital layout for a new facility, you operate in a world that's really just defined by the unknown.
Absolutely.
You have to make these huge, costly decisions right now, but the future environment they have to operate in, things like customer demand, machine failure rates, global logistics delays, all of that is inherently unknowable.
Right. And traditional mathematics, I mean, the neat formulas we all learn in school, they're just not built for that level of chaos. They can't handle it.
Not all.
That's really the core tension of modern operations. You can try to force all that complexity into a standard optimization model, sure, but those models are fundamentally built on deterministic assumptions.
What do you mean by deterministic?
They assume that if you put X in, you will get Y out, always, every single time. The moment real-world noise enters the equation, and noise is inherent in literally everything, your perfectly optimized deterministic solution becomes brittle. And frankly, often just plain wrong.
Which is exactly why we're here today. We are doing a deep dive into the analytical heavy hitter that's been designed specifically to thrive in this noisy environment. We are talking about simulation optimization.
Or SO, as you'll often hear it called.
Right, SO.
And simulation optimization is really the necessary bridge between that theoretical perfection we just talked about and the actual operational reality on the ground. It's the art and the science of finding robust, optimal decisions when you are dealing with a system that's so complex, so full of randomness and feedback loops that you just cannot define its behavior with a single clean equation.
Okay, let's break that down, because the term itself, it's really two core technologies working together in tandem. First, you have the simulation models. They're like the digital laboratory, right? The engine that runs and evaluates the performance of your system over and over again. And this is the crucial part, under uncertainty.
Exactly. And second, you have the optimization techniques. This is the intelligence. This is the search mechanism that takes all that performance feedback from the simulation and then actively searches for the best possible set of, say, managerial decisions to input into that model. It's a dynamic learning loop.
So what we're aiming for here, the ultimate goal of SO, isn't just to find a decision that works once, but to identify decisions that optimize the expected performance. That distinction it's paramount.
It's everything.
We aren't looking for the one perfect deterministic outcome, because that outcome, it might only happen in a tiny fraction of all possible scenarios. We are optimizing for performance that is statistically reliable and robust across the full range of possible futures.
It's the difference between planning for your best day and planning for the average of all possible days, especially the really stressful ones. You're optimizing against the statistical average of what the future could hold, which, that includes the risk of catastrophic failure and the possibility of extraordinary success.
Okay, so let's unpack this. And maybe let's start with the philosophical question here. Why do we even need this level of complexity? If traditional mathematical optimization has worked for decades, why are modern systems suddenly demanding this elaborate two-part combination?
Well, it's because the systems themselves have changed. Traditional optimization, often relying on calculus or linear programming, it's fantastic for simple, well-defined problems where relationships are proportional and variables are constant. But those techniques, they just break down when they're faced with the reality of modern business.
And the sources we looked at detail 3 key characteristics of real-world business systems that make that traditional optimization pretty much impossible. They really explain why the nice, clean math is, well, instantly useless.
That's right. The first characteristic is that modern systems are highly stochastic.
Stochastic, that just means random, right?
It means there's an inherent presence of randomness, yes, but it's more structured than just random. To put it simply, we are dealing with systems where key variables are governed by probability distributions, not single fixed values.
Okay, give us an example.
Think about a retail checkout line. We can model customer arrival times with a probability distribution, let's say a Poisson process, which is pretty standard for random arrival counts over time. We might know the average rate, maybe 10 customers an hour.
But the actual arrival count in any given minute is like a roll of the dice?
Exactly. And if you have 5 cashiers and all 5 of their checkout times are also random variables, say they follow an exponential distribution, you now have 10 interacting random processes just to determine something as simple as the average queue length.
And if you try to replace those distributions with a single number, a simplifying average, what you call the deterministic trap,
You miss the most critical part. You miss the interaction of those random variables that causes the bottlenecks in the first place. It's the coincidence of a really slow service time happening at the exact same moment as a high arrival rate that creates the crisis. The average model will never, ever capture that possibility.
okay, that makes sense. So that's stochasticity. What's the second characteristic?
Secondly, we have highly nonlinear relationships. In that deterministic world, we like to assume proportionality. If I double my warehouse size, I have my stockout probability, nice and clean.
But reality is never that clean.
Never. In a complex logistics network, doubling your capacity in one single node might completely overload the entire preceding rail line. That could create a downstream bottleneck that actually increases your overall cost because of storage backlog. That non-proportional, non-linear response is impossible to capture effectively using traditional algebraic methods without, resorting to huge complex equations that just become unmanageable.
And thirdly, you mentioned complex feedback loops and interactions. What does that mean?
It means that systems don't just progress forward in a straight line, they react to themselves.
Ah, okay.
Think about a classic queuing theory model, the kind you learn about in school, MM1, which is a deterministic ideal. In reality, if your wait time goes up significantly, a customer might just give up and abandon the queue.
Sure, happens all the time.
Right. And that abandonment changes the demand dynamics for the whole system. Then, if your wait time suddenly drops, other customers might notice and decide to wait, increasing the demand again. It's a living system. Traditional optimization models struggled profoundly to incorporate these continuous dynamic adjustments that are based on the system's own performance.
So if you model a system assuming fixed inputs, that deterministic trap again, the resulting decision, your so-called optimal inventory level, or your staffing solution, whatever it is, becomes incredibly brittle.
That's the word for it, brittle.
It only works flawlessly on the one specific day you modeled, a day which may never actually arrive.
So the necessity of uncertainty, it's a fundamental design parameter for any robust decision-making framework. Simulation optimization forces your decisions to be evaluated not just in a single ideal vacuum, but across a whole spectrum of possible realities. It models the inherent randomness that really characterizes the real operational world.
What's fascinating here is how SO addresses this complexity where analytical or what are called closed form solutions simply aren't available. It almost sounds like you're conceding defeat to the pure mathematician, saying, look, I can't write the perfect formula, so I'm just going to model it instead.
That's exactly the insight. It's a very pragmatic admission. In high-stakes, highly interactive systems, like, say, optimizing air traffic control sequences under unexpected weather or designing a triage system in a hospital's ER, the resulting system behavior is just too complex and the outcome's too uncertain to derive a perfect equation.
There's no single formula.
There is no single formula that perfectly maps the optimal inputs to the optimal outputs. So we have to create a virtual world and just test the inputs over and over until we find the best statistical outcome.
You are replacing mathematical derivation with computational experimentation.
Precisely. You are running the system's life thousands, maybe millions of times to understand the full probability distribution of outcomes associated with one specific managerial decision. Without that sophisticated simulation capacity, any high-stakes stochastic decision is just reduced to an educated guess.
So let's break down those two engines that power this robust method. Let's start with the simulation side, the part you called the evaluator.
Right. The simulation model is the operational heart of the entire process. Its role is, well, it's simple in concept, but incredibly complex in execution. It replicates the system's behavior over time under all the defined random elements.
So if you tell the model, staff 10 nurses, what does it tell you back?
The simulation tells you, okay, based on these patient arrival distributions and these random service times you gave me, here is the resulting average wait time, the utilization rate, and the total cost over a simulated year of operation.
And the mechanism it uses for this is more sophisticated than just running some averages, right? It generates possible outcomes by repeatedly sampling from probability distributions.
That's the critical mechanism. That's what introduces the realism. We use what is essentially a highly refined version of Monte Carlo sampling. For every stochastic variable, say the time between customer arrivals, we define its probability distribution. Maybe it's an exponential distribution, for example. The simulation model then uses a stream of pseudo-random numbers, what's known as the random seed, to draw values from that distribution.
So if the average arrival rate is, say, 10 customers per hour, the simulation doesn't just plug in 10 every hour.
No, that would be deterministic. Instead, the random number generator pulls a value, and maybe it's 8.3 minutes between arrivals for one customer, and then it pulls another, and it's 1.1 minutes for the next, then maybe 15 minutes for the third. It replicates the realistic clustering and the gaps that you see in real life.
And this is happening for all the random parts of the system at the same time.
Simultaneously, across all random variables. The service time for that first customer is drawn from its service time distribution. The arrival time of the next customer is drawn from its arrival distribution. It's the complex interaction of these thousands of simultaneous random draws, all governed by their appropriate statistical distribution, that generates the realistic messiness of operational reality.
And we can categorize the type of uncertainty that is typically modeled here. I mean, these are the inputs that make or break how realistic the simulation actually is.
The source material really highlights the fundamentals. Customer arrivals are the core source of demand in any service industry, and accurately modeling their distribution is absolutely essential. Demand fluctuations are critical in retail or manufacturing. There, you might model the distribution of, say, order size or daily sales volume. Then you have service times, which dictate your resource utilization and your queue behavior.
And I imagine you can model even broader variables like market responses to a pricing change.
Oh, definitely. That might involve modeling the probabilistic outcomes of competitor actions or consumer uptake rates. The point is, if the model is constructed correctly, running it thousands of times gives you a statistically valid picture of the full range of possibilities for that one specific decision.
So essentially, the simulation answers the core question for the system. What happens to my key performance indicators, my profit, my wait time, my utilization, if we choose this specific set of decisions? It's the performance feedback mechanism.
Exactly. It's the report card.
Okay, so that's the evaluation side, the report card. Now we have to flip to the second engine, the optimization side, or the searcher, as you put it. The simulation just tells us that decision A resulted in an expected profit of $10 million. The optimization piece has to look at that result and decide whether to try decision B or C or maybe Z next.
And that's a huge challenge. The role of optimization is to intelligently traverse a vast, complex landscape of possible decision alternatives. Remember, if you have just 5 variables, let's say inventory level, staffing, shift timing, pricing, and supplier choice, and each of those has hundreds of possible values.
The decision space is effectively infinite.
It's astronomically large. An exhaustive brute force search is computationally prohibitive. You could never do it.
So the optimization has to be smart. And its 2 main purposes are, first, determining which decisions to test out of that nearly infinite number of possibilities, and second, determining how to move toward better performing solutions based on the results of the previous tests.
And this creates the critical self-correcting feedback mechanism we mentioned earlier. The optimizer uses the simulation results, that expected profit, the average wait time, as its sole performance feedback. If it tries decision A and gets 10 million, and then it tries decision B and gets 12 million, the optimizer now knows the direction of improvement in that local region of the decision space.
We can actually detail the core loop that's central to SO right here. It's this continuous, iterative learning process. Step 1, choose decision. The optimizer selects a new set of input variables based on its past learning.
Right, then step 2, simulate. The model runs thousands of times to evaluate the performance of that decision under uncertainty.
Then step 3, evaluate. The optimizer receives the statistically stable performance metric, that expected value. And finally, step 4, improve decision.
And in that last step, the optimizer adjusts its internal model of the world and selects the next choice, iteratively moving toward what it believes is the optimal decision region.
And this loop just runs and runs.
It runs until a predefined stopping criterion is met. Maybe that's a budget constraint on computation time, or maybe a hard time limit, or simply when the optimizer determines that the statistical improvement between subsequent decisions is negligible. It's basically constantly refining its map of the decision landscape until it finds the highest statistically proven peak.
It really sounds like we're building a specialized AI, one that's designed just to learn the perfect operational policy for our specific system.
That's a very good way to think about it.
But before those engines can even start running, we have to clearly articulate the problem space. And this brings us to section 3, defining the decision space. What can we control? What are we trying to achieve? And what limits are imposed by reality?
This is so critical. Setting up the decision space correctly is often harder than running the optimization itself. I mean, garbage in, garbage out. It's an old saying for a reason.
So we start with the decision variables. These are the controllable choices. These are the levers you can actually pull as a manager, and they're the inputs to the simulation model.
Exactly. And these variables can range from the very strategic to the very tactical. Strategic examples might be inventory levels for essential raw materials, or maybe budget allocations across different marketing channels. Tactical examples would be staffing numbers on various shifts, the exact personnel count, or maybe even service policies, like the threshold time after which a customer receives an automated apology or a discount.
And the optimizer's sole mission is to select the exact optimal values for every single one of those decision variables, and to do it simultaneously, ensuring they collectively improve the system's outcomes.
Which leads us directly to the next piece, the objective function. This is the performance meter. If the variables are the controls you're turning, the objective function is the definition of success. It's the metric that the optimization is tasked with either maximizing or minimizing.
So we might define success as minimizing the average patient waiting time in that ER we talked about.
Or maximizing expected revenue from a new product line. Or maybe minimizing the total integrated cost of logistics, which would include both shipping and inventory holding costs.
And here is where that stochastic nature is critical again. Because the outcomes are random, these objectives are almost always calculated as expected values over many, many simulations.
You have to. You can't just run the model one time and report $10 million in profit. That number is meaningless. You need to run it, say, 10,000 times, calculate the mean of those 10,000 results, and then report that mean as the expected profit.
which means the accuracy of that performance estimate, that expected value, is directly proportional to the computational time we're willing to spend.
Exactly. If you only run 100 simulations, your expected profit figure is highly vulnerable to just random statistical noise. If you run 100,000 simulations, your expected value is much more stable, but you've now spent 1,000 times more computational resources.
That fight between reliability and speed must be the analyst's daily struggle.
It absolutely is. We're trying to find the statistically best answer while racing the clock.
Okay, so we have variables and objectives. Finally, we have the constraints, the rules of the game. I mean, the optimal decision for a manager who has an unlimited budget is pretty trivial. Constraints are what impose reality.
Constraints define the feasible decision region. The search engine can only look for solutions that satisfy these limits. The most obvious constraints are what we call hard constraints. These must always be satisfied, no exceptions.
It's like physical capacity restrictions. You can't deploy more trucks than you actually own.
Or absolute budget limits. If exceeding the constraint means the solution is literally impossible to implement, it's a hard constraint.
But the sources we looked at also distinguish an interesting nuance. Soft constraints.
Right. Soft constraints are typically policy rules. A soft constraint might be something like, we must ensure that no more than 5% of our customers wait longer than 5 minutes.
Okay, so violating that policy isn't physically impossible, but it carries a pretty severe penalty.
Exactly. It's not good for business.
So how does the optimization handle a soft constraint like that?
We integrate a penalty function directly into the objective function itself. If the system finds a solution that causes, say, 10% of customers to wait over 5 minutes, that violation incurs a large, sometimes crippling, fictional cost or negative value in the objective function.
So it makes the bad solution look less attractive mathematically.
It effectively pushes the optimizer away from solutions that violate the policy, even if that violation would otherwise yield a slightly higher expected profit. It allows for highly profitable yet non-compliant solutions to be technically explored by the algorithm, but it penalizes them into infeasibility for the final decision.
So the optimization engine has to search only within the boundaries defined by all of these hard and soft constraints. It's looking for the globally optimal expected outcome within the limits imposed by budgetary, physical, and policy realities.
It creates a boundary, a fence, around the solution space. We are trying to find the best possible outcome in the real world, not the best outcome in some imaginary rule-free landscape.
Okay, here's where it gets really interesting, and I imagine where the computational demands just explode. How do they handle the inherent uncertainty when the outcome is constantly shifting just because of the random numbers being drawn? This feels like the core challenge that sets simulation optimization apart from all other analytical methods.
You've hit on it. We are squarely in Section 4, the challenges of noise and computation. We are talking about the stochastic nature of evaluation. This is the noise problem.
Let's imagine we are testing a simple inventory policy. We run the simulation 1,000 times and we get an expected profit of, say, $12 million. Then we immediately run the exact same policy again for another 1,000 runs, just using a different set of random numbers. You might get $11.8 million this time. The policy didn't change at all, but the result did.
That variance, that difference between $12 million and $11.8 million, is the noise. Since the simulation is constantly sampling from probability distributions, the same decision inputs produce different outcomes, because the sequence of random events, the virtual dice rolls for arrivals, service times, and failures, are different each time. This inherent randomness introduces noise into the performance evaluation feedback loop.
And this must create a crisis of confidence for the optimizer. If the optimizer is testing a slightly different inventory policy that yields $12.1 million, how does it know that the $100,000 improvement is actually real and not just a lucky sequence of simulated demand?
This is the moment where statistics meets optimization. This is the whole ballgame. The optimization routine has to rigorously distinguish between true performance improvement, a genuine shift in the decision variables that benefit the system, and the inevitable random variation introduced by the simulation process itself.
So that raises a really important question. How do you trust the feedback when the data is inherently so noisy?
You can't. You cannot rely on point estimates. You have to rely on confidence intervals and statistical procedures. We don't just ask, is decision B's expected value higher than decision A's?
What do you ask instead?
We ask, is decision B's expected value statistically significantly higher than decision A's, considering the variance of both?
So it's a statistical test. So if the confidence interval of the $12 million profit estimate from decision A significantly overlaps with the confidence interval of the $12.1 million estimate from decision B.
Then the optimizer might conclude that the perceived $100,000 improvement is statistically insignificant, that it's just noise, and the search should move to a completely different region of the decision space. It's not a real improvement.
And how is that actually implemented?
It's often implemented using statistical comparison techniques known as ranking and selection, or R&S procedures. R&S specifically allows the optimizer to discard inferior choices quickly while investing more simulation runs, and therefore more computational time, in the most promising candidates, until those candidates are statistically distinguishable from each other. It forces the search to be data-driven and, well, conservative.
And since evaluation is so computationally expensive, I mean, you said we might need 10,000 runs just to get one stable expected value, the optimizer cannot afford to just wander aimlessly or test every possible combination.
Absolutely not. As we noted, an exhaustive search is computationally impossible for any realistic problem. Therefore, SO relies entirely on intelligent search strategies.
And these strategies have to avoid getting stuck, right? They have to avoid the local optima where the search gets stuck thinking it found the best answer, only to discover the truly best answer was far away on the map.
Exactly right. They employ sophisticated methods, often referred to as heuristic or meta-heuristic approaches. One of the most famous examples, and one that really beautifully illustrates the concept, is the genetic algorithm.
A genetic algorithm, how does that approach SO?
Okay, so a GA treats potential solutions. That set of decision variables, like inventory 500, staffing 10, price 15 as individuals, or chromosomes. It starts with a whole population of random solutions. Each solution in that population is simulated, and its performance, its fitness score, is evaluated. The best performing solutions are deemed fit.
And then just like biological evolution.
Precisely. The fittest solutions are selected to reproduce, which is a process called crossover, where they combine parts of their variables to create new hybrid solutions. And we also introduce mutations, small random changes to the variables, to ensure the search doesn't get stuck in one place and can explore entirely new, unexpected regions of the decision space.
So it's this evolutionary pressure that guides the population toward better performance over successive generations.
Yes, effectively traversing that complex, noisy landscape in a very efficient way.
And that explains why these methods are preferred. They sacrifice the mathematical guarantee of finding the absolute perfect global optimum for robustness and computational efficiency. The result is always approximate, not guaranteed optimality.
It's the necessary trade-off. It has to be. We exchange theoretical perfection for practical, robust utility under uncertainty. We found the best answer we could find for this model, and statistically, it's highly unlikely a significantly better one exists, but we can't prove mathematical perfection.
Which leads us directly into the analyst's nightmare, the accuracy versus computation trade-off. This has to be the great tension in the field.
It's a constant tug-of-war. We know that more simulation runs improve the accuracy of our expected performance estimates. If we move from 100 runs to 10,000 runs per decision, our confidence interval around that expected profit shrinks dramatically.
Which means we have much higher confidence that the difference between decision A and decision B is real and not just noise.
But 10,000 runs is 100 times more computational work.
Yeah.
And if your search strategy requires evaluating, say, 1,000 different decision points, that speed difference scales up massively.
Yeah.
What takes an hour with 100 runs now takes 4 days with 10,000.
And conversely, if you use fewer simulation runs just to get a quick answer, the process is fast, but the trade-off is higher uncertainty. You have wider confidence intervals. You risk making a costly managerial decision based on results that were just statistical noise.
So the analyst must constantly balance the need for precision, a tight confidence interval, with the critical need for decision timeliness. I mean, a good enough decision delivered in time to meet the quarterly budget deadline is instantly more valuable than a mathematically perfect answer that arrives 3 months too late.
Right.
The analyst has to determine the acceptable level of risk introduced by the simulation noise relative to the value of a timely decision. It's an operational constraint layered on top of all the mathematical ones we already talked about.
Okay, let's transition now to how this complex, computationally heavy, statistically noisy approach actually translates into tangible, real-world value for businesses. Why should a company invest in this level of analytical machinery?
The advantages of the approach become really clear when you just recap the core strengths. It's the only analytical technique that can handle complex systems, inherent uncertainty, and interdependent decisions simultaneously without having to simplify the messy reality.
The major benefit, the one that probably excites system architects, is that SO doesn't require all those sweeping, simplifying assumptions that are so common in traditional models. You don't have to assume service times are constant or linear. You can actually model the real complexity.
You can include incredibly specific real-world details. Cross-train employees who work faster in some departments but slower in others, machines that fail following a very specific Weibull distribution, or supply prices that fluctuate daily. The fidelity of the model can be extremely high.
And the end result of all this searching and statistical confirmation is the production of solutions that are robust under variability. They're designed to withstand the stress test of the simulation.
A staffing policy derived through SO is robust, precisely because it has already been tested against hundreds of simulated spikes in customer demand, employee sick days, and machine failures. The solution won't just optimize for the average day, it optimizes for the worst possible days, ensuring the system degrades gracefully rather than just collapsing immediately.
The source material gives us some fantastic examples of typical business applications. Let's try to make this real for the listener by walking through a few detailed scenarios.
Let's start with a classic one, call center staffing. Call volumes are the absolute definition of stochasticity. They are governed by the time of day, the day of the week, ongoing promotions, and completely random external events.
So a large call center needs to determine how many agents to schedule for every single 30-minute block throughout the week, while also maintaining a really strict service level like, say, 80% of calls have to be answered within 20 seconds.
Right. The decision variables here are the staffing levels for each of those intervals, and maybe the cross-training level of the agents. The objective function is typically a minimization of the total operating cost, which is mainly labor cost, subject to the hard constraint that the service level target, that 80-20 rule, must be met at all times.
So why does SO beat just a standard spreadsheet forecast here?
Because a spreadsheet might forecast an average of 100 calls between 9 and 9:30 a.m. If you staff for exactly 100 calls, the moments when the volume randomly spikes to 120, or when two unusually complex calls randomly extend the service times, you instantly destroy your 80-20 target.
He failed the constraint.
Instantly. So the model's the probabilistic risk of not meeting that target, and the optimizer finds the most cost-effective staffing buffer to absorb those inevitable random spikes. It doesn't eliminate the uncertainty, it minimizes the operational exposure to it.
That makes perfect sense. Okay, let's look at another one. Inventory and supply chain planning. This is a perennial problem in retail and manufacturing.
Here, the goal is all about managing demand variability. Demand is never a fixed number. It's always a random variable. The manager needs to decide the optimal reorder points and safety stock levels for hundreds or even thousands of different SKUs.
So the decision variables are the reorder quantity and the safety stock level for each item. The objective function would be to minimize the sum of inventory holding costs, the cost of keeping stock on the shelf, and stock-out costs, which is lost revenue and goodwill.
And so vital here, because holding costs and stock-out costs are often nonlinear and highly interdependent. Holding too much stock might increase your inventory cost linearly, sure, but holding too little can lead to exponential losses in customer loyalty during peak demand.
So what does the simulation do?
The simulation runs thousands of years of random demand, random supplier lead times, and random shipping delays, allowing the optimizer to find the exact safety stock sweet spot that perfectly balances the risk of running out against the cost of capital tied up in inventory.
We also see extensive use in healthcare operations, specifically around capacity and resource allocation.
Oh, absolutely. Think about optimizing the flow of a new emergency department. Patient arrivals are stochastic, and the time required for diagnosis and treatment, the service time, is also stochastic and depends on the complexity of each case.
So the decision variables could be things like the number of triage nurses, the number of diagnostic imaging machines, and even the physical layout of the beds. The objective is often to minimize the overall patient length of stay or wait time while still adhering to budget constraints.
And Solus allows hospital planners to simulate the impact of these decisions on patient flow under extremely stressful conditions, like a mass casualty event or a seasonal flu spike. They can see, for example, that adding one more imaging machine reduces the average wait time by 50% only if they also add 2 more transport personnel to move patients. This kind of interdependence is something only a stochastic simulation can really uncover.
These results, however compelling they are still just decision recommendations, right? They're not guarantees. And that feels like the final critical piece of this puzzle, the layer of managerial interpretation.
This is arguably the most essential step, where the analytical output meets human judgment. The manager cannot treat the resulting policy as a guaranteed perfect answer. They must understand the inherent variability of outcomes that is associated with that recommended policy.
So instead of just reporting the optimal decision yields $12 million in expected profit, the analysis must show the full probability distribution.
Yes. What does the standard deviation around that mean? What is the chance of profit falling below 10 million? What is the worst case fifth percentile outcome? You need to show the whole picture.
Absolutely. The manager has to carefully assess the necessary risk-reward trade-offs. Analytically, we might find a solution that maximizes the expected profit, that $12 million number, but that solution might also carry a 1% chance of losing $5 million.
And the manager might look at that and say, we absolutely cannot tolerate that 1% catastrophic risk.
Right.
So they might choose a slightly less optimal solution, one that yields, say, $11.5 million in expected profit, but which has a 0% chance of falling below $9 million. This is often visualized through a concept called the efficient frontier, or Pareto front. It shows the set of solutions that are not dominated by another in terms of both their expected return and their risk. The manager then chooses the point on that frontier that aligns with the organization's specific risk tolerance.
So ultimately, simulation optimization supports risk-aware decision-making. It allows the management team to see the probabilistic consequences of their choices, allowing them to make a final decision that's informed by the system's noise and variability, rather than just aiming for a deterministic fantasy.
It completely changes the conversation. It moves from what is the single best answer to what is the most robust and secure answer for the level of risk we are willing to tolerate given the operational and financial constraints we face.
So, to sum up everything we've covered today, simulation optimization is the necessary tool for navigating complexity when systems are stochastic, interdependent, and when outcomes are uncertain. It trades the absolute mathematical certainty of traditional deterministic models for robust, risk-aware, approximate decisions that are tailored to the messy, real world.
It's the analytical framework for the modern operational world, a world forced to reckon with randomness at every single turn. It embraces the fact that you can't know the future, but you can statistically plan for the most probable and manageable versions of it.
So what does this all mean? It means embracing noise as an inherent part of the operational solution, not as some bug in the system. But we have to end with a thought that brings us back to that core limitation, the fact that this is all an approximation.
Indeed.
Yeah.
We spent a lot of time discussing how the optimization engine deals with noise and finds the best approximate answer. But that answer relies entirely on the quality and the validity of the initial simulation model itself.
Meaning, if the probability distributions you feed into the model, the customer arrival rates, the supplier lead time variances, if they don't accurately reflect current reality,
Then the optimal decision found by the optimizer will be perfectly optimal, but for a fictional system that doesn't actually exist.
And that's the critical final layer managers have to constantly assess. How much trust should you put in a decision framework that relies on approximate results? And maybe more importantly, how often must that model be revalidated and recalibrated to keep pace with changing real-world randomness, like shifting customer behavior, new economic patterns, or technology disruption?
The optimization loop finds the best decision for now, but the model calibration loop has to be continuous to make sure that now remains accurate. That's the ongoing work.